All the participants in the corridor may please join the Homi Baba auditorium and take the front seats. Please come in the front. Those who are sitting in the back seats, please come in the front. I request all the participants who are sitting in the back seats, please come in the front. I request participants who are in the corridor or in the tea area, please join the Homi Baba auditorium and take the front seats. We are now starting the session.
Good morning, everyone. After a hectic first day full of technical talks followed by a musical evening, we are back on day 2 of the 12th Indian Particle Accelerator Conference 2025. Today, there will be 3 technical sessions. This particular technical session will comprise of 3 talks and will be chaired by Dr. Vandana Nanal. Dr. Vandana Nanal is a senior professor at Department of Nuclear and Atomic Physics at Tata Institute of Fundamental Research, Mumbai. She is a life member of Indian Physics Association and Indian Society for Particle Accelerators. She has more than 100 technical papers in reputed journals and conferences. Now, I request Dr. Vandana Nanal to take her seat as session chair on the stage.
Thank you for a generous introduction and the invitation. We really had an exciting day yesterday, and we already heard about the outline of the session. So let us start. The first talk is on the status of Indus synchrotron radiation sources by Dr. Puntambekar. Puntambekar is mainly working in the synchrotron radiation sources and accelerator beam diagnostics. He is a world-renowned expert in these areas. He received an Homi Bhabha Prize and also the DAE Scientific and Technical Excellence Award. He has received DAE Group Achievement Awards, has more than 90 publications in journals and conferences. As I said, he is a world-renowned expert, and we will look forward to hearing from him. So over to you.
Good morning. Thank you, session chair, for kind introduction. And I thank organizers to give me opportunity to present this invited talk on the status of Indus synchrotron radiation sources. Specifically, I am happy, it's my pleasure to present this talk in presence of Shri Gurnam Singh Ji, who is present in person today. And he had been associated with the Indus accelerators right from the beginning. He has led the team which has designed these accelerators, beam dynamics design, and later on the commissioning and operation. Everywhere he led the team. So I am happy to present in front of him. This talk is, as I mentioned, it is on behalf of the complete Indus team. Indus team is a large team which comprises of many divisions who are involved in the development, maintenance, and operation of this Indus 1 and Indus 2 sources. So I'm presenting on their behalf, and this talk I'm prepared. Basically, it's a compilation of the inputs that I have received from various divisions, various experts who have contributed for making this presentation. So with this introduction, I go to start my talk. Okay. Huh? Okay. So this is the outline of my talk. I will give a brief introduction to Indus synchrotron radiation sources. Then I will talk about the status of Indus operation in terms of the operation statistics, and then some statistics on the synchrotron radiation utilization aspects. And then since we are developing various technologies to improve the performance of Indus 2, and also there are efforts to develop upgraded systems which replace the old and outdated systems in Indus 2. So I will be touching upon recent upgrades in Indus 2 and some of the technology developments which are targeted for our future improvements. Basically, I will be covering only the recent developments since the last INPAC, which was in March 23. So mostly I'll be covering the developments which have been done in the last 2 years. Then a major upgradation of Indus 1 storage ring has been completed in this year, in the last year. So that I will touch upon, and now in the end I will summarize. So this is the schematic of our Indus facility. And this Indus 1 and Indus 2, they are indigenously built synchrotron radiation sources operating in round-the-clock mode since February 2010. Indus 1 was commissioned in 1999 and Indus 2 was commissioned in 2005. However, their regular operation in 3-shift mode started from February 2010. And from April 2010, these sources are being operated by the trained operation crew members. Presently in Indus 2, there are 20 beamlines, out of which 18 beamlines are user beamlines and 2 beamlines are diagnostic beamlines. And Indus 1, there are 7 beamlines. The facility consists of a microtron, which is a pre-injector. It is a 20 MeV accelerator. The electrons are generated from a LiB6 cathode and accelerated to 20 MeV. And these electrons in the form of pulse of around 500 nanosecond at repeating at 1 Hertz, they are injected into booster, which increases the energy of these electrons to either 450 MeV for injection in Indus 1 or 2.5 GeV for injection in Indus 2. And then these are injected into Indus 1, which is basically a storage ring, 450 MeV and 125 milliampere. And there is a magnet here, switching magnet, by which we can divert the electrons either to Indus 1 or Indus 2. So for filling in into Indus 2, this booster is operated at 550 MeV and the electrons are injected into Indus 2 through TL transport. TL is transport line 3 and it is accumulated. Indus 2 is a booster cum storage ring, means there is a ramping, energy ramping, and then there is a storage of electrons. And the specifications are 2.5 GeV and 200 milliampere of beam current. The green ones here, they show the beamlines, synchrotron radiation beamlines which are operational. I will give the details of the beamlines later on. And sorry, this is the statistics during 2024. Indus 2 has operated. This is the beam availability to users I am mentioning. So Indus 2 5840 hours. And it is worth to note that this is the best performance in terms of the availability to Indus users in any calendar year. And Indus 1 5707 hours. This is less because, as I mentioned, there was a major upgradation of Indus 1. So there was a shutdown taken for that. Just quickly, I will go to what is Indus 1. So Indus 1 is, these are the specifications listed here. I will not go through the details. It has a critical wavelength of 61.38 angstrom. And RF frequency is 31.613. And this is the typical operation cycle. So we inject the beam and then the beam is stored at 125 milliampere and then it decays by its natural decay. Presently, the beam lifetime at 100 milliampere in Indus 1 is typically 2 hours 40 minutes. And then once the beam comes to a lower level, then again it is refilled, and then it continues. Now, Indus 2 synchrotron radiation source. Here are the specifications: 2.5 GeV, 200 milliampere, circumference is 172.4 meters. There are 3 Undulators installed in Indus 2, and 2 more are in the process of development, which are superconducting SWLS, wavelength shifter, and 1 multipole wiggler. Will be in due course of time, they will also be installed. So total 5 insertion devices, provision of 5 insertion devices there in Indus 2. And this is the cycle of operation. So we inject the beam, we accumulate the beam basically up to the required current level at 550 MeV, and then there is a process we call as the energy ramping process, which takes the beam to 2.5 GeV, and then after applying various feedback systems, the beam is made ready for use. And presently the lifetime in Indus 2 is typically 55 hours at 100 milliampere. Now this gives the statistics of beam availability to the users in Indus 1 and Indus 2, it gives the performance of last about 5 years. So you can see that it has maintained, the sources have maintained very good performance over the years. And already I have mentioned that this is the highest number of beam availability in calendar year 2024. And this is less because there was a shutdown in Indus 1 for upgradation. And here the availability is less, obviously because of the COVID affecting, the years which were affected by COVID. And this gives the per day, average availability per day. So you see that almost Indus 1 is, we are providing more than 20 hours per day and about 17.5 hours in Indus 2. This is the average availability. Now these are the beamlines, list of beamlines which are available operational in Indus 2. So these are 20 operational beamlines, list of 20 operational beamlines. And these 3 beamlines which are in blue color, they are basically on undulators, 2 planar undulator and 1 Apple II type of helical undulator. And all the 3 beamlines are operational on these undulators. And these 5 beamlines, they are under design and development, and they will be commissioned in due course of time, out of which the beamline on as this extreme conditions XRD and protein crystallography, they will be on superconducting IDs which are under development. I will be mentioning about these developments later. These are the beamlines in Indus 1, 7 operational beamlines in Indus 1. And now the same thing, but just in terms of the experimental facilities which are available on Indus beamlines. So list of facilities, so all variety of experimental techniques using the Indus beamlines is available for various areas of material research and engineering applications and the drug research in drug development, etc. And these are the facilities which will be available in future. So tender X-ray, absorption in tender X-ray energy range, photoemission electron spectroscopy and diffraction up to 90 kV using wavelength shifter. Now, this shows the utilization statistics. At present, this Indus beamlines, they are being used by more than 140 institutes across the country, which includes all the major R&D institutes, government R&D centers, academia. And this shows, this depicts that the usage, the users, beamline users are spread all across India of Indus. And from few years, since few years, we are also getting users from industry, mainly the pharma industry, which use these beamlines, Indus 2 beamlines for their research in the drug development. Here we see the number of experiments which are carried out on Indus beamlines annually. And we can see that now almost we have reached more than 1,000 user experiments are performed every year on Indus beamlines. And the publications, number of publications since last year has also crossed 200 every year annually. So very good statistics from user point of view. Actually, I will not be covering the details of the experiments which are carried out because I believe that there is a talk by Tapas Ganguly later on. He will be touching upon the experiments, the interesting experiments which have been carried out on Indus beamlines. I will be more concentrating on the machine side in this talk. Now it is worth mentioning that this Indus facility, we are operating, this facility is being operated by licensed, trained and licensed operation crew. So there is an exhaustive training program for training of operation crew, which we call as TQLP, in short for Training Qualification and Licensing Program. And this is a comprehensive training program for 8 months, which is formulated on the line similar to other nuclear power plants. Then they are qualified at 3 different levels, level 3, 4, 5. We don't have the higher levels, 1 and 2. Then more than 150 personnel till now, they have been trained in 5 different batches and training of 6 batches going on. And presently, the operation crew consists of pooled manpower, that is, the manpower which is contributing in their R&D, they are pooled into trained manpower for certain time. they are given training and then they operate. And for some time they also work, partially they also work in their parent divisions for the R&D issues, R&D activities. Now in 2022, the Indus facility has been admitted into the qualification and incentive scheme, that is QIS of DAE. And this is the first accelerator facility in India to be admitted under this scheme. And presently around 60 trained person operation personnel of Indus are getting qualification incentive, although it's not the monetary benefit, but more I will emphasize that this is a recognition to our training program, which has been recognized by DAE, and this QIS has been made applicable. Then the operation calendar of our Indus facility is made available on the RRCAT web page well in advance. That is, now you will have the full year operation plan of Indus facility available. And in this we take some plant shutdowns once in 2 months, basically for some upgradations, maintenance activities, some longer shutdowns for specific reasons. And then every month there are 2 days which are reserved for the machine experiment, that is the experiments which are used by the machine people, either beam physicists or other system people, for carrying out their experiments towards enhancements, etc. And these days are not available for users. And rest all days are, which are shown in green here, they are available to the Beamline users. Now I come to some recent updates in Indus 2. So one important improvement that has been carried out recently is operation of the Indus 2 at a lower emittance of 45 nanometer rad. Actually, since commissioning, Indus 2 was operated at a relaxed optics, which resulted in a beam emittance of around 140, 135 nanometer rad. And this was basically due to there were some issues faced during injection in the tight optics condition. So we were not able to inject. So that's why we were continuing. But then our efforts were going on to get a solution how to give the beam at lower emittance. Actually, design emittance is 57 nanometer rad. So towards that, various experiments were conducted and some improvements in the system, like the operation of Indus 2 at 0 orbit, etc., were also done. And finally, after a long series of experiments and after stabilizing all the operation conditions, now we have started operation since last year in 45 nanometer rad region, which has also improved the beam quality to the users, Indus 2 users. And here the injection is at the relaxed optics only as earlier, but later on during ramping and during the storage, the optimization of the already planned change of the sextupole and quadrupole is done, so that when we reach 2.5 GeV and user is given the beam, the low emittance optics is applied. And this is the result of a long series of experiments by APS and other team members. So I will not go into details, but this is the lattice function which was there, which is there for 135, and this is for the 45 nanometer. Basically, the effort has been to reduce the dispersion function at the bending magnet section, to reduce the emittance. And the measurement of the beam size during this exercise was done using the synchrotron radiation SR interferometer, SRI beamline on Indus, which is a diagnostic beamline. And here for a measurement of beam size, and you can see here, this is not like chronology, it is not like one day, it is like series, the data which is collected during the series of experiments and then plotted just to show how the beam size is changing. So this is the injection, this is the horizontal beam size only I am showing, and then during ramping, and then when the low emittance optics is applied, we come to this level. So you can see clearly the change in the beam size. I mentioned the quantitative numbers here. More details will be there in the Akashdeep. This is presented by Akashdeep in this oral poster. Then we have beam position indicators or beam position monitors installed in Indus 2 Basically, these are for monitoring the beam orbit, and the information of beam orbit is used in our orbit feedback systems to maintain the orbit within the required bounds. And these BPIs were installed long back, more than 20 years back, and they have, some of them are now showing problems. So we are now replacing them in phased manner. Basically, to replace them needs a venting of that particular section. So we cannot do everything in one go. Whenever there is a venting, we choose one by one section and replace in that. And this new upgraded, we call upgraded BPI, they have improved version with these features. And in the last December 24 shutdown, we replaced 5 more, and this makes total 39 out of 56. They are now with upgraded, and this remaining also will be replacing soon in future shutdowns. Then this is a enhancement of the digital LLRF system of Indus 2. So here basically for station 1 and 2, our RFSD team has developed a compact LLRF system, and here 2 stations, they are now catered by one single rack, and with these features which are given here. Then one important development in Indus 2 is development of digital beam position monitors. Earlier, the processing of this beam position monitoring signals was done using analog electronics, which was later on replaced. Some of them were replaced with commercially available digital position monitoring electronics because of their obvious advantages. And later on, we have taken up, the team has taken up the development of indigenous digital beam position monitor, and already 2 such electronics, they have been developed, and with these features, and they have been deployed in Indus 2, used in slow orbit feedback system. And this shows the test for their usefulness in fast orbit feedback system, where fast changes in the beam position will have to be reduced, or they have to be stabilized, and shows the result. This is Libera is the commercial version, and Nayan, this is given the name Nayan. So they are showing the comparison. So they compare well the performance, and here it shows that when FOFB means local fast orbit feedback. So when this is on, this is the level of disturbance, but when it is off, the level increases. So there is a reduction in the level. This will be presented by Dr. Rishipal Yadav in his oral talk.
Yeah, 5 minutes.
Yeah, okay, I will try to complete. This is a single button operation to help the operator to quickly go through all the procedure just by a click of single button. Again, details will be presented by Bhavna Med in her talk, in her oral talk. Then there is a system implemented in Indus 2 already, which is based on AI, and optimizes the injection parameters, the transport line and various parameters of injection is optimized using this AI-based system, which we call as autopilot, and it takes care of the optimization without need of expert operation person there. And this was recently upgraded with an additional module, which is called kicker feedback system. So this kickers Indus 2 injection is done using 4 injection kickers, and their matching, their pulse matching is very important. And due to various drifts, sometimes the pulses do get mismatched, and then operator has to spend a lot of time in again getting the optimized matching to get proper injection. But this system automatically takes care of the matching. So you can see that this is the reference, 4 pulses overlapped on one another, and this is the condition which is a mismatch condition, and this feedback system brings them to again the reference condition. So the power converters also, there is a continuous effort in upgrading them. Old outdated power converters, they are replaced with new power converters based on the latest topologies and with better performance. So in this series, upgraded power converters for quadrupole magnet and skew quadrupole magnets were installed and deployed by SNPCS. And then in the beam diagnostic devices, development of water-cooled scraper. The scraper is a device which is used for measurement of dynamic aperture. Earlier, the scraper, they were not able to withstand high heat load, but now this water-cooled scraper will be used, which can withstand up to full 200 milliampere at 2.5 GeV, 120 watt heat load, and it will be installed along with wavelength shifter in long state section 4 when that shutdown is taken place. And one development, which is a novel development, is a fast current transformer. Basically, it is developed for its deployment in our industrial accelerator. And the novel feature of this FCT, normally FCTs are mounted on a ceramic isolator in the beam vacuum chamber, and the core is outside. But here the ferrite and core is inside the vacuum, thus eliminating the need for a ceramic gap, which makes it much rugged and compact also. This is already deployed in our industrial accelerator. Then one important development is development of superconducting insertion devices. There are two devices which we are developing, wavelength shifter and multipole wiggler. Wavelength shifter is this center pole is superconducting and two normal conducting outside poles. And this multipole wiggler is a series of poles of around 48 poles are there. This shows the for wavelength shifter. The first wavelength shifter is going to be installed in Indus 2. After it, I will show the present status of this development. So this shows various photographs of the WLS development and MPW development. I'll show some more photographs. This is done by Accelerator Magnet Technology Division. And then this is the cryostat, which is a very important technology which has been developed in local industry with our design. And recently only it has got delivered and it has passed all the tests required for our installation and commissioning in the lab. So it shows the main pole, superconducting main pole, then hang assembly, cryostat assembly, and this is the complete assembled thing. This is done by our Proton Linac development division. Show some photographs. So it is during our testing in lab. So this is the dummy magnet, cold body, and then surrounded by 50K copper shield. And this is in the fully assembled condition, and it attained 2.9 Kelvin in about 4.5 days during its testing at RRCAT. And this shows the graph of that. 5 minutes. Okay, I will try to complete. And this will be after magnetic characterization and rest of the things. It will be we expect that by September 2025, this will be ready with full characterization and everything. And later on, then we'll take a decision for taking shutdown to install it in Indus 2. But this is a very important development towards, because this is the first superconducting ID which will be indigenously developed and installed in Indus 2. And this is the high stability power supply which will be required for development of, energizing the superconducting shifter, wavelength shifter magnet. More, this is done by Accelerator Power Supply Division. More details will be presented by Shri VK Gautam. Now I come to Indus 1 upgrade activities. Indus 1 was commissioned in 1999, but since it is working for more than 25 years, so there were a lot of problems with systems because of their obsolescence and outdated systems. So we took a decision to upgrade the whole ring with new components and with additional facility of closed orbit COD correction scheme, which was not present in the earlier version. And for this last few years, we were developing various systems, and in 24 and 25, there were around 2.5 months shutdown was taken. Sorry, in December 23 and 24, this shutdown was taken to replace the whole ring with the new components, and that has been successfully completed, and now it is running successfully. This is just to show that this is the old layout. We have not changed any rest of the thing because we didn't want to change anything, any alignment or any this thing regarding the beamline. So we have kept everything same, all the dimensions, etc. But then challenge was to accommodate the new functionalities that are required. That is the new devices which are required to add these functionalities of COD correction. and other things. So you can see here, just by visually, you can see that there are many additional devices which have been accommodated in the same physical space. So this is the installation of upgraded ultra high vacuum system in Indus 1. One development which is indigenous SIP and NEG, non-evaporator coated vacuum pumps, which have been developed indigenously and deployed in Indus 2. So it shows the photographs of various systems and the new vacuum system which has been deployed. These are the combined function magnets which have been deployed. Basically, in this combined function magnet consists of, earlier there were only sex 2 poles, but now we have sex 2 pole. Along with that, we have skew quadrupoles and steering magnet coils also on the same combined function magnet. They have been deployed. These are the power converters to energize these combined function magnets. More details will be presented by Rahul Pokarkar. Then ion clearing system, upgraded and revamped ion clearing system for Indus 1 developed by RFSD has been implemented. This is also taking time. This pointer is not working smoothly. Okay, so these are new because we needed a closed orbit distortion correction. So 8 beam position monitors, compact beam position monitors have been developed and installed. And the electronics for this processing is also developed indigenously and implemented. Just I am running because of shortage of time. Again, 4 BPMs which are integrated. And then this shows the installation and commissioning of digital beam position monitors in Indus 1. And more details will be there in one poster and oral presentation as given here. Then for tune measurement and feedback system, we have developed the strip line kicker and pickup. Basically, these are the devices which excite the beam and then pick up the signal from the beam. And details will be presented by Akhilesh Karnewar in his oral poster presentation. And to take care of the additional systems, all power supply, diagnostics, etc., the whole Indus 1 control system has been upgraded to include all these facilities, and details will be presented by Rahul Rana. This is the COD correction result. You can see that this horizontal and vertical, this red one is the before COD correction and this green one is the after COD. So you can see the reduction. Here in horizontal, you can see that slightly it has not gone to its best possible condition because there are 4 horizontal correctors in dipole magnets which are yet to be taken into this correction scheme. That will be done soon. And this is the deployment of slow orbit feedback system. Just like in Indus 2, we have deployed now slow orbit feedback system using this BPM electronics and the control system, and more details will be presented by Rana in his oral poster presentation. Okay, so now I summarize. I summarize my talk. So Indus synchrotron radiation sources are operating as a national facility in round-the-clock mode for more than a decade. And there are 20 operational beamlines on Indus 2 and 7 beamlines on Indus 1, which are being used by a large number of researchers. And various upgrades have been carried out. I have given a glimpse of some of the developments which have been deployed in Indus 2 and also some which will be now deployed in future. And Indus 1 has also been now upgraded and successfully running with COD correction scheme and slow orbit feedback system. I would like to I thank the entire Indus team, all the divisions, independent sections contributing directly or indirectly in the upgradation, maintenance and operation of Indus facility. Then a very big thank to Indus operation shift crew members. They are operating the machine in 3-shift mode in a very dedicated manner. And I also thank all the colleagues who have contributed slides for this presentation. With this, I thank you.
Thank you for a very expansive review of both Indus 1 and Indus 2, and congratulations for successful operation last year, what you have achieved for Indus 2. It's a very nice developments. I'm sure there are many questions. Although we are running late, we should take a couple, we have time for a couple of quick questions. Yeah.
Yeah.
There is an online question too. There are no full magnets tested in Indus 1 upgrade.
No, not tested. Nahi. मैंने Indus 1 upgrade, there are direct dipole, there are 4 horizontal character coils.
Yeah, whatever.
Yeah, they have to be incorporated.
They have to be. After
Yeah.
that, what is the targeted orbit?
Targeted, I have that slide. It will be better than this. Whatever is there, it will come to better than this.
Within 60.
But one thing I would like to tell here that we are not operating because there is a we need to provide the beam to users, Indus 1 users. So although we can bring the beam to its very minimum condition independently, but to cater to beamlines, because these beamlines are also quite old in Indus 1. So there are provisions to align the beamline with the centered beam is somewhat limited in some of the beamlines. So we have to go to a orbit which is like a where we can give the beam in a better way to Indus 1 users.
There's a question there. Just wait for the mic. Please.
Okay. What is the question?
Okay.
Yeah, there is an online.
Okay.
Yeah, first of all, sir, congratulations on running this national facility and so many research papers and R&D going on and increasing the beam operation time. Sir, this on the multi-pole wiggler as well as the wavelength shifter, you are going into now superconducting domain.
Yeah.
Are the magnets superferric type or pure superconducting magnets? That was the question. I have also typed it on the chat box in case not available.
Can you repeat the question? I couldn't get the question.
Are these magnets iron plus superconducting coils or
only coil that I showed in the wavelength shifter? The center coil, which is 5 Tesla, is superconducting. Rest two are normal conducting. Multiple pole wiggler, full superconducting.
Full super. That's right.
Any more questions? Comments? Otherwise, of course, we can talk with speaker in the tea break. So thank you once again, Puntambekar.
Thank you.
We have a memento from organizers for you. So. We now move to the second talk. This is by Professor Arup Bandyopadhyay, who is head of Accelerator Physics Group at VECC, Kolkata. Arup has worked on many areas of accelerators, online ion sources, isotope separators, room temperature and superconducting magnets, and cyclotrons. He has more than 50 publications in international journals, and his work has been very well recognized by various awards, Group Achievements Awards in DAE and Scientific and Technical Excellence Award in DAE. So, Arup.
Good morning, everybody. Thank you, Professor Nanal, for the nice introduction. Now I have to prove that I have done some of those things. So my title of my talk is Particle Accelerators of VECC, Present and Future. I'll be basically giving a bird's eye view of the present accelerators and the future accelerators, and not cover any details, further details or the developments which have taken place. Rather, I'll talk more about the performance because for other R&D parts or the developments, my colleagues have already different, they will be presenting their work in different orals and posters. So I request all of you to kindly visit them at the poster session and encourage them and their research. Now, 2 years back, we celebrated Azadi Ka Amrit Mahotsav, and then in 2004, we are going towards 2047, when we are planning to take our nation from developing nation to developed nation. So I'm trying to dream that as a part of the accelerator community, how we can contribute in country's journey towards this direction, as far as the accelerators are concerned. So I'll be talking about variable energy cyclotrons. Natural because I am from VECC, the center itself is named after cyclotron. So considerable part of the time will go behind that. I'll also talk about fixed energy cyclotrons. Then I'll also talk about linear accelerators and VECC and future facility of rare ion beams ANURIB. So I just happen to note I'll be talking about each and everything except what Puntam Bangar sir has just now covered. That is a very high energy electron accelerator. So you'll get a flavor of everything. This is the room temperature cyclotron. Can we have the lights dim? Then you can see the slides better probably. So the room temperature cyclotron we commissioned in 16 June 1977. So this year in June we'll be celebrating 49th birthday of the machine, and next year will be a 50th birthday. I believe all of you agree that that is a milestone for any accelerator to achieve 50th birthday, and I think we should celebrate in a great way. Now, for cyclotron to function, you need high magnetic field. The accuracy and the profile of the magnetic field are two very important requirements. And also for different ion species, you require different profiles of the magnetic field. So the magnetic field is generated not by a single coil. You have a main coil and you have 17 trim coils which give small corrections based on the requirement. These corrections are very minute level corrections, but unless all these 18 power supplies are perfectly tuned, you cannot achieve the required magnetic field and you suffer from beam losses. Also, for different Q by A, for a particular energy, you require RF frequency which are different and also high amount of RF power. So you have to have a variable frequency RF system. From room temperature cyclotron, this looks like this. So this is a D, and these are the basically the structures which come forward and backward. In that way, you change the inductance of the RF system and the frequency changes. So in room temperature cyclotron, you have 1D. The RF frequency changes from 5.5 to 16.5 megahertz, and the RF power is 300 kilowatt. These are the different ions that we are accelerating, but again, the details are there in other presentation. One thing I want to point it out, that last year in 2023-24, we achieved the highest amount of cyclotron availability, that was 89.1%, and that we could achieve because we are spending significant amount of time in system upgradation or in introduction of the new components. As you can see, last year that was 15.3% time for the planned maintenance and 35.3% of the time year previous to that. And because of that, the unplanned shutdown and the system breakdown is gradually reducing. So to keep one old machine running, these are very important aspects, you cannot ignore it. Next, I come to superconducting cyclotron. This is the one. So when you need much higher energy, you need higher magnetic field. So you go for superconducting magnet. So here, compared to the earlier 1.7 Tesla magnet, this is 5.8 Tesla magnet. Here also you have the main coil and the trim coils to get the required magnetic field. Here also you have the variable frequency, but the difference is here. In the earlier room temperature cyclotron, the RF system is in the median plane, but here it is top and down, and you can see it is almost 12-meter long RF system. And there are 3 number of these. In the room temperature, it is 1 number. RF frequency variable in this range and 3 RF transmitters. So these are the hills of the magnetic field denoted by H. Actually, what you are seeing on the top of the hill, you have the RF liner. So you are seeing that. And in the valley, you have the D. So this is the valley region. This is the D1, D2, D3. So this machine is delivering beams since December 2020. List of ions primarily we have delivered so far at this, and to note that this is the highest beam energy machine in the country right now. Beam current delivered to the users is only 5 to 10 electron nanoampere, although we can get up to 25 electron nanoampere and 12 meter downstream of the extraction zone, around 95% transmission. But this low current is because of the user's requirement of very stringent beam condition. It should not hit their target mounting and things like that to reduce the background. but however, we can go up to this current. Next, I come to the medical cyclotron. Now, I said that I'll be talking about fixed energy cyclotron, so this is one of them. Why I'm telling them fixed energy cyclotron? The earlier two cyclotron, you have magnetic field variable, RF frequency variable, in order to accelerate different charge to mass ratio and also in order to get variable energy. But in this machine, the magnetic field is fixed, the RF frequency is also fixed. So that's why it is a fixed energy machine. However, you can get variable energy here also. So what you are doing, you are extracting the beam from the inner radius. You are not allowing the beam to accelerate its full turn up to the circumference. So in that way, although it is a 30 MeV machine, you can get energy from 15 to 30 MeV. We accelerate here proton. It is capable of delivering up to 350 microampere. Here also magnetic field is generated by room temperature coil, 1.7 Tesla. It has got two number of Ds. It is shown on this picture here. This is the one D, this is the other D. These are the this is a 4 sector magnet. So 1, 2, 3, 4, 4 holes. And this is the value it is literally value, you cannot see the lower surface actually. You have two number of Ds, the frequency is like this. So this machine we are primarily using for the production and delivery of radioisotopes every day. So it was commissioned during the COVID time, and since that time, almost every day, I think it is Sunday we do not deliver, we are delivering to all Calcutta hospitals these radioisotopes. These are the 4 such examples we are delivering, and then there are R&D going on for developing other radioisotopes as well. And then here VECC's responsibility is to keep the cyclotron running. The radiochemistry and the delivery of the radioisotopes is within the scope of BRIT. Now, here one important thing is that if you see the PET isotopes, PET, you have two types of isotope, PET and SPEC. PET is comparatively short-lived isotopes, but then they provide much higher resolution of imaging, which is essential for the cancer treatment. Now, PET isotopes are having very short half-lives. As you can see, this is the range of short half-life. So you have to produce these isotopes and you have to use it within 3 or 4 half-lives. So by evening, this has to be used. So if I have a machine in Calcutta, I cannot supply the machine to Darjeeling or some other places because it will decay by that time. So ideally, we should have this type of machine every corner of the country. And so far, all these machines are imported from outside. So VECC has taken up a project to develop such a machine in collaboration with CDM BARC. And this is an 18 MeV machine, 50 microampere current. This is the model of the machine, and these are the specifications of the machine. This is a 4 sector machine, and this is a sector angle, etc. Different parameters are shown here. The basic design aim while going through this process was that we have in front of us one IBA machine, but then we wanted to ensure include the changes which should be cost effective, and it should be feasible to make it in our country. And after the first machine is built, we plan and actually working in that direction to transfer the technology to the Indian industry. This is some of the snapshots. This is the magnet pole pieces now fabricated in BRC. Some of these magnet pole pieces, which is within the scope or the machine length of the VECC that VECC is also manufacturing. This is the coils. This is during the inspection of the coils. It has been already fabricated in the local industry. This is a model of the D and the RF system. This is the D stem, etc. You can see these are actually have been fabricated in VECC workshop. I have seen it just before coming. And we have also developed 2 versions of the multicast ion sources with different magnet geometries. These are fabricated and tested. The ion source part is over. Now I'll go to another machine, again another cyclotron. This is 50 MeV 200 microampere proton cyclotron. This will be used as a driver for ANURIB project. About ANURIB project, I'll come later. Let us concentrate on the machine. These are the parameters of the machine. This is a 4-sector, hill gap, valley gap, etc. All the dimensions are shown here and the optimized magnet parameters. And the RF frequencies are 62, which is different from the earlier machines. And the magnet has been designed with reasonable dimensions for the driver cyclotron. Oh. Now, for cyclotron, because it is a multi-turn machine, it is keeping on rotating. It is important to maintain the synchronism throughout its motion, isochronism. So that can be ensured if the frequency error and the integrated phase shift when it accelerates is within some limits. So we could achieve it is less than 0.04%, it is less than plus minus 5 degree. These are shown on these two plots, which is good enough for our purpose. We have done the beam dynamics using these codes, and you can see well-centered beam accelerated up to 50 MeV. One important consideration for the design is the resonances during the acceleration process. And these are the two deadly resonances. One is nu r is equal to 1, other is nu z is equal to 0.5. And these are the two lines for that. As you can see, we are well above that. So we do not expect anything wrong. So we are satisfied with the beam dynamics design. Now we are basically getting budgetary estimate, etc. So this is in the design lab, you can say. It is not yet, fabrication, etc. has not yet started. Now I come to another regime altogether. So cyclotrons I have more or less covered. Now I will come to the regime of linear accelerators. Just one slide, very elementary. Suppose I want to accelerate oxygen ion. I have options like this. I can accelerate 16, 17 or 18 mass number of oxygen. These are stable isotopes available in nature. But then those we are accelerating can accelerate in principle for the accelerators I have shown you earlier, cyclotron, etc. But then when you aim to accelerate isotopes of oxygen like this, spanning from 19 to 24 and 13 to 55, they are not stable isotopes. They have a short half-life, and these are beta plus emitters, these are beta minus emitters. So when you want to accelerate these isotopes, you call it as a rare ion beam accelerator or RIB accelerator. Now, in VECC Bidhannagar campus, we are already having an isol post-accelerator type of RIB facility. There are other types of also facility, but I am not going there. So the basic process here is that you use a primary accelerator and a suitable target to produce the RIBs. And then you feed it to an ion source. And after ionization, you use an isotope separator to single out the particular RIB of your interest. So at this point, you have RIB energy 1 to 2 keV per nucleon. But primarily for nuclear physics experiment, this energy will not do. So what you do, you use various post-accelerators. And in RIB facility at VECC, presently we can accelerate up to 1.5 MeV per nucleon. Now, RIB, I'm not going to the mathematics. Primarily, if you see the primary accelerator, the beam intensity, what you can get compared to that, the RIB intensity is 3 to 4 magnitude lower. This is a basic way it is. And now, your post-accelerator, therefore, should be as efficient as possible. Now, linear accelerators have the maximum efficiency, transmission efficiency. So, linear accelerator is a better choice compared to the cyclotrons. But some laboratory cyclotrons are also used because cyclotrons in one accelerator, you can accelerate with much higher energy. For linear accelerators, you need many of them. But we have gone through the Linac route. So that's why we are now leading from cyclotron to Linac. So if you summarize this way, basically you are having these 5 building blocks for making an RIB post-accelerator type of RIB facility. Driver accelerator, suitable targets, online ion source, online isotope separator, and post-accelerator. Now, driver accelerator I have already talked that we are using the room temperature cyclotron. These are alpha and proton beams. This is the energy range. Now we can produce RIB using this machine using two different reaction mechanisms. Fusion evaporation reaction mechanism, which gives us neutron deficient RIBs, and fission reaction, which provides us primarily neutron rich RIBs. Then let me touch upon the next part, suitable targets. Now, as I said, that for RIB, the one main concern is what is the RIB intensity. That RIB intensity depends on this factor, very familiar to the nuclear physicist, primary beam intensity, number of targets per square centimeter, sigma is the cross section of a particular reaction channel, and eta has within itself all efficiencies involved. Now, only thing which you can play here, because sigma is fixed, you don't have much control. Primary beam also there is a limit. This NT, this is the number of target atoms per square centimeter. So there are two ways to maximize it. One is you use a thick target, or you use multiple thin targets. The difference is, if you use a thick target, you have to use some other techniques so that the recoil atoms or the reaction products can come out from that thick target for further utilization. And if you use thin target, the target thickness should be so thin that the recoil atoms can by itself can come out. It is it should be ranged than the recoil range of the reaction product. We have gone in VCC RIB facility that multiple thin target route, because for the thick target route, we do not have the required space in our RTC beamline to accommodate it right now. Now, this is the beam chamber for that. As you can see, this is the target ladder where I can use multiple thin target. And we are using a technique which is called gas jet recoil transport technique, by which what is happening, this is the primary beam from the cyclotron. The reaction products will be confined here, and we are pressurizing it in the atmosphere of helium or argon, some inert gas. So the recoils are coming down to a very low energy. And then using a technique called differential pumping, that is at the other end of the ion source, we have a heavy pump like a roots blower. You suck the reaction products along with the carrier gas. The advantage of this technique is transport efficiency is almost element independent, and it is a fast technique. It requires around 100 milliseconds for a distance of 6 meters. So for majority of the radioisotopes, it is a good technique, but we cannot go below 300, 400 milliseconds. But this technique provides an undesirable gas load for the ion source, so your ion source has to be special in nature. So for the online ion, for the online ion source, this is a picture of that. So this is a 1+ ECR ion source which has been designed and developed recently, and it has been tested. This ion source is specially designed to take care of the large dynamic gas load. Higher chastity is not possible because within the ion source the vacuum is not that good. Then for linear accelerators, higher chastity you need, because otherwise your accelerator length will be too large. So what people are doing, and we are also in the same train, that you use two different ion sources in cascade. So from the first ion source, you extract the beam and you inject the same beam to the second ion source to get the higher chastity. But then, before injecting the beam to the second ion source, you have to decelerate the ion from the first ion source. Otherwise, the ions will just simply pass through. They will not get ionized further in the second ion source. So this is the first ion source I am talking about, and this is the 6.0 GHz second ion source. Both these ion sources are in place. We are doing experiments for the charge breeding, we say, that is from 1+ to n+. And right now, I don't have the slide to show you the results, but we are working on this. But both the ion sources are functioning perfectly all right.
Arup, 5 minutes.
5 minutes. So next part is the isotope separator. Next part is the isotope separator. So there we have a very what I should say, moderate isotope separator, which separates the ion from the ion source and feeds it to the RFQ. We have worked on linear accelerators. Now, linear accelerators, again, different types of linear structures are suitable for different energy range. So I'll be talking about 3 different linear accelerators. The first one is the RFQ. This has been commissioned and working since 2008. It gives us from 1.73 to 98.8 kV per nucleon. Next one is, I'll be talking about the linear accelerators. These are called IH Linac, room temperature linear accelerator, but this is very specialized. This is not DTL. This uses transverse electric mode for the acceleration of the ions. And we are having two different structure here. The first three are copper plated steel, and the next two are copper plated with mild steel. And this will give us around 1.04 MeV per nucleon. We have also bunchers in between to take care of the longitudinal phase space. We have 5 of them for various energies. I have shown here the frequency and the energies. And then finally, we have also developed a quarter wave resonator. This work has been done in collaboration with Trump, Canada, and it has been tested also. And this is in the earlier slide, what you see. This is the quarter wave resonator 1, 2, 3, 4, and in the center you have a solenoid for transverse focusing. And that thing, this is the whole quarter wave resonator assembly that goes into the cryostat like this. These are some of the parameters of the test result. And we have tested it, and it is achieving much above what we want to achieve, actually 5 MV per meter. And this is the present site at VECC RIB facility. And right now we have transported the beam up to the end of Linac 4. Linac 5 and quarter wave resonator is yet to be beam commissioned. They are in place. These are the some of the RIBs we have accelerated, and these are the stable beams. So stable isotope beams are regularly delivered to the users, and some of the RIBs up to 415 kV per nucleon can be also used. We have a commissioning clearance up to 1 MeV per nucleon, but regulatory clearance is only up to 415 kV per nucleon. Next, I'll go for the electron Linac. This is another route for the production of the RIBs, where you use a superconducting electron Linac and a different reaction mechanism called photofission to produce RIBs. This again we have developed so this is the front end of that superconducting electron Linac. In the same line Dr. Vineet Kumar was talking yesterday. This is the ion source DC cut RF matching section. This is the LEBT line, and these are already in place in VECC. And this is the superconducting electron Linac model. These are the different stage of fabrication. This has been tested at TRAP. Next, I'll take just 2-3 minutes more. Now, in the Mega Science Vision in 2035, the recommendation of the committee was development of the new accelerator facilities within India for radioactive ion beams, high current stable beams. So in that direction, we have to develop a facility of RIB, which is much more, which can deliver much more compared to what we can deliver from the VECC facility now. So we have now working on applied and nuclear research using rare isotope beams or ANURIB facility. So it is also isol post-accelerator type of facility, but it will have 2 injectors. One is a proton cyclotron, which I showed you earlier, and other is the superconducting electron Linac for the production of the RIBs. And this is the 1+ ion source, N+ ion source separator, and RFQ room temperature Linac, superconducting Linac. So we're planning up to 2 MeV per nucleon. And then we have the provision of expansion at a later stage. Using superconducting Linac and ring cyclotron, we can go to much higher range. So as of the first phase, what we are proposing now, we'll have proton driver, both rare and stable isotope beams accelerator. And if we go pick up this part at a later stage, it will also provide the option of PFS type RIB facility and fragmentation of RIBs for producing near drip line nuclei. These are the 3 different accelerators for this facility. And then when we are going for this, there is a question of technology readiness level. So there are the different stages of technology readiness level starting from 1 to 9. 1 to 3 is research, 4 to 6 is development, 7 to 9 is deployment. So you remember the color code. So again, you remember the different building blocks of what I showed you. So for the primary accelerators, we are in the deployment stage for electron Linac. Cyclotron is the research and development. Thick target, again, research. Ionization, ion sources is the deployment stage. Separation is the development stage. RFQ and the post-accelerators, majority of them are in the deployment stage. So majority of the thing, we are in a very good position, or the technology readiness level of this project is very high. This is the VECC Rajarhat campus. The whole facility will come up in the new campus. This is the ANURIB present facility. This is the space for the future expansion. This is the RMRC project of BRC hospital. And then this is the zoning of the facility, different zone 1, zone 2, zone 3, etc. And last month we have got the regulatory clearance for the site approval, and now we are preparing the DPR, which is expected to be submitted by the middle of the April. So with that, I have come, and I should acknowledge the contribution of different partners in the journey. And thank you for your kind attention. I think I have already shoot up my time. Thank you.
Thank you. Thank you, Dr. Arup, for a very extensive review of the present and showing a nice pathway to future. I'm very glad you touched upon the projections in the mega science, because yes, the radioactive ion beam is of a great interest to the community, nuclear physics community, for research. And I think these efforts to make the proton accelerator for the medical application, the development efforts are really commendable. The talk is now open for discussion. Yeah, so Dr. Vinit Kumar first and then later.
Arup, very nice talk. We all enjoyed it. Just a comment that you mentioned about the mega science based and nuclear physics document, which has recommended about the RIB facility. I just wanted to tell you that our mega science accelerator document,
that also has the same thing.
That also has put it strongly. Thank you.
Yeah, I think he wants to show the end use. That's why he should.
Because
yeah, it's a lot of commonality. Yeah, very good. Yeah.
Yes, sir.
Thank you for the talk. Just out of curiosity, I just wanted to ask that, see, for that RIB production of ions, radioactive ion beams, you have shown that you will be putting the beam on a suitable target where the ions will be generated, and then you will have an online ion source you have shown.
Right.
So what does that online ion source do?
Yes. The difference is, suppose the normal cyclotron, room temperature cyclotron, I have a source of gas in a cylinder. I can feed the feed gas in the ion source and get it ionized. But online here, the RIBs are produced in a primary accelerator. You are straight away feeding it to the ion source. There is no stock of the feed material here. It is produced immediately and fed to the ion source. So the main consideration here is the efficiency factor of your ionization should be very high. But in the other type of ion source, you can play with less efficiency, because there the main criteria is very high jasted. So the design of the ion source is slightly different. Also, as I said, in this type of ion sources, because of the high heating of the target, the vacuum is one important consideration. So it's different from the normal conventional ion sources. Means these ion sources will not get off the shelf from any manufacturer.
Yeah, why this thing was that already ions are produced before that online ion source?
No, you are producing the ions in the online ion source only, because the reaction products which are coming, by the time they're thermalizing in the gas, they're losing their charge state.
Okay, thank you.
Yeah, maybe you can discuss more. There's one more question here.
Thank you, sir, for the presentation.
I can, yeah.
Yes. Sir, I want to ask about the RIB. So you said that RIB depends on the sigma, and the sigma has, of course, the sigma has always have an energy part. So what is the comment on the energy of the protons that will give rise to more number of radioactive ion beams?
No. The energy of the beam is see, suppose I want to produce RIB-A. So I will first do by different nuclear physics codes, what is the production cross section versus energy. So there is an energy window. So my beam energy should be within this energy window. And then if I use thick target, I will adjust my target thickness in that such a way that I can use that entered energy window.
Okay.
Or if I go for the thin target, every target there is an attenuation. So my number of targets will be determined such so that I can use the entire energy window.
Okay. And the second question is regarding the current part. Since the cyclotron is in nanoampere order, so
No, what said you?
This in a particular cyclotron?
200 microampere what we are designing.
Okay.
And the present one we are writing, see the one we are designing now is 200 microampere. And the other one which we are using it now, it can give you proton up to 4 or 5 microampere or even more.
So that will be order of milliampere only.
Yeah,
for RIG.
target.
For RIB.
Yeah.
Yeah, I'm saying
Thank
for
you, sir.
production target, you will need.
Yeah.
Yes. Thank you, sir.
Okay, thank you. Okay, last
So one two questions here.
Up to the chair. I don't know if she allows.
Yeah, but
Yes.
make it short. Yeah.
So first question is in the ion sources from 1+ to n+, when we are taking it,
Right.
is there a significant emittance growth, or the emittance of the ion source is not dependent upon the whether we are taking after the first and the second stage?
Emittance growth will be there, but now you see you have one option. One is you are having 1+ chested.
Okay.
Now you are also in the linear accelerator design.
Yes.
So if you have 1+ chested, you can imagine how long will be the length of the Linacs.
Yes.
So we want to produce something which is not offline, but at least something in between, reasonable chested. Emittance growth measurement, etc. I don't think anybody has approached so far. So what people have done, either they have used two cyclotrons in cascade, or they have used a surface ionization and ECR in cascade. But I don't have any measured data. People have talked about only the whether they could successfully produce charge breeding, and if so, what is the efficiency?
Because in Linac, the
So
emittance.
maybe,
at
sorry
this-
to interrupt, but in interest of time, maybe
Yeah,
further discussion you can take.
Okay,
in the
okay,
discussion,
thank you.
okay? So thanks to Dr. Arup once more. Nice talk. And there is a memento for you from organizers. We now move on to the third talk in this session. This will be given by Professor P.A. Hassan. He is Associate Director of Bioscience Group. And as we can see in this session, we are getting a very wide variety of expertise. So he works mainly in soft condensed matter, nanomaterials, and scattering of light, X-rays, and neutrons. He has many achievements. So name a few. He's a member of American Chemical Society and member of Royal Society of Chemistry. He has many technical papers, more than 190 papers in journals, and also has a patent, amongst other things. And he will be talking to us today about role of accelerators in mutation breeding program. So over to Professor Hassan.
Thank you. It was this one. Okay, thank you. Sorry. Oops. How do you go back? Sorry. No, first page. If you okay, that's okay. I think. Can you go back? Go back and forth. No, this will not work. Okay. Thank you very much. At the outset, let me thank the organizer for giving me an opportunity to deliver a talk in this forum. I don't know how I am fitting into this audience. I believe mostly it is physicists or those who are working on accelerators. I am professionally a chemist, and now I am a spokesperson for bioscience, basically. So I'll be talking about the application of this type of accelerators in some of the biological sciences, mainly in agriculture. So as you all know, even nuclear science has got we have got an extensive program in the non-power applications of nuclear sciences. So I believe that even accelerators in future can play an equal role in delivering some of the non-power applications what have been used by gamma radiations. So the outline of my talk, I will first I will give a brief introduction to this, basically the role of radiation in mutation breeding. And I will just say that how the charged particle based mutation can also be tried in future as opposed to the conventional gamma rays or X-ray induced mutation. And I will give some of our preliminary experiments in the area of nuclear agriculture using charged particles and some of the future perspectives. So those who are not very familiar with mutation breeding, basically I would like to introduce you that mutation is a spontaneous natural process, as you all know, due to the breaking and the recombination that happens in our DNA. We evolve to develop in any living organism new varieties or new characteristics. So what a charged particle or a gamma ray, what it can do is the speed or the rate at which this mutation can happen in a living organism. So that can be altered significantly because the number of breaks and recombination that happens per unit time, that is enhanced by giving an external radiation. And I would like to also introduce that. So what is the advantage of doing such alteration with the help of an external stimuli is that you can finally select based on that. You may end up with either adverse characteristics or you may get some superior characteristics. So after introducing such changes in your genetic changes, you can look for varieties that has got either a superior yield or drought resistance, salt tolerance, early maturity. In case of plants, I'm now today I will talk about how these accelerators can be useful in agriculture, basically in nuclear agriculture, which we have been encouraging. There are multitude of applications like in food preservation, and you all know that in food technology we have been gamma rays have been used for preservation and shelf life enhancement of various food produce. So there also accelerators can play a role. Today I will not talk about it. I will be discussing mostly on how you can enhance the crop productivity by using this technique. So all these problems will evolve, because of the change in the climatic condition or weather condition. Farming is a business which very much depend on actually the climatic condition. The farmers, they can encounter many problems because of the adverse climatic condition, and we all know that the climatic conditions are changing and that is adversely affecting the farming community. So what we can do is that can we develop varieties that can give superior yield, or it can resistance to adverse drought conditions, or there are due to excessive use of fertilizer, the soil quality is getting hampered, like you have salt resistance, salt tolerance, because the salt content in the soil or in the coastal region, it can increase. So all these adverse conditions can be one can try to overcome by using radiation-induced new varieties. I would also like to add that this is much different from the genetically modified varieties, which that is also another area of research in which artificially a particular segment of the gene has been introduced in the plant so that you can overcome this problem. But this is not a genetically modified way of doing agriculture, but it's simply accelerating the spontaneous mutation that generally that happens in plants and even in any living system. So DAE has a very ambitious plan for our Amardkal to develop something like a double the number of varieties. So far, we have about 70 varieties that has been developed by nuclear agriculture, that means by gamma ray, mostly by gamma ray, in this mutation breeding program. And by 2047, we are aiming to double that number earlier, because last year it was 60 plus. So we were planning to do 120 plus. Now, last year we could get 8 varieties released in 2024, which adds to from 62 to now 70 varieties have been introduced. So this will have lot of implications for giving the benefit to the farmers. So what this mutation breeding can offer. So one is actually creation of new genetic variability in crop plants, and we can improve 1 or 2 traits in an elite or well adapted variety. Basically, suppose there may be one characteristics which is very high yielding, but the quality is very poor. They have low oil content, for example, if you guys. So we need to improve if you want to do compare. I mean, include more characteristics to a very well adapted variety. One may be disease resistant, but at the same time the yield is poor. If you want to introduce that, it is possible. Then sometimes you can actually break 2 tightly linked traits. Basically, what does it mean? Sometimes the gene that is present very close by each other. One is actually, if A and B, they are of opposing nature. One is actually advantageous, another one is actually inferior. So you can actually break this and then you can separate this thing. And you can also improve vegetatively propagated crops. So because radiation is a good source to do in other crops if it is not vegetatively propagated. So you can do hybridization. So people have been using hybrid techniques, hybridization of to one tall variety and a dwarf variety to introduce in the progeny both the characteristics. But that is not possible in the varieties that has vegetatively propagated. So they are in such cases like a potato, sugarcane, banana, rose, they are all actually from vegetative propagation, meaning you cut the plant and then you do it. You don't have any breeding what you can do. So there even radiation can help. So the genetic improvement by radiation is normally done by induction of the genetic variability with the help of radiation, or that can be done even by accelerator driven process. And by doing that, you get many genetic variation, and finally you choose from that the traits you observe physically. So which one is having better characteristics, and you take it, and then you try to propagate and check whether the variety is finally giving the desired yield. You could also go for actually crossing. So you take one mutant and then check one mutant, genetically verified, a different mutant, and then you cross it with another mutant. That also will leads to further new crop varieties. So similarly, you can cross it with the original one parent and the mutant and this mutant derivative. Like that, there is various options. So essentially, what we do is that we develop by mutation. You first irradiate the seeds with appropriate radiation, and then you grow it, and finally you check for the desired features, and then you select it after selecting, and then you grow it multiple generations. So once you get the stable generation, then you release it for your application. So I would like to bring to your attention that typically the release of one variety, it is a very long time consuming process depending on the lifespan of one crop variety. For example, for one rice variety, so it may take something like 90 days for the maturity. So you need to take, first you collect, you choose the appropriate trait, so which is the one which you want to irradiate depending on the qualities. Then you irradiate, and then you induce the mutation, and then you check. The first one is called the M1 generation. Then you choose from that. Again, you go on from that you get the seeds, and then you cultivate for at least 6 generation to ensure that whatever changes, genetic changes that has happened, it is stable. It will be able to reproduce even the future generation. So once 6 generations are completed, then it is actually tested in various agricultural universities, and finally it will be released for the farmer to cultivate. So typically it takes 8 to 10 years for a variety like a rice or a wheat to come to the market. So again, the mutagenization process, it depends on many things. So one is, as I mentioned, it depends on the sample size, dose rate, dosimetry. So all those things initially you do. Then you also do the radio sensitivity analysis. The first stage is you need to optimize the dose. What is the appropriate dose in which that is suitable to induce such a type of genetic changes, then reproducible treatment, and then finally creation of the large scale. Once you stabilize at least up to 6th generation, then you have to multiply it and get it in the large scale. So this is just to show you. So typically there are multiple ways of inducing the mutation. One is by chemical. So there are chemicals which can be used to induce mutation. Other one is called the physical mutation. So mostly people use X-rays or gamma rays. So by using appropriate radiation sources. But currently now people are actually exploring ion beams, then neutrons, and even actually space irradiation is also becoming, like the space agriculture is becoming a new field in which people have been looking at sending the seeds to the space and then getting it back and then checking its genetic variability. So why these ion beams or electrons are becoming important as opposed to gamma rays or X-ray? The main reason is that the energy transfer is actually much higher as compared to the gamma rays or X-rays. And by virtue of this high LET, so they have relatively very high biological effectiveness, in the sense, in the same DNA, at multiple places, the introduction of breakage, that is the double strand break or the deletion, so that probability is very, very high, because you deposit the energy in small region where actually in a much larger amount. So multiple scission that can happen within the same DNA is much higher. So in that eventually that will leads to actually large higher mutation frequency and the mutation spectrum as compared to X-rays or gamma rays. So that is the advantage. So now I will show you some of the studies that has been done in BRC. So here in BRC, using electron beam, mostly we have attempted the mutation breeding in various varieties like the rice, urad bean, cluster, cowpea, horse gram, and moringa. So these are the typical crops in which BRC has done. So one result which I would like to show is actually in urad bean. By using, as compared to gamma rays, the electron beam induced the variant, we were able to show high chlorophyll content as well as their morphological changes. That is the mutation frequency that is observed is compared for the same dose of radiation, it is found to be much higher as compared to that is observed in this thing, urad bean. Similarly, in black gram, so you could see that. So one important development is the increased stem length in plants. So that is very much suitable for machine-based harvesting. So if you want to do machine harvesting, it is desirable to have the stem length higher as compared to the conventional one, because that is amenable for this. So we could get actually a mutant with a large yield as well as the increase that are amenable for harvesting, mechanical harvesting. So their tall mutants are always preferred for mechanical harvesting. Again, large seed size groundnut mutants. So this is the one which you can see that the parent, this is the Trompe groundnut variety which is already released. This mutant TG89 and TG90. So these are two mutants which has been developed, which is under trial, not yet released. So what we found is that the electron beam induced a mutant. So it is in under testing, at Gujarat, Navsari Agricultural University. So you can see about 17% actually perform in Chhattisgarh as well as in Gujarat. In Gujarat, it is about 48% is actually their increase in the performance in terms of the yield of the product. Whereas in Chhattisgarh also about 17% increase in the yield of the product. Similarly, high yielding cluster beam mutant in vegetables using electron beam. So you can see here, this is the parent variety. As compared to that, the number of pods, so that you can see actually in the cluster beam in the mutant that is being developed by electron beam is found to be much larger. So if you have per plant, the number of pods are larger, that could yield, it will significantly enhance the yield of the crop in that sense. So again, these are just for fundamental interest. You could see that there are multiple different types of pods. So something like smaller ones, even long ones, or even different size pods can be. This is of interest to the fundamental studies. Again in Moringa, so what we observed is, so they are typically, normally they grow in large trees. Basically, so the farmer has to, for yielding purpose, harvesting purpose, if you have small plants and where you can actually pluck it even from the ground very easily. So it is a tree type of thing, the restructuring the plant type basically, so that could be achieved even at a small height. It is able to give the yield, and it can be plucked very easily by using electron beam treatment. And also it is a very nutrient species having high protein content and biological value. Then another one is lodging tolerance by electron beam in rice. This is done in Tamil Nadu Agricultural University, Madurai, is in collaboration with, the height of the plant is actually very high, the normal one with a high yielding. But with the electron beam, you can make the stem more stable, and they are of shorter height, and so that it can actually sustain even the lodging at adverse climatic conditions. Then in this again a variety where you can see that the mutant is having a smaller height as compared to the one which is the original, the control or the parent variety at a different doses of irradiation. Then terminal pods, again, this is very important as compared to one is terminal pod with electron beam irradiation, they could develop, which is good for actually mechanical harvesting. Then synchronized maturity, this is also important. Synchronized maturity means, because here actually all the pods actually they grow at the same time as compared to the original parent, where you will see that initially it will come and then it will grow, the yield will be in a different stages, whereas here you will get all of them will mature at the same stage and you get enhanced yield varieties. Then in horse gram, again, this basically it is electron beam versus, but both by gamma rays as well as electron beam. You can get early flowering about more than 15 to 12 to 15 days earlier. So it can start flowering, so that yield can start giving you the yield much earlier than the control variety. Then in horse gram, you can see per plant the number of pods are actually much higher as compared to if you have much more pods per plant. So that will also add to the yield, significant enhancement in the yield. So we also do during this experiment, not only that we look for the qualitative assessment of the quality of the yield, but we do the characteristics, either molecular and the gene level characteristics of the parent, once it is developed, the parent and the mutant variety. So in this case, it has been done by other experiment. It has been shown that, so this high yielding variety or the large seed variety, because there is a change in the size of the cells that has been developed within these seeds. So since they have, as compared to the original one, you have a larger size cells, the cell dimension is higher, that eventually leads to large seed size, because the number of cells may remain same in all of them. So, but it leads to a higher yielding crops. One is the cell size, and the number of cells per layer is also more. And similarly, the genes, so they do also do the genetic mapping, which are the genes that is involved. So once we the stable varieties obtained, the parent and the mutant, the complete gene sequencing of the parent and mutant will be done. And by that way, you will be able to identify which are the genes responsible for a specific trait that is being observed for that plant. So once we know that, this will help in future if somebody would like to introduce genetically modified variety. So which gene has to be introduced, that can be studied by using this type of approaches. So this is just
you have 5 more minutes.
Yeah, I'll just this is just to show you some of the results. So it is again whole genome sequencing. I will not go into the details. So how we can identify the number of deletions, insertions, and single strand breaks. All those things can be studied. I will just show you a couple of preliminary attempts to do the proton beam induced mutation. So as compared to the other gamma rays. So here there are several challenges to look at when we have a proton beam, because the orientation of the seeds are also very important, because the beam has to penetrate through different layers, and it should introduce that changes in the genetic component. So what is observed from literature is that if you look at the electrons or the carbon ions, you can see the number of mutation frequency observed is significantly higher, something like 3 times or 3 to 4 times higher than that is observed in using different beam. So our colleagues have developed by using in collaboration with the Pelletron facility, an automatic scanning, seed irradiation system, in which the seeds can be arranged at different levels, and it can be moved inside to the beam side aperture, so that different seeds can be irradiated at different time points. Sorry. Yeah, so this is the preliminary experiment. The first stage of experiment is to find the appropriate dose. What is the dose that is needed? So if you look at it with an increasing dose, you can clearly see that the growth of the plant is retarded. So this is the region where we will find actually the good genetic variability in terms of the yield. So we need to identify. So if it is too high a dose, the plant will eventually get killed, and it will not be able to survive. And at very low doses, you will not be able to find much change as compared to the original parent. So first you optimize the dose, and then identify. So this is only preliminary with respect to the proton beam. We have done the preliminary study to identify the dose response, and finally the traits are under evaluation. So I'm happy to say that with the various with the efforts from mostly by gamma-induced mutation, BRC has so far delivered 70 trompe crop varieties, which is popular among the farmers in across the country in various crops, different varieties. So mostly in groundnut, we have about 17 varieties that is being developed in groundnut, and is under cultivation in many places all over the country. And last year, we could get about 8 varieties in 2024 with different characteristics. And so this is the map which shows actually which are the places our varieties are being released and utilized. We have our presence in all over the India. We have been working on various varieties. So just to give you the final perspective, I believe that actually, so this is just to show that actually how radiation technology is important in agriculture. So this is the last year, the news item that has come, Dr. Jitendra Singh, our minister, honorable minister, has in the assembly, parliament, he has actually indicated the role of DAE. And in IAEA also collaborating electron beam application. So there is a lot of interest in food, agriculture, and of course in health and environment. As you all know, you may hear from some other speakers. So IAEA is also putting a lot of emphasis on use of electron beams in future. And incidentally, last year, China has actually set up an electron beam based accelerator specifically for crop improvement program. So there is a enormous scope for the accelerator community to venture into these fields. And I believe that in future, we could get actually more new desired crop varieties in this. Oops. Where is it actually? Yep. So with this, I would like to conclude my talk, and mostly I have taken help from my colleagues, Dr. Anand Sauframanian, Gautam, and Dr. B.K. Das. So they have contributed to this. I am only a spokesperson on their behalf to showcase some of the activities that is being done in nuclear agriculture. Thank you very much. I'll be happy if you have any queries.
Thank you, Professor Hassan, for a very nice and a different perspective. Personally, I'm very happy to see results from our VRCTF Pelotron facility. The talk is now open for discussion.
Can I have the first question from you, sir?
Yeah.
Yeah, please.
So this radiation can damage a DNA sequence. Can it also create a new DNA sequence?
Radiation, it can damage. So that is why I told you need to optimize the dose in which we do not go to that high dose in which the DNA can be completely damaged.
And
but you know this DNA, it breaks and recombination spontaneously. It do happen even in natural
what you said that 6 generations. So is it repairing itself in those?
Yeah, it itself repairs. So that is the dose we work on. We introduce the breakage and it repairs by itself. During that repairing process, it can actually make changes in the sequence.
Thank you.
So that will lead to actually new
I
traits.
see a lot of hands, so I'm going to ask everybody to ask only one question. So
Hello.
then Puntambekarji and then one more there.
Sir,
Yeah.
one question.
Hello.
Please wait for your turn.
I just have a very fundamental question. In fact, it's a very interesting to listen to your talk. My basic question is that, see, you are increasing the rate of mutation.
Correct.
Artificially.
Yes.
So there is a natural set of mutation taking place. You are enhancing that and increasing the yield, things like that.
Correct.
So what about the, consequence of that if a person is consuming such mutated food in terms of, because when we go for public awareness program and all, quite often people ask this question, what is the quality of the product which you are irradiating and breeded this thing? So definitely you might have done some studies. Can you please?
Yes, very good question. So that is why first itself I told it is entirely different from genetically modified varieties. In genetically modified varieties, what you do is the entire gene, so more than 20 base pairs that the sequence that is being introduced through an external route into the system, and what is its consequence in the life cycle or the consumption is not yet actually established fully. So GMP is often not actually recognized. In this case, we do not introduce any artificially any gene inside this. We only, because as I mentioned, because the spontaneous, even the cosmic rays or whatever radiation in our body also, you know that the viruses, they mutate very fast. So you don't know how to do, because they are the sequence like this very small. So it can actually, their life cycle is very fast. So you are able to observe. In humans or any organism, it is very difficult. You have to actually wait maybe years, thousands of years to find actually any change. So here, what we do is that we don't introduce any gene sequence in the system. We are only, it is again, it will break and recombine by repair itself. So there is no adverse effect, which otherwise would have happened. But it will take in this plant, if I do, I have to generate maybe some thousands of generation it come. And this has been already people have been doing. They do the selection and crossing, and you choose and then you deploy it.
This has been experimentally proved.
Yeah. So what we do, the second point, what we do is that it's not only just you introduce. So when you introduce these changes, giving radiation, you artificially you break and recombine. What happened? There are many things can happen. Some of them will be actually poor nutritional value. Some of them will be of not very high yielding. So all those things are actually eliminated. So this is called a mutation followed by screening. So that is why it takes 10 years to screen and see that only those traits which are actually permanently retained and without loss of its nutritional or any adverse value. So this testing has already been done. If that is not the case, then this ICR will not permit you to release. So, you know, in one irradiation, I can get 70 varieties. But for the last so many years, we were able to release only 70 varieties.
Okay, thank you.
Yeah, we are running really short, so only one last
Yes,
question, and for others, please discuss in the tea time. Yeah.
Just one question. This selecting optimum dose for getting particular variety or particular, you have a lot of data. So are you also working in the field of AI-based techniques to decide what type of, say, to optimize the dose for any particular trait or this thing? Any work is going on?
No, as of now, we are not doing. We do actually the real experiments we do and we try to identify. But I know people have been using AI to choose. There is something called sequence-based screening. So, for example, that is useful if the lifespan of that plant or the crop is very, very high. So I cannot wait actually, say, for example, in coconut or something like that. So you see all the varieties, they are only something like a 3 months duration. So where it is possible within 3 months, I will be able to experimentally get the data. So there is sequence-based screening. So if you, when we do this experiment, once we identify one is giving a high yield as compared to the parent, now we do the sequencing, gene sequencing, and identify which are the common genes that is actually showing difference in these two. So multiple genes we identify, and we then people try to do, you can knock out that genes, and then you see that really whether that gene is responsible. So if you know that, then when you want to do the screening, you do only one generation you grow, and you get the seedlings, and you do the gene sequencing, and there itself you will be able to screen and then eliminate. Instead of doing 6th generation, automatically you grow. So that is the advantage what people are looking. But other than that, AI, I am not aware of actually.
Sorry, we need to close the talk now. So thank you once again for a very interesting talk. And let's also thank all the speakers of the session. You have a moment from the organizers. So.
Thank you so much.
Very nice. Should give a talk in TI for
Yeah, thank you.
Madam. On behalf of organizing committee, I would like to express our sincere gratitude to Dr. Vandana Nanal for navigating this session seamlessly. I now request Sri Mahendra Lad, Director, Proton Accelerator Group, to present a memento to Dr. Vandana Nanal as a small token of our deep appreciation and sincere gratitude. With this, we come to the end of the third technical session of INPAC 2025. Now there will be a 30-minute tea break. I request all the participants to join back in the auditorium for the fourth technical session by 11:30 a.m. Thank you. All the participants are requested to be in the auditorium back by 11:20 a.m. And there's one more announcement regarding the ISPA membership. Those participants who are not members of ISPA can obtain ISPA membership by filling out the registration forms that are available at registration desk. The participants who are having posters for today can go downstairs in the poster session area and place their posters on the respective boards. The list of mapping of the poster boards and the abstract IDs is there in the area. We will reassemble here back at 11:20 a.m. for the 4th technical session of INPAC 2025. I request all participants to join back in time.
Hello, welcome back. We are going to start session 4. In this session, there will be industry presentations also. And for chairing this session, I invite Shri Tushar Puntambekar ji. He is graduated from 31st batch of BRC Training School, and he has expertise in synchrotron radiation source and beam diagnostics. He has earned various awards, including DAE Scientific and Technical Excellency Award. He has more than 90 publications in his field. I invite to chair this session.
So welcome to the 4th technical session. And the first invited talk of this session will be given by Professor Raghavendra Tiwari, Director Materials Group, BRC. He is a PhD in metallurgical engineering, and his areas of research work are physical metallurgy, refractory metal alloys, transmission electron microscopy, pump probe spectroscopy, materials for nuclear reactors, alloy designing. He has received various awards which are listed here, and he has more than 261 international journal publications. With this brief introduction, I now invite Dr. Tiwari to present his talk. And I will give a alarm bell at 20 minutes. Total is 25 minutes. I will give at 20 minutes for when 5 minutes are remaining.
Yeah. Okay. So welcome back after tea. And basically, at the outset, I want to thank Dr. Chokse and his team for inviting me. See, the topic I'm going to give is slightly different because I know the community is an accelerator development community. I am the user of the accelerator. Rather, one of the first user of accelerators. I started from VECC. I have gone to different places, including the latest LEPA. We have used it. And I wanted to convince you in next 25 minutes why you should also look for accelerator to test materials. So with this idea, because you all know, when we are developing new structural materials for any nuclear reactor, the problem is that apart from the high temperature strength, very good ductility and many other factors, corrosion resistance and all, in nuclear reactor, the material should sustain the irradiation damage caused by the fast moving neutrons and other fragments of that. So because of this, accelerators provide a very nice tool to examine or scan the materials for the new coming up reactors in that. To tell you my point, that suppose I want to do one experiment in the neutron to assess the neutron damage inside the nuclear reactor. I have to at least cross through the 3 committees, and before I start the time I have sort of got about the idea to work and the first experiment to start, it takes nearly 1 year time. Then reactors design, capsule design, everything takes another 6 months. Then after 1.5 years, the system goes inside my samples go inside the reactor, and amount of the damage if I want to create in my materials, I required a residential period of 3 to 5 years inside the reactor. When this system comes out of the reactor, it is highly radioactive, so you cannot take it away. So the only way is that it rests in the bay, and then it moves to PID, that is post-irradiation examination division. They will first assess whether the radioactivity on the activity on this material has reduced considerably or not. Otherwise, you have to wait. So the point I wanted to say, just to generate one data, I had to wait 7 to 9 years time. Now in this time, I will be retired, my young fellow will be retired, even the younger fellow will reach the retirement. Now if suppose he doesn't have interest, so these samples are going to become national liabilities. So that is why this is not the way to do experiment, and this is the one of the reason that material based reactor was the one concept we mooted long back, nearly in 2000. And lot of debate has taken place now. HFRR is something which is being proposed now to cut down this time. But so we had to look for an alternate way, and that is where accelerator comes very handy, because the same experiment in neutron, which is going to take 2 to 3 years time, in proton it will take only 2 to 5 days time, and as a consequence your entire damage can be generated. And the best part is sample is not radioactive, so you can immediately take it to the lab and scan it. The only precaution here to take, that the energy of the proton should not be more than 8 MeV, otherwise it will cross the Coulomb barrier, the nucleus, and your sample will become radioactive. So to do that, if I want to do a larger damage, we talk about DPA, 100 DPA, 20 DPA, 40 DPA, then you have to take the shelter of heavy neutron, because heavy ions, they can give the very high dose without generating any radioactivity, because the Coulomb barrier in case is very, very high, and generally 300 kV, 400 MeV, you can work very easily and generate the damage. However, everything is not very simple, because in case of neutron, the most of the damage is very low one and fairly uniform across the thickness of the sample. But in case of proton, suppose I put 3.2 MeV proton, in the beginning that you can see the dose rate created is nearly 3 order up. So your time comes down 3 order lower. But the point is that it is not travel through the sample, but the first thing, because it's a positive charge, it will immediately experience the electron drag from the free electron of the samples, and as a consequence it will start reducing energy very fast, and moment it reaches to the cross section where elastic collision can take place, it will dump all the energy here, and this region we generally call as a Bragg peak, where most of the energy is dumped. Most of the defect will be located only in this region. In contrast, if I take heavy ion, then most of the damage is in the 5 MeV range. And this is the one difference. The second difference is that MeV, if I take 1 MeV electron, only handful of the Frankel pairs, that is the interstitial and vacancy, will be generated. However, if I take proton, because the mass transfer will be not very efficient, because the size of the masses between the proton and your atoms are very large. So many kind of cascade damage will be taken, very small, very cascade damage take place. Heavy ion generally mimics the neutron one of the best way, but it generates only on the surface. With this limitation, we have to design our experiment to extract the value which we want to do it. And that is where I want to tell what efforts we are trying to say and what accelerator can provide us. Accelerator can provide us very good control over the irradiation parameter. I can control energy, I can control temperature, and I can control beam energy, I can control overall influence. So as a consequence, I can select the variable and control it. So that is the advantage accelerator provide to me. Now, just to give you example, we have taken 316 stainless steel. It was damaged by the neutron as well as by proton. And then we were looking at random grain boundary and see how elements are distributed. As you know that the defect generated by the irradiation, they provide a path for atoms or the solute atoms to diffuse to the different sites. What you can see, the pattern by the neutron and proton is more or less same everywhere for all the elements almost. So what I wanted to emphasize over here is proton does mimic the effects of the neutrons. The only problem was that if you look the this thing strength, because proton was experiment done at 360 as compared to neutron, which has the reactor operating temperature. So what you can see is there is a difference in the yield point, but the pattern of the yield point, that is increase in the strength, is very well again represented by the proton. The strength increase is generally comes at the cost of ductility, and that is what we call as a irradiation embrittlement. That is why you cannot keep the sample inside or even the structural material inside the reactor very long, and life of the reactor becomes because is shortened because of the life of the structural materials. So with this, I just want to take you and one few more points just to give the basic of that these one line what you see are the dislocations which is generated because of the defect into the material. But these kind of small loops, you can see all the dots, these are generated by irradiations. Their density and their size decides the properties of the material. And this is where we do the localized work and try to extract the information from that. See, what exactly happening is that your ion is coming, hitting, knocking off the atoms from the lattice, and if it has sufficient energy, if it will knock the subsequent next atom, it will, if that atom has a sufficient energy, it will further, as a consequence, a cascading chain starts. But these interstitials, they migrate very fast as compared to vacancies. So what happens, majority of the time these vacancy, they coalesce together to find this depleted zone, and these depleted zone are the reason for the loss in ductility and cause the reason for that. Now, since most of my defects are generated locally, so I have to design my experiments and tools to look into only the local region. For example, I don't do normal XRD. I go for the gazing angle XRD so that I know the interaction volume. I generally look into the TM, taking especially from the region where the damage has taken place. Nano indentation, which is give you the information exactly from the region where you want to take out the thing. And nowadays 3D atom probe. This 3D atom probe gives you the atom by atom information. These tools are now available. 20 years down the line, we didn't have so many tools of that except TM and nano indentation from outside. So we get all this information, and then we take the rescue over the simulation. So I will just take you how. See, this is the typical, you must have seen that the multi-scale modeling, people work ab initio where atoms are taken. What we do is we don't work on the ab initio, we work on the molecular dynamic simulation. What we do additional, that apart from taking the potential energy function from the ab initio calculation, we take the input parameters from in terms of defects, their density, size, and insert in the molecular dynamic simulations. From here, I take different slip system activity interaction coefficient, go to that this thing and try to generate them by the dislocation dynamics, then try to go to the continuum medium. In next 20 minutes, I will try to show you how we are using it. For example, this steel T91 steel was prepared by us for the fusion reactors in the ITER. This steel we wanted to test it. So argon gas ion were used. This was used in the ECR source in VECC, and damage was generated. So 5 dpa, 10 dpa, 20 dpa, 3-4 samples were generated. What we have seen, different defects, as you can see, these kind of small loops are there. Some voids are there, and particles started dissolving back. The problem is this getting the sample from the same place, and because a lot of defects are there, background diffusion is very high. Then what we had done, that we had done the nano indentation, and what you can see that unirradiated sample as the radiation increased, its strength is hardness is started increasing, because for the same depth the load is increasing. And if I can plot the difference delta H, then what happens, the delta H shows the same behavior as the yield strength change is there, which was predicted by this was available in the literature. So what we have shown that if you can do this experiment, you can do this experiment of the change in the yield strength, or you can do this experiment of the nano indentation of very small sample, and you get the same data. Now, I need not to put so many sample inside the reactor. If I have this master curve available with me, I know that what is the multiplying factor which we have worked for it. This is close to 0.32 something. So what happens now for the future till this is holding? So we can go up, this is 20 dPa. If you do one experiment of 100 dPa and you find that that is also lying on the same line, I can predict the yield strength for different dPa, and I can tell you this material is going to stay for this many years in the harsh fusion reactor environment. So this gives me advantage that the materials requirement reduces, you get the same information, and without wasting too much time, you can find out whether this material is suitable for the time predicted by the designers. And this now I'll take you a little bit deeper into that. When these defects are generated, these dots line you can see all around. And these dots we can count, their size we can count, and start going back to the MD simulation curve. The left side, this curve is a pristine sample, no defect. You can see all the dislocation lines are linear and they move very smooth function. Moment one is introduced here, you can see there is a buckling here, because this defects that hold the dislocations, they don't allow it. And if you have multiple of them, then this dislocation will not move. This retarding of the dislocations during the motion manifests itself in terms of increase in the strength, and then you can calculate that and you can find out that this kind of density, what is the increase in the strength. Now this strength I can theoretically calculate, and I can experimentally come out with the nano indentation. So I can always cross check whether my simulations are going correct or wrong. And that is why when we found this was slightly under predicting, so we started going to the next level, that is straight away you start simulating nano indentation into the material. When we do that, we have shown experimentally that this experimental curve was generated here, which I have shown you before, and now we started simulating. Simulation has one advantage, that I can introduce only one type of defect. For example, just vacancies, or a void, or a dislocation loop. So I can find out which particular defect is the most potential defect in increasing the strength. That was the idea. So we started using this. So what you can see again, the pristine sample will show you the very large dislocation vector. But if I start putting the loops, only one type of loops, you can see there is a symmetrical distribution of dislocation. Here it was more or less uniform. Here it is one particular dislocation which is interacting with these loops. They will grow faster as compared to other which get arrested. And if I have vacancies, lot of these vacancies hold, like this sort of a very large group of the ants can bring down the elephant. The same thing is happening here. They are not single vacancy is not a very potential threat, but number is very large. They can really bring down the dislocation motion to zero. So vacancies which people were in the beginning were thinking very harmless things, they are really very harmful in general sense. Now I will show you the void. See, this is the one void where this dislocation is there. So we were trying to simulate this and wanted to show you that when the dislocation comes close to the void, it's feel sort of attraction towards the voids because of the stress fields are like that. And then if you had to apply the force, the dislocation find very difficult to come out of it, and your stress level will keep increasing. Now, moment it is released, you can see the dislocation, the stress comes down drastically. Now, these values largely depend on the diameters there and their number density. So, I can simulate that if suppose my fusion reactor is working for 3 years, how many voids will be generated, how many voids are there, and how much is the change in the strength. So these many things where accelerator comes very handy to use and predict for the future materials. So I will give you one more example about zirconium alloy system where this experiment was done. See what happens in many of these defect systems. Some of the zirconium materials without showing any prior sort of a event for the failure, they generally give some prior symptoms. Some of the zirconium materials failed. This is not our problem. Problem happened in England. So we had Indo-UK project. So that time this discussion took place, how to find out what are the reasons. So they had partial information and rest of the information we have supplied. For example, over here, if you see what we are doing, we have experimentally know the orientation of the crystal. We do the nano indentation. And then we can find out that if the sample is in a pristine stage again, the dislocations, when you take the indent, dislocations generate. When you take away the indent, the dislocation go away. But in case of irradiation, if you are doing it, this environment little bit changes. While going down along with the indent, the dislocation try to sweep or clean these structures. And as a consequence, when you do multiple times, this kind of channels are generated and these channels becomes very soft. So all the deformation takes place only through those small channels, and as a consequence, the materials fail without showing any symptoms. And this part we have experimentally shown, and we have shown that, and we have worked it out, and we have shown, this was the paper written by them about these small channels, how it is they are affecting, changing the properties. And then we have shown even at dislocation by dislocation, interaction by interaction, and how it can be done. Now, this is the one set of experiment, and here again the irradiation was done. In the proton irradiation was done, and large single crystal zirconium, and then we had taken sample out of it and wanted to show how the defects takes place. And again I will show you that defects, because of the presence of these defects, the atoms are again, these dislocations are bowing down all along, and you can see that I can capture this picture over here where these dislocation was there. So many points dislocations, these are generated, strength properties are calculated, and based on that lot of work was done. And these all work were done inside in the proton and other electrons. Now electron irradiations can also be used in certain cases. Why? Because electrons do not generate too many vacancies, but they do generate lot of electronic excitation. What is that is, they say phonon. They induce certain phonon. As a consequences, some transformation take place. In case of zirconium, this transformation is very common. That is beta to omega transformation. In this process, because of the electronic excitation, the constant vector, the collapses here, and then atoms started moving onto that side. And that, as a consequence, you will have, I think it doesn't move. Should not go out. So what happens that you see additional reflection started coming in this dislocation in the selected area diffraction pattern, and the transformation starts. This is the BCC structure, and it started collapsing and becoming completion takes place here, and it manifests itself in terms of these two dots and their movement of that. So I can very constantly predict this movement. So when it becomes 0, then my transformation is complete. Now electron irradiation, when we carried out at 473 K, you can see that the transition started, it has reached to the completion, and then it holds over there. But now if I take it at 573, you can see that everything is started, reaches to a near completion, it appears is going to complete, and then it reverses back. and everything started dissolving back. Question is why and how? And this is the question in the zirconium. Whenever you design the alloy, everybody was scared of forming omega phase. Omega phase comes because there's a lot of beta particles are there. They can locally induce this omega phase, and if the omega phase has formed, its material will become brittle. And that's why entire zirconium, this flow sheet philosophy runs behind that. And then there 3-4 decades there were questions that why it is happening. So just to give you idea, if I take and just age the sample, again the same transformation takes place, but it takes nearly 1 lakh seconds. But if I do the same thing with the use of electrons, it completes within few hundred seconds. So this gives the advantage.
Yeah, 5 minutes.
Yes, sir. And then you have, if I increase the energy to 2 MeV and temperature, these transformation do not reach to completion, that they hang out in the middle. Question is why? So we were trying to answer this question, and then we have found out that the vacancy concentration, how small it is. If it is there generated by electrons, then there is you can define the entire system as a region of instability and region of stability, and then vacancy concentration is the deciding factor in case of electron diffraction. And based on that, we have shown not our result, but all the results published in the literature were superimposed here, and they follow the same logic. So everything was rationalized based on that. Now, since time is little short, I wanted to just show you a couple of things. This is in zirconium 1 niobium. This material is used in our this thing for the naval submarine systems. So what we wanted to show how the damage does. So we have taken out this snapshot at different DPA values, and this is our finding, that as the displacement damage increases, in the beginning, the particle increases, size increases, and then it comes down and dissolves back. Question is why? This was done in electron irradiation and neon radiation under electron microscope in England. So in this process, we have shown that what is the reason for it. The reason for it, in the beginning, niobium tries to move because of the because of that excess, there is a lot of excess niobium available in the matrix. That is why the defects were in the beginning, they were increasing. But as we generate too many defects into the system, it will dissolve back. So based on this, we have predicted many properties and corrected it. Now, there is the last couple of example I want to show. Now currently we are doing for the RPV steel, which is going for the Indian pressurized water reactor. So in this, what we have done, that again microstructural characterization was carried out by taking different sample, and then data was fed into the continuum model, that is FEM model, and I'm now trying to generate the curve. You need not to do the test. I can generate the curve, make the profile for you, and the property will be completely predicted by them. And this is the example. This is the one EBSD pattern where color is showing the orientation of the different lattices on that. And based on that, we have generated texture data. This is experimental texture data. Then by FEM model, we have generated the simulated data and matched them. Based on that, we have developed this this different equations. I don't want to go into detail. And then we have generated the curves for different loop sizes and others, and predicted that the old analytical model which is available in literature does not predict a small deviation we have observed in the RPV steel. And that sometime if you miss that part, this will be life limiting factor of the RPV steel. The irradiation, most of these experiments are being done. We have shown that how the irradiation is increasing the strength at the cost of ductility. Those parts have been done. Still some work is going on. And now I just wanted to show you this point, that our simulation result shows this curve. And these experimental curves are coming very close by. We have finished for 2. This was done in the neutron experiments. Now I'm waiting for the sample to come out the neutron so that we can do experiment. Now we want to do this experiment in well-designed accelerator which can mimic the structure. Once that is done, and if I can reiterate this curve in the accelerators, my job is done, because then I can predict RPV can work for 20 years, 30 years, 100 years. We can do this kind of prediction. So what I want to know, in short, I want to tell you in the end, that see, accelerator provides me a much shorter and efficient way. And that's why we look for the materials-based accelerators. So far, most of the accelerators are used for doing the basic physics experiments or some different other experiment, or for the Proton for the spallation sources and all. For materials based accelerators have never been thought of, because what we required, LEPA was one. So what we generally do is, whenever such accelerator comes in, because guards are lower, people are still ready to test whether their accelerators are working or not, we generally go and do our experiments. We did in TFR, when the TFR was, Pelletron was going on the process. We did in VECC, when little window was made available to us. Then we have done in the LEPA, we were one of the first user of LEPA. Even in abroad, Bakum, in the Janus, in Manchester, wherever we get accelerator, and we use that. The reason is, so far accelerator community has not given very serious thought about making accelerators for testing materials, which is a very practical aspects or application of accelerators. So you have listened Dr. Hassan talking about accelerator for the biology. I am talking about material. Thank you very much for your kind attention.
Thank you, Dr. Tiwari, time and on a very comprehensive presentation on the irradiation damage, study of irradiation damage on the structural nuclear materials. Now the talk is open for 1 or 2 questions. Yeah.
Sir, this 8 MeV is the limit you told for the proton. So how that is decided? And next question, like we have RFQ and the lower energy like 3 MeV or 5 MeV, whether that is useful energy?
Yes, it is. Actually, see, the point is, my window is like this. 8, the upper limit is that Coulomb barrier should not be crossed. Okay. That is the upper limit. Lower limit is that ion should have sufficient energy to displace atoms from the unit cells, so that the defects are generated. Okay. There are 2 problems in case of most of the accelerators are there, that either they go for 20, 40, 60 MeV proton. Then it is generally meant for some other experiments. Rutherford backscatter and all those experiments, they are more inclined. So what happens for them, just like LEPA, it was 10 MeV, I was using it. Now they moved it to 20 MeV, it is useless. So if my requirement is relatively in a high energy, means in the MeV range, as you're telling, 5 MeV, but current should be close to milliampere side, so that I can cut down the time. Suppose it is 100 nanoampere. So it will take me 10 days to 15 days to generate the damage. Who is going to give me accelerator for 10 days for doing one experiment? Because that is where materials-based accelerators are slightly different from others. So a small this thing, if you can give 900 nanoampere is the minimum requirement. 900 ampere current, 5 MeV is the one of the best thing I can do a lot of experiments.
Like we are going to commission soon this RFQ kind of.
Yeah. Actually, this is one of the reason I started coming here, just to figure out what is happening. And that's why I wanted to contribute also.
3 MeV is useful for you.
Yeah. 3 MeV is very useful for me. See, I've shown you 2 MeV, 1 MeV kind of results. Right. They take time. See, problem is, it is difficult experiments, easier said than done. See, if I expose 10 samples, the correct configuration hitting, while sample preparation hitting the correct region, will be successfully done only in 2 or 3 samples. Okay. 6 or 7 will go waste. We'll miss while preparing the samples. So I didn't go into those experimental detail that is done. So this is why 10 sample if I required and 1 sample is taking 10 days. Nobody on earth can give me this accelerator. Yeah.
Okay, thank you. We can take one more question. Yeah, please.
Sir, I want to
Hello,
ask
sir.
Just, okay, I will take yours. Don't worry. Yes.
Sir, how you compare this ion irradiation with the neutron damage? Because ion and neutron both have a different properties. So you are doing with
Correct.
ion.
This is exactly I was trying to show in my second slide. They are different. You have to design such an experiment what you want out of them. See, defect generators are slightly different. The spread out defects are slightly different. So you have to see the local where these properties are matching and take sample only from that region. In the bulk sample, they are totally different. What you said is correct.
Because neutron easily pass through these material
yes.
and
yes.
So where ion is easily stopped by the.
But my point is I have to predict how many neutrons a material can bear. That I can do by accelerator very easily.
Yes.
That's the last question. Yeah, he was.
Sir, I want to ask, you are talking about the DPA.
Yeah.
What about the rate of DPA into the material? Rate of progression of the DPA?
Yeah, that's why I gave the value there. See, DPA and rate of DPA both are important. That's why I'm putting the condition on the current close to 700, 900 nanoampere kind of thing. Because higher you put the DPA, rate is not going to increase. Basically, the recombination process also takes place.
Yes.
Nature has a tendency to restore.
Yes.
So what happens if you generate too many defects too early, they will cancel themselves anyway. So that's why there is an optimum window on which you have to operate.
And one more thing, sir, since RRCAT and DA also is proposing for a 6 GeV electron synchrotron, and that has also potential for radiation damage.
Yes.
So this electron beam, 6 GeV electron beam radiation-induced damage, so that is also a potential studies for.
Rather, we have this in our proton accelerator, electron accelerator in our Kharghar, commercial electron. We using those two also. I tell you, there are many examples I have not given because those examples will not excite. See, dosimeter,
yes.
What you use, okay, how to calibrate them. So there is a CAF2 crystal comes, but to generate appropriate dose in that to generate the calibration, we don't have anything. So we 100% depend on foreign, whereas such a small thing we can do ourselves. So that is where these kind of accelerators are very useful.
Thank you, sir.
Yeah.
So let us thank Dr. Tiwari once again for a very nice time. On behalf of the organizers, it's my pleasure to present a moment to Dr. Tiwari.
With the permission of chair, I will just make an important announcement. Those who are interested in visiting Indus facility, tomorrow morning, 7 o'clock, bus will leave from RRCAT guest house, and we can accommodate 30 persons, or if more will come, the organizers will make that arrangement. Their names may please be given to the registration desk, and not to mention, no pen drive and mobiles are allowed inside, and one has to carry their host institute ID also. Thank you.
So the next talk is by Dr. Manjari Pandey. She will be speaking on roadmap of integrated RF systems for ion accelerators at BRC. And display the profile here. So Dr. Pandey holds PhD degree from Mumbai University and she received the S.N. Seshadri Award for indigenous development of inductively coupled plasma mass spectrometer by IPA.
and she has 150 scientific publications in international conferences, journals, and symposiums, and one paper in international book chapter. You have 20 minutes total presentation, so I will give a bell at 15 minutes.
Sure. Good afternoon, everybody. At the outset, I thank the organizers for giving me the opportunity to talk about our work. So on the behalf of my colleagues in ACND, I'm presenting this work. Somehow the first slide is not visible here. So I'm starting directly with the second line. So the title of my talk is Roadmap for the Integrated RF Systems for Accelerators, especially ion accelerators at BARC. We have been, BARC DAE has been proposing upcoming accelerators, and RF technology is a very important part of that. So I'll be talking about the roadmap for these radio frequency technologies. So outline is the roadmap and existing technologies. I will give a very brief, and then the upcoming MEHPA, then LEHPA upgradation, and the devices technologies, all these things. So this is what I will be talking about. So it is high power RF systems for LEHPA upgradation. So cyclotron, we are for cyclotron high power RF systems, we will be just exploring. Then we'll be going for MEHPA, also the devices and the solid state technology. In any accelerator, if you are experienced, the majority RF AC mains power is distributed across many things, but the major power is consumed by radio frequency accelerator, radio frequency power systems, high voltage, high current, power supplies, magnets, and vacuum. So it is very important that the efficiency of the accelerator, now in the worldwide, everybody is interested in high efficiency accelerators, and in high efficiency accelerators, the RF system of high efficiency are very critical, and hence the wall plug efficiency is very important, and it is being improved across all the major labs in the accelerator labs across the world. The key important system is again RF, and as everybody is aware, the wall plug efficiency will have AC to DC, DC to RF. So our job in RF technology is to improve the RF efficiency of the RF system, and hereafter whatever are the presentation in that, right in the design itself, design aspect itself, we are designing from the good wall plug efficiency, reliability, and all those things. I'll just pass through some existing capabilities. You can see everybody has talked about, and everybody is aware that 20 MeV LEHPA has been already installed and commissioned. So in this, ACND has a major contribution in the form of 3 klystron-based RF systems of 1 megawatt each, 1 solid-state RF system. So this is only about high-power RF systems. If you see the integrated RF system, the high-power RF system, prior to that, will be low-level RF, then there will be RFPI, resonance control system. All those things ACND has already designed, developed, and deployed, and has been used in 20 MeV commissioning of the LEHPA system, LEHPA. Similarly, under the aegis of Fermilab collaboration, Indian Institute of and Fermilab collaboration for PIP2 IT, PIP2 we have a collaboration under which for PIP2 IT, which is prior to that demonstration, you might have heard already with Mr. Sarwan yesterday. So we have already have a contribution towards it, and we had developed and deployed for PIP2 IT 8 number of 7 kilowatt systems, then LLRF, RFPI, then resonance control. All these things have already been developed under this collaboration, and in the next phase, we will be continuing with many more systems like this. And again, I'll skip this diagram because this shows again the RF systems, same RF systems, and the LLRF, RFPI, again the ACND contribution for under IIFC collaboration. And then also prior to this, we have also developed tetrode-based RF system 60 kilowatt. Now everywhere except the main RF device, which is either klystron or tube, and the circulator, everything else is very indigenously developed. And hence now we have the wide experience in tetrode-based systems, klystron systems, and solid-state array. So basically the lessons learned during all these developments, taking into account all the futuristic technologies, advancements, the feedback generated because of this, we are going to use this in our all future accelerators, and where there will be RF technologies, structures with low cost, combination of discrete and distributed architectures, then energy recovery techniques wherever possible. So, and coming back to the RF technology, we need to have high efficiency vacuum devices, probably multi-beam klystrons, multi-beam IoTs, high efficiency, high voltage DC supplies, low insertion loss RF transmission components, and the simpler control philosophy. All this with high MTBF and low MTTR, so to have high RF availability for the accelerators. Similar goes for the solid-state amplifiers and digital LLRF systems. So BRC has already embarked upon very ambitious projects for 1 GeV Linac, in which there will be phases. It will be equivalent to LEPA, MEHPA, and HIPA. Then 30 MeV electron Linac, heavy ion accelerators for IIB. All this will be at VECC. And then we are also exploring the option of high energy cyclotron. And all these RF accelerators do have a high power RF systems and low level RF systems. And hence they are very critical and have a very high amount of contribution. Normally in any RF accelerators, the percentage of RF systems, both operational cost and investment cost is very high, and they decide the overall things, and hence that decides the economics, and hence the very reliable and very efficient RF power systems has to be done for the future accelerators also. So I'll just, I'll be talking about for the roadmap ahead, advanced RF systems in which there will be indigenously feedback compensated solid-state amplifier development. Then as a device, we don't want to depend only on one technology. So we are diversifying horizontally also for indigenous klystron development, indigenous input, inductive output tube development, digital LLRF, most of them is already, the development is done. Also fast RF protection interlock. This is project wise, and I will be giving the indigenous solid state technology we are going to design for MEHPA and LEHPA upgradation, in which we plan, the details will come out in the next slides. In this, we plan to develop feedback compensated solid state amplifiers as well as IoTs or klystrons. And then for cyclotron, we are just started exploring the new kind of RF systems. It will not be the duplication of whatever is earlier. New concepts, new combinations we are using. So these are the already LD MOSFET based systems which have been developed, but with the new RF MOSFETs in the horizon, we are transforming this technology in the more higher power. Then we are also, this is the model IoT, and then there will be klystron. So for MEHPA 40 MeV at VECC, we need a lot of amplifiers, 20 kilowatt, around 8 to 9, and around 14 to 18 numbers of 50 kilowatt amplifier. So here our basic architecture remains the same, but we will have two configurations. We are studying these two configurations. One is a cavity combiner based system, and one is like Triumph. We have already 20 kilowatt or maybe 50 kilowatt. We can combine the racks together. Now with the new MOSFETs, 120 kilowatt, which we have already developed, will give me now, if I use a new MOSFET, maybe 30 kilowatt. So my life may be easier from the power combining point of view. So different kind of combiner development we can do here. And we plan to go for either of the option for 40 MeV MEHPA. In this already our layout is already done. So you can see here there will be almost 20 amplifiers, all the architecture and conceptual drawings already done. And we are in the process of making a detailed project report to be submitted to the department. And we can have the specifications of something like the 50 kilowatt CW and pulse. And then we have 4 megahertz bandwidth. AC to RF efficiency is a bit ambitious at higher power, but we will try with the newer techniques, innovative designs, and latest architectures, we plan to have this kind of efficiency, which will give my accelerator people the more bandwidth in the form of economics as well as power. So this is the kind of. Second is the LEHPA upgradation. As I said earlier, for LEHPA, we have been using clystrons, all the 3 clystrons. These 3 clystrons are imported. So hereafter, we don't want to develop on imported things. So our vision, or in fact, already we have started the progress. We plan to replace all the 3 clystrons with 10 RF systems of almost 400 kilowatt each. In Klystron, we used to generate 1 megawatt power and distribute it among the ports of 2 RF ports for RFQ and 4 RF ports for 10 MeV DTL and 4 RF ports for 20 MeV. So total there are 10 RF ports. So we plan to have now 1:1 amplifier system, and the combiners for this have already been designed by my colleague. And you can have a look for the detailed technical information on in the poster session. Mr. Ramarao is having this poster, and he also has an oral. So you will get more technical details during this presentation. As long as all the amplifiers, which are, whether it is MEHPA or LEHPA upgradation, there are different RF systems like DC power supplies, which is also one of the major contributor. Interlock protection and monitoring systems, as well as individual 1 kilowatt or 2 kilowatt power amplifier modules. All this, there are dedicated posters in the session, in some of the sessions by my colleagues, and you can get a more technical information and detailed technical information in those posters. So we plan to completely replace the Klystrons with this of 400 kilowatt each. So this kind of technology, we have already developed a 64-way cavity combiner. So we will go for more number of 128-way combiner, and we will combine these two. And this way we plan to give for 1 port of LEHPA. So it will be 400 kilowatt each. And since we have already developed number of 7 kilowatt systems, number of 20 kilowatt systems, the technology demo, we are very confident, and technology is matured. With the new things, we will go further for these things. And this will be the plan layout, and you can see here the comparison between solid state amplifier and Klystron. So you can have, we will have per port 300 to 400 kilowatt. AC to RF power efficiency, though Klystron is having 50 to 54%, at the moment we are having a conservative number. We are well aware the issues or the challenges we will face for even achieving 50 plus minus 2%, but we are confident with our new techniques, we will go for that, and eventually we will be able to successfully replace the Klystron with the RF systems. So these are now shifting from solid state amplifiers to the devices. As I said, we don't want to depend on only one kind of things. We want to laterally as well as vertically develop for the RF systems. So we want to do the device development also. And there are some other techniques also which we want to use it. So basically, Klystrons and the IoTs are the alternatives for solid state amplifiers. Use of linearizer circuits, then efficient modulators if we use a Klystron, then high MTBF, low MTTR ensures me the high reliability or high RF availability. Simpler philosophy for IPMS will reduce the MTTR, also MTBF I can believe. With all these improvements, we should be able to do efficiency improvement and with reliability in consideration, and it will have a direct impact on improving the accelerator operation and the cost. So we have started with the IoT. With the academic institute in India, we have already a collaboration, and this is just to show that IoT is a combination, especially RF person are very well aware, it is a combination of vacuum tube and Klystron. So we have already for 325 megahertz, 100 kilowatt RF, for making it RF amplifier, we already have simulated this in collaboration with an academic institute. In fact, the person is doing PhD over this, and this will be a This is already designed. RF design is over. Thermal analysis is over. Now engineering design is almost completed, and we will embark upon the prototype development of these components. Next is a Klystron. So here we want to develop a Klystron of not 1 megawatt capacity. Again, similar to solid state amplifier, we want to go for a vertical mounted 400 kilowatt Klystron. But the difference is this should be again high efficiency. So again, with a collaboration with academic institute, and this program has just started in this calendar year. So not much progress has been done. So this is the Klystron at 352 megahertz, 400 kilowatt peak power at the moment. Eventually we will shift to the CW, and at the moment efficiency we are targeting is 70%, and this will be DC to RF conversion efficiency. Already DC supplies AC to RF conversion efficiency has already increased more than 90%. So we are confident that we will be able to achieve a high efficiency Klystron based RF system with a very high efficiency. And these are very preliminary simulations. As the time passes, we will mature this technology. Similarly, we also have a high efficiency Klystron design. Already BARC RRCAT has collaborated for S-band Klystron for our combined program on electron accelerators, but that program is quite mature now, and slowly it is coming to the maturity, and definitely we'll be able to demonstrate something by next year. But that will be with a regular efficiency of almost 40 to 50%.
Dr. Pandey, please conclude in 2 minutes.
Sure. So another program parallelly has started, and it is for high efficiency, in which we are targeting again more than 75% efficiency for S-band Klystron. And again, this has started in this calendar year. So work has just started. So for the normal S-band Klystron, which is not a high efficiency Klystron, we have already we are indigenously developing. So our RF design of window has already been done. Thermal and RF thermal multipacting analysis has been done. For multipacting analysis, again, one of my team member, Jose Mentis, will be having the poster in one of the session. In development, we are in this stage of this tin coating and cooling arrangement is going on. So slowly we have already reached the development of this, and this is the RF design, and cold model testing probably next 2 months. Within next 2 months, we'll be able to do and thereafter the high power testing. And this is the typical specs of that, and this is the initial thermal analysis with cooling jackets, more including in enhancing the cooling. This temperature has again come down in the thermal analysis. So as I said earlier, we are also exploring cyclotron based ADS. We are aware that at very high energy, high current is a very high challenge, but we don't want, there are other useful applications of high energy cyclotron. So we are also started exploring the option of cyclotron based ADS, and these are just a couple of RF systems. The 2-3 slides hereafter are not our contribution. This is just an exploration and the overview of that. So these are the kind of amplifier systems, and since we already worked in the high end of UHF range of the amplifiers, and working on the high end of HF or lower end of VHF, we will be able to use, we will be definitely embarking upon, but here we want to go for a newer kind of things and not what have been already developed. Now again in cyclotron also you can see here the contribution, this is the data taken from PSI. So the 42% of efficiency, 42% of contribution in the overall budget is from, power budget is from RF, and hence again I will reiterate that the high efficiency and highly reliable RF systems are very important. For cyclotron based system also, this is a typical block diagram. We can, till now, there is a tube based systems are going on for a very high power, 80 kilowatt and 100 kilowatt. We have planned to have either hybrid system up to some chain of amplifiers up to some, and last stage might be an amplifier of 100 kilowatt, or of latest, the GmbH has already developed for their cyclotron the solid state amplifier of 150 kilowatt.
Please conclude your talk.
Yeah, just one slide.
Yeah.
So, and this is in China. They have already, again, feedback compensated integrated RF system. They have already done a 16 MeV cyclotron with 16 kilowatt RF system, which has a both solid state LLRF and all RF feedback based compensation. So this is the typical RF system, new RF system for cyclotron, which we are exploring. We are not developing, we are exploring this. As usual, all the things has to go for a very stringent qualification test, and these are the typical that. So in the conclusion, we have the expertise and capability, so we want to take it into the next level. So we have already developed an indigenous RF systems in the form of solid state in the kilowatt region, then in the form of high efficiency vacuum devices are already the work has started and has reached to certain level, and with the help of all the ACND team within the BARC collaboration with RRCAT, we are very confident that this will definitely end up in a very excellent for our own accelerator program. Thank you.
Thank you, Dr. Pandey, for a very comprehensive coverage of the roadmap of the development of RF systems for future ion accelerators, and also very important topic of the indigenization of the RF devices, imported devices, the steps taken towards indigenization of IoT and Klystron.
Thank you.
Talk is open for questions. We can take only 1 or 2 questions because of the want of time.
I just want to ask 2 questions. One is that this IoT and Klystron, what is the timeline for development of this with?
Yeah, for IoT, our design and engineering design and both RF and thermal design are already complete. And this year we have started the typing of each of the components initially, and then integrated we want to do next year. So this is just a prototyping.
So maybe in 2 years we get IoT.
Hopefully.
Okay. Mukesh Jain, note it. And the second is this Klystron, cyclotron you are exploring, no?
Yes.
So which will be the partner institute for the actual development?
Obviously VECC.
VECC. So you had some interaction with them about this?
We will start now because first our homework should be completed and then only we will approach them.
Dr. Jain?
Madam, you talked about the efficiency. So I presume that the 50% efficiency which was projected for that this cavity combiner, it was wall plug efficiency.
It was?
Wall plug efficiency, not the DC to RF combiner. For the complete system.
It is AC to RF.
AC to RF. So in that system, you are planning with the, this water cooled power supply, DC power supply for biasing the amplifier?
There we are exploring 2 options.
Okay.
One is, yes, water cooled supplies, but then water management of so many supplies. We have to look into that, or we can have a DC-DC bus bar, and then we can have the...
So single supply or single bus bar will be supplying to many of the modules, and not one-to-one, as we have planned for Fermi also.
Yes. So we are exploring that option because in this 400 kilowatt LEPA upgradation especially, the number of modules are very high. So we are exploring both of the options, DC-DC bus bar. And
in line with this IoT and Klystron development, means one couple of years back, I heard that LDMOS development is also going on. Still it is in, or you are also planning for that?
No, not yet.
Thank you.
Mukesh.
This is regarding multi-beam Klystron. So from where are you going to procure a cathode or multi?
Good question. Because in the S-band Klystron, also we are facing the same problem. So as usual, BRC will have a dual approach. One is the indigenous, and Tiwari sir is here. His group only has started the cathode development, material development. And initially we will procure for the cathode, but material development has already started. And a small piece of demonstration will be available within next couple of months.
And regarding this IoT development, I think this paralletic graphite technology is used for fabrication
Paralletic graphite, great.
and machining with lasers. And
Yes.
all those technologies, somebody is working on that?
Yes. Again, same thing. First, we will buy, and then we have already started the electron gun design has already started at the same institute as a separate project. And BRC also has, but it's a triode electron gun.
Yes.
It's not a diode. So we have to first do the proper design, and then we will go forward it.
And in Klystone development, are you planning to use second harmonic cavity for enhancing the efficiency?
Yes.
Or it
It
is
will be multi-cavity.
multi-cavity? No use of second harmonic cavity for.
Second harmonic, yes.
Maybe later it can be.
Maybe you can continue your
Okay, thank you. Thank you.
Because of the lack of time. So let us thank Dr. Manjari Pandey once again. On behalf of the organizers, it is my pleasure to present a moment to Dr. Pandey. Now, in the next half an hour, we have presentations from the industry participants, and each one will get the time for presentation by each industry is 5 minutes. The first is a 10-minute slot in which two industries, representatives from Rudraksha and Rudraksha Technologies and Pico Technologies, they will be presenting. So first, I invite both of them, and first will be by Mrs. Rudraksha Technologies. So 5 minutes.
Good afternoon, all. My name is Akash Bansal. I am the founder of Rudraksha Technologies. So I thank you all the contributors to organize this event, BRNS, ISPA, RRCAT for INPAC 2025. So Rudraksha Technologies is having a 4 vertical. One is the data acquisition system, second is system integration, third is test and measurement, and fourth is product development. So as a founder, I'm having a total experience of 15 years. And currently this year I have done 10 plus projects with different R&D institutes and IITs all over India, like IIT Bombay, IIT Madras, and IIT Kanpur. So we having a pan-India presence right now. And after that, so we have a different kinds of products and services. So we mostly focus on right now is data acquisition systems, some kind of like power supplies, some kind of FPGA modules, some kind of microcontrollers modules, some kind of control systems. So we have the partners with us in our stall, exhibition stall, that is Pico Technology, then Hioki India, then Massibus, AD Equipment Technologies, Fluke, and Rital. So these partners is having a different kinds of equipments and the different kinds of services. So the future roadmap of Rudraksha Technologies in next 1 year is like we have to develop our own indigenous system in Indore, Madhya Pradesh only. And we are looking forward a support of DI people and experts to develop certain incubation center here. And we can develop certain portfolio and a product with the help of you guys. So we are having a build to specs and build to print different kinds of products. So we are also looking forward in the next 1 year, we will develop a facility here in Indore so that we can develop our own PCB with the help of your requirements, custom FPGA boards, design and development. microcontroller programming with FPGA interfacing. So currently we are into the stage to bring people, industry expert to help us to make the indigenous system here in Indore. So in the next 1 year, we will able to perform different kinds of products into the Rudraksha technologies. So apart from that, we are planning as a OEM to the JAM portal soon. So in the JAM portal, we will have our own products, and we can also add your particular requirements, kind, let's say power supplies, some controller system, some kind of FPGA boards onto the JAM portal. Recently, we are also started like local content support for imported products. Let's say if you are importing some kind of test and measurement equipment, and if you wanted to add certain local content, so we have some kind of integration work associated with LabVIEW, MATLAB, Python, or any kind of SCADA solution you wanted to develop it. So we have the solution. If you wanted to explore more about our products and services, we have the stall 1 to 4. And I would like to pass more for the Pico technology. Mr. Hari is here. He will give you the more information about the Pico products. Pico is having a USB-based oscilloscope kind of products. Thank you. Thank you so much. Yeah.
So, good afternoon. I'm Hari Rao, Business Development Manager of Pico Technology in India. So, I'd like to present Pico Technology. So, I'd like to start by introducing Pico Technology. So, Pico Technology isn't just a company. So, it's a 34 years legacy of pushing the possibilities, right? So, we founded in 1991. We are the global leader for PC-based test and measurement with 2 Queen's Award and 4 innovations, right? So I'd like to show you the product family, what we have. So we have the real-time oscilloscope, ideal for debugging and analyzing with bandwidth up to 3 gig. And we have a sampling oscilloscope for fast transient signal up to bandwidth up to 30 gigahertz, right? And we have the data loggers, scalable solution for monitoring temperature, voltage, and current. So in critical systems. So we have the RF products, let's say VNA, agile synthesizer, as well as pulse generators. So why PC-based instrument? So Pico Technology shifts the power to the PC. So because of this particular approach, the size is small, we have the less weight, lower cost, lower power, and more reliable. And like our product can be programmed and integrated to any applications using MATLAB, Python, LabVIEW, C, C++, etc. Right. And coming to our product profile, especially oscilloscopes, or let's say picoscope. So we have a wide range, more than 80+ model. We have the highest performance picoscope real time to 3 gigahertz. So deepest memory of 4 gigasamples per second, so which is industry long right now. And we have the highest resolution oscilloscope starting from 8 to 16 bit. We have 8 channel 12 bit, 8 bit to 12 bit ADC resolutions. And we have 4 differential, which means an isolated channel oscilloscope as well, right? So this is the software which works for picoscope, all the Pico oscilloscopes, real-time oscilloscope. So the special category of picoscope 7 is free software update and lifetime support. So, and it's completely user-friendly, and you can customize according to your need. So we have few, let's say that, few high bandwidth products, but like due to the low time, due to the limited time, so I will just pass the 3 slides. So we have VNA with 8.5 gig and 9000 series with 30 gigahertz, and data logger, you can expand the channel up to 160 channels, right? So finally, I conclude by stating that, like Pico Technology, leading the world in PC-based innovation with the new product version to transform the future. And we are trusted by VSSC, BEL, HAL, ISRO, and leading innovators and researchers like you. So thanks for this opportunity. And For Make in India, we have collaborated with Rudraksha. And for any clarification, please visit our stall from 1 to 4. Right, thank you.
Thank you, Mrs. Rudrash Technologies and Pico Technology. On behalf of the organizers, it is my pleasure to present you Momentum. Now I invite Mrs. Rohde Schwarz, India Private Limited, for their presentation.
Yeah, hello everyone. This is Abhishek here from Rohde Schwarz, India. So I think most of the DAE scientists and customers sitting here know me. I'll just jump in directly to the presentation because we have a little bit less time. Just a brief about Rohde Schwarz. So the two people you see on the screen are Dr. Rohde and Dr. Schwarz, who are actually, I would say, in the college, they were friends, college friends. And from a two-man lab, today we see that we are a 2.4 billion euro company, which is there into RF test and measurement. And you'll be surprised that it is still a family-owned business. So we are not still in the, I would say, in the stock market. So it's a family-owned business founded in 1933. So we are more than 90 years in the world. So just this one. And financially very independent. It's a fully owned company. I'll just move forward. Yeah, so just to give you a brief, I'll just play a small video about Rohde Schwarz. So just enjoy it. Was the video. I hope you liked it. I'll just move forward. Yeah, so also a brief about Rohde Schwarz India. So we are the Indian arm of R&S Germany, and we are present in India for 3 decades now. And we have a very competent team and a very good clientele in India. You can see the pictures with the customers also. We have some collaborations. And we have a very good team of also channel partners which are there. I would like to mention some of the facts about the company, what distinguishes us. The engineers which we have are actually trained in R&S Germany, and few of our R&D colleagues have worked also with R&S Germany for a period of more than sometimes 1 year also. So we are very experienced service and application team who can directly interact with the customer and solve your application issues. So it's not just only the products, but we bring the German technology and the German engineering to your labs as users also. So this is one of the points I wanted to highlight about the company. Moving forward. Yeah, so this is about our locations. So in India, we are present in Delhi, Mumbai, Hyderabad, Bangalore, and our headquarters is Delhi. And we have a full-fledged service and calibration center in Bangalore. I come from the Mumbai office, so this is where I'm located. And there are some places like Chennai, Trivandrum, and Pune, where we don't have a local office, but we have resident engineers who are covering the market there, the customer requirements. And what to say? Now we are also having another subsidiary called as Rohde Schwarz India Systems. So in Rohde Schwarz India Systems, we not only do products, but we will also do like an AT or a system development at a system level for you. It's not about only the boxes, but we can design complete radar ANDs, ADTs, sorry. And also, if you have some customized AT which you want to design, that also we can discuss and also design that. So this is something new what we are offering. Just moving forward. Yeah, so this shows you the calibration and test facility, which is there in Bangalore, which all our equipments across the country, they are centrally brought to Bangalore for repair and calibration, and then they are sent to the respective customer locations. We also do as a first level service, we will do a check on the customer lab, customer location. If it cannot be resolved on the customer site, then we send the equipment to Bangalore. So it is not directly, we always, on the first shot, we send it to Bangalore. We'll first try the on-site service. Then as in second option, we will send it to Bangalore.
Excuse me? Please conclude.
Oh, okay. I think I have to go fast. So I'll just skip it. Coming directly to the products, I think most of the customers here are aware what we do. So we are having signal generators, spectrum analyzers, VNAs, then oscilloscopes. Also, we are having a wide range of 16 gigahertz is the maximum. And then we have power meters and also power supply. I'll just quicken up. So here you can see our signal generators, the various signal generators what we have. Starting from 3 gigahertz, we have even 67 gigahertz in one box solution. There are varied signal generators, and on this one, we have a compact solution. So you don't need a display here. You can directly it's like a LAN, like a LAN switch size signal generator we have. Moving forward, this shows the spectrum analyzer portfolio. So we are having a 90 gigahertz as the maximum, and then you have different vector, analog, and this handheld equipments also, handheld spectrum analyzers, handheld VNAs also we have, which you can see here. Moving forward, this is our vector network analyzers. We have this without screen models also. Multi-port, the ZNBT, you can have multi-port
Please
VNAs also.
because we are running out of time.
Yes, and these are the oscilloscope. I just want to mention that we, from the low 50 megahertz, 60 megahertz, we are going up till 16 gigahertz also. So very good range. And then some power supplies. So this is all what we have. So I thank you for the listening and patient this one with me. Yeah, thanks a lot.
Thank you. Thank you for your presentation. And it's my pleasure to present you a memento on behalf of the organizers. Now I invite representatives from Logic Fruit Technologies Private Limited.
Good afternoon, everyone. I am Sonu Singh. I'm a senior manager at Logic Fruit Technologies. Somehow I couldn't show you the first slide, so I will go right away. So we are a high-performance embedded computing company based out in Gurgaon, and we have a presence in Bangalore as well. It has been more than 15 years in service. We have been serving various customers in defense and aerospace, semiconductor, and research and development for automobile as well. The area of expertise span in various, in embedded computings. We have a deep expertise in FPGA CPU-based systems. We have a deep expertise in high-speed serial protocols such as PCIe Gen 6, CXL, and Ethernet. We have been developing embedded software and accelerator AI systems as well. And we have been a deep expertise in mixed signal processing across radar, wireless, and image processing. Coming to the expertise, we provide complete solution in the real-time processing from the hardware layer to the application layer. We have a complete dedicated team of the FPGA handling the various protocols such as PCIe, DDR4 as well we have handled. We have worked on various ADC and DAC systems across various labs in India. Apart from that, we do have a complete embedded team as well in-house, which has delivered various complex systems and mixed signals systems as well. Coming to the complete, we have been a very FPGA-centric firm from the start itself because the founders are coming from the FPGA background. So what we do is we offer complete architecture understanding of the customers till the RTL development and embedded software as well. Now we have added AI accelerator to it. We have been doing system hardware design as well for the customers and the final integration and testing. We have a dedicated IVNB team as well. We have a various expertise on the DO certification on the aerospace and defense side as well. We have been owning very cutting edge IPs in the defense and aerospace. We have various high-speed protocol IPs, as I mentioned, at PCI Gen 6, CXL, Ethernet. We have Ethernet till 400G. We have been working. We have a complex high signal processing IPs as well, FFT, FES, and modems as well. And we have worked on various mixed signals hardwares as well in past, and have been working on various image processing IPs as well for DRDOs. Our capability has spanned onto various things, but to focusing on this particular event, we will highlight that we have a deep expertise on high data rate acquisition and controls. We have a complete team dedicated for the data acquisition model development. We have our own made in India product for that. We have deep expertise in radar processing units as well. We do have expertise on particle accelerator as well. Now we are expanding that team as well. We have a various high digital speed IP partners and engineers in-house who has, built a complete basket for the IPs for us. Now coming to the new edge technologies which we have been investing, we have been developing various FPGA-based solution on Versal, based on NVIDIA-based edge processing AI modules. We are also building. We are doing a lot of work around AI accelerator on the CXL. We have our own IP for that. We have been working on various SOM modules as well. We have a dedicated development for the Kriya SOMs and HLX as well. Now I will going through some of our products which we have developed in India, which are completely made in India. So this is one of the IFRF signal generator and receiver, which we have developed for defense and aerospace customer in India for the DRDO. This is a single board computer. This is a 6U VPX board, and the similar board we have supplied for Sukhoi 30 platform, which is the airborne qualified, already flying in the aircraft. So we have a complete expertise on that as well. And this is an Indianized version of that. We have developed from the scratch, from the electronics, we have just procured from the outside. Apart from everything we have developed in India, everything application, firmware development, and the drivers as well. We do have a product called HDR, which is a high data rate modem. This we have supplied to ISRO. We were the first company in India to have such a product in competition to Safran, which is a European-based firm. So we have developed this system, which has its own GUI, which provide a complete demodulation and modulation techniques into it. We have a dedicated data acquisition systems as well, as I mentioned that. We have our own made in India product. It can scale up to 1024 channels we have delivered to IPRC, ISRO for engine testing bay application. Now coming to RF data recorders and playback systems also we have.
Excuse me, please.
Yeah, just I'm concluding. Thanks. So yeah. And this is our team. We have been founded by 3 IIT Kanpur batchmates, and in 2009 we started the business, and we have been scaling throughout. And thanks for listening, and thanks a lot.
Thank you. It's my pleasure to present you a memento on behalf of our organization. Now I invite Scientific Mesh Technique Private Limited for their presentation.
Yes. You can use this also if you want.
Okay. Okay. Good afternoon, everybody. Myself, Yogesh Pandey from Scientific Mesh Technique. I welcome all of you on behalf of my company. Okay. So we manufacture and distribute wide range of test and measuring instruments. And our company was started in 1963. We were the first to introduce analog cum digital oscilloscopes in India. Our R&D lab is recognized by Department of Science and Technology from last more than 35 years. We have our own test and calibration lab located at Indore. We have pan-India presence with 6 offices across the country and more than 20 dealers. We have our manufacturing facility and head office at Indore. Our product range include test and measuring instruments, power supplies, EMI/MC test solutions, and electrical test instruments. We also provide customized solutions as per requirements and integrated test solutions also. Our product range includes DSOs, MSOs ranging from 50 megahertz to 1 gigahertz. Arbitrary function generators are ranging from 10 megahertz to 250 megahertz. We have indigenously developed programmable DC power supplies ranging from 200 watt to 25 kilowatt. We have taken technology transfer from RRCAT for bipolar power supplies also. So that also we manufacture and deliver. We have indigenously developed electronic loads also ranging from 175 watt to 100 kilowatt. We represent several global companies for low voltage, high current power supplies or high voltage, low current power supplies like Delta Electronica and Magna Power. We also represent techniques for high voltage power supplies and capacitor charging power supplies. We offer spectrum analyzer cum BNA from 2.1 gigahertz to 7.5 gigahertz. Our VNA range is from 1.3 gigahertz to 44 gigahertz in single box solutions. Using frequency extenders, our VNA range can be extended up to 330 gigahertz. So these are basically USB based VNAs. Then we also offer a full-fledged EMI/MC test solutions for emission and immunity testing. We have indigenously developed LISNs, surge generators, and bus generators. We also offer power analyzers from Newton's 4th UK. Our power analyzer range, frequency range is up to 2 megahertz, and the channels are from a single channel to 6 channels. We also offer impedance analyzers and FRAs up to 130 megahertz. Our customers includes various defense establishments like HL, DRDOs, and many other companies. We regularly supply our products to Department of Atomic Energy, ISRO, various public sector units, research organizations like IITs and universities. Thank you. Thank you for your attention.
Thank you. It's my pleasure to present you a memento. Now I invite Inox India Limited for their presentation.
Good afternoon, everyone. I am Vijay Gehani. I represent Inox India Limited. First of all, thank you, the organizing committee, to give industries the opportunity for presenting the, the capabilities what industries can also do. So Inox India is one of the leading manufacturing company for providing the cryogenic and the vacuum solutions. Coming to this specific, conference, particle accelerators, the cryogenic plays very important role, where especially those accelerators which are aiming to the high energies, which rely on the superconducting magnets and the cavities, which actually such kind of magnets should go into the extreme very low temperature below the helium 4 Kelvin, and also which has to be put in the enclosure which is called cryo module. So we do have the experience where Inox can play the role for providing such kind of solutions. So we are more than 30 years old company and 4 different verticals: industrial gas, LNG, cryoscientific division, and the sustainable industrial packaging. So the industrial gas division is, the mostly covering the different ranges of the cryogens of different pressure and temperatures. So those providing the standard, the storage solution from the lower capacity to the highest capacity. LNG is catering the, business related to the LNG market, where we have supplied the LNG mini terminals to Scotland and the other European areas, where we have built the largest tank up to the 1000 kiloliter, and recently we are developing 1500 kiloliter capacity of the tank. I particularly belong from the scientific, cryo-scientific division, and handling the business from the scientific domain. So these are just numbers. I would rather skip this part because limitation of time and the interest of the crowd. I would jump into where our contribution to the big science project. We are truly the Indian multinational company. Normally foreign companies are coming to India, but being Indian company now, we are going to the global. So we are proud to say that. We are established in Vadodara, Gujarat, and we have also established our plan to Brazil, Europe also. We have extended our facility to Savli and Silvassa along with Kalol, which is nearly 50 kilometers around the around the Baroda. And recently we have the listed company on the Bombay Stock Exchange 1 year back, and revenue, I would say, around more than 1,000 crores company. Market leadership, we are among top 5 globally because of the very niche market in this cryogenic area. And we had a good contribution to the COVID time also. We supplied a lot of tanks to the, and where we have almost 60-70% of areas we have supplied our oxygen tanks. In big science projects, our contribution, one is the very classical ITER organization, France, where the fusion reactor is being built. We have a good collaboration with the ITER India, where we have started in 2008 for making the prototype of cryoline, which is multi-process cryolines. And you can see you can see the cryolines which are running from the cryoplant building to the tokamak feeders. So around we supplied 4 kilometers of cryolines and 6 kilometers of warm lines, and this order which has come 10 years back, and almost 90% installation work has been completed, and our people has been deputed there, and we are really proud to say that we have got a good footprint, and followed by we are getting good amount of orders from directly ITER. These are just a glimpse of picture of installation there. where our quality of NDT testing and everything has reached to the more than 90%, so which were very recognized company in ITER. We are also having other big science project. You can see the first wall box and the jumper connection, which you can see, which is FAIR Institute, the facility for anti-proton and ion research, where they are also making the accelerator. And I think VECC and Bose Institute as the nodal agency as being an in-kind contribution. Cryogenic is not a part, but we secured this order from the Wrocław University, Poland. But this was supplied, 3 such wall boxes has been supplied and installed at FAIR Institute. And we have also secured another contract for 12 such wall boxes, which needs very good amount of expertise in the manufacturing and the design domain. And we have to follow the strict instruction in terms of maintaining the quality of the fabricating such wall box. We have also good contribution in the CERN project, where the LHC project, which is under expansion, and where we have supplied the jumper connections, which was very small, I would say, in terms of number, but it was also the significant contribution for CERN. We have built the wall box for ITER also, which was completely designed, manufactured, tested, installed, and commissioned by Inox India. Also in India, we had associated with ISRO since 3 decades, the second launch pad, all the cryogenic and gas servicing as a turnkey project. This was the first, I would say the largest in the big science project we have received in 1999 or 2000, which was successfully supplied. And you can see the launches which are happening currently, which was done by, supplied by Inox India. And the hydrogen tank we have developed for SHAR, some coolers also we developed. We have also supplied the acoustic test facility, the 6.5 meter thermovec chamber to Komnavec in SAC, another pressure vessels, high pressure tanks. This is very close to our heart with as closely collaborated with RRCAT, and we have supplied the horizontal test stand thanks to the RRCAT colleagues, where we have built 2 such the vessels HTS. One is currently under transit to Fermilab, which maybe the RRCAT colleague will be presenting today. And that's why we would say that this relation is not like customer vendor, but it's merely, majorly like collaborative partners, I would say, for big science projects. Similarly, the first
presentation.
Just sir, 3 more slides. I will be fast. This is the first indigenous MRI magnet cryostat, which was built along with the IUSC, Inter-University Accelerator Center, which has been currently under testing. And persistent mode has been achieved with 1.5 Tesla. Magnet was not indigenously made, it was imported, but we are shown our interest for the making the magnet also indigenously. And as a consortium partner, we'll be looking forward to manufacture it. This is one last 2 slides I will cover. For this, as ITER project, these are the thermal shields which have gone under the repairing phase. And we have shown our interest for, the repairing these thermal shields. It was supplied by Korea earlier. And we're proud that we have almost 4 sectors have been repaired, 3 are under repairing. And this is just a process flow where the criticality was very much, where tolerances has to be maintained, machining has to be done where large machining bed to be required, polishing. And you can see the last picture where the first sector has been recently installed in the tokamak pit, probably a couple of months back. So thank you so much, and visit our booth number 22 for discussing more about it. Thank you.
Thank you. My pleasure to present you a memento. So this ends the industry presentations during this technical session. And now we come back to the talk. So the next talk is by Dr. Gautam Sinha. He will be speaking on the development of undulators and solenoids for accelerator-based light sources. And his brief biodata is here. He is MSc Physics, PhD from IIT Kanpur, PDH from TIFR Cardiff University. His areas of research work include design and characterization of magnets for particle accelerators, PM-based undulators, and magnets for MRI applications and dynamics of charged particles. He has more than 65 publications in conferences and journals. So you have total 20 minutes. I will give you an alert at 17 minutes.
Yeah, thank you, Chairman, for your nice introductions. I will also like to thank the organizer for giving me opportunity to share the work that we have been doing. I'll be presenting the work on behalf of Accelerator Magnetic Technology Divisions. And just first, we have talk about something called undulator and solenoids. We'll justify what basically we're doing. We'll start asking questions, what I actually mean by first slides and gone. So let's see where it is. Anyway, first slide's not been displayed here. Let me explain what is undulator. Undulator is a kind of periodic array of magnets. If you are to do a single magnets, how do we really look into the radiation that coming into this magnets? First, we have a collections of a magnet where we have to place so that our magnetic field varies as we move along the line, electron line vertically down. If you go into vertically down, then electron passes through that in horizontal directions. As it passes to the horizontal direction, it will provide radiations, and the factor called the radiation that's coming from electron is paid out with an angle called 1 by gamma. Its gamma is depend on the energy of this. Now, if the electron oscillations are smaller within the radiation domain, the radiation emitted by all electron will actually interfere, and they give you a intensity, very bright intensity. It's brighter compared to Indus 2. You say that the intensity that we get from dipole is around, it will be enhanced by 1000 times. And if you look into why do we need the insertion devices, because it will enhance the brilliance and the same time will give you the energy extension for that. If you take an example of Indus 2, it will critical energy maybe 6.5 keV. If you want say 10 EV energy, then for that reasons we need to have undulators so that we can expand our energy on that part. Now, one critical part we talk about undulator is its parameter K. K parameter is actually the product of undulator period. Undulator period means when you see the magnetic field is going into sine or cosine curve, that determine the kind of period. So this K value, a textbook is written K is equal to less than 1 is undulator and K is greater than 1 is wiggler. Let me clarify that point. Most of the practical undulator K value is 1, 2, 3, 4. It's not really less than 1. Less than 1 is the undulator. The property that you just do into that, the moment it start, if K is less than 1, then it will give me on pure fundamental output on that. There's no higher harmonics. As you gradually increase the K, you will getting harmonics on that. As the harmonics is increases, then it will smeared into a just simple one single band that will go into the wiggler. So the transition from wiggler to undulator to wiggler is not very sharp. It's a gradual transition from that. This is one of the field pattern as we're talking about. It's actually varying as a oscillations like this. We have to critically design this field so that we have to control. How do we control? We'll show. This will cause an antisymmetric. Here the field is slightly up and down, then here slightly down and up. That helps us to control the trajectory of the particle, which we actually wanted to control. We'll giving the output radiations on that. And undulator behaves such a way that electron comes into that, say it's a 0 position, it will do all this oscillation while going, it will be passing, almost nothing has done to that. And that we each and every turn will get radiation, they will smeared off, and we'd like to get the enhance of this magnetic field, which goes as number of period square theoretically. Now, how do we build it up is the questions now. This is the basic need of this. So undulator that we have developed at RRCAT is, this is the particular picture here is have a, this is we call a guider, and on the top of the grader, we have a BESS because we need to develop something which is scalable. Very quickly, we can make large numbers of undulators because in our present and future projects, we need this kind of devices where we'll be able to scalable. Here we make a base plate. On the base plate, we put the arrays of magnet. I'll go slightly detail on that, how to do into that. Now we can divide it, the total undulator in 3 parts. One is the mechanical structure, maybe girder, another thing. There will be strength, enough strength so that it don't deflect. We have a magnetic assembly, and then is a control section. So we will slowly look into that one by one. So here in the particular cases, we have used around 400 to 500 small magnet blocks. We put into that. The structure is standardized for 2.5 meter length. As we put the magnet on one by one, we'll be able to generate a magnetic field. Now, this is the measured magnetic field. We have reduced the pole gap to 12 mm, and the magnetic field pattern, what you see is that this is the measured field, which is very close to the kind of predicted magnetic field. We'll go into the complex detail into that. As the magnetic row, you will see into that, this is the red color was the magnet. I have put some dots here. The dot represents something called correction. It's called magic finger. We'll come in details what is this. Rest of the magnet is basically one by one magnet is placed. Placement of the magnet plays a very significant role in this. Now, each and every magnet is been designed such a way that I have some freedom range, maybe at 100 to 200 micron. That's play a significant role, how to manage the magnetic field profile properly so that it will produce the kind of radiation that you want. Apart from that, any accelerator magnet, what I need is the entry and exit plays a very significant role. In the middle of the magnet, I have a north-south pole equivalent magnet one. But at the beginning, we'll say the yellow color is a magnet. Their sizes are different, and there is a gap between this. So what I saw in the earlier graph, that how do we create this anti-symmetric kind of magnetic field, this small part, so that I have a typical sine wave field. So this end block actually played a significant role to do that. So now we move into that undulator control systems. And here we have 4 motors. This undulator will be operated by the users. They are not supposed to know but complexities in between. Therefore, it will be user safe and very simple fashion. There's some instruction given. So all the safety features will be inbuilt. What we basically do into that is we have 4 motors. They are synchronized. When the motor moves, this is the magnet array. When the motor moves, it's have a absolute encoder 4 different places, and there is a tilt meter. So allow that there should be no relative tilt between them. This amount of relative tilt around 10 to 20 micron, that's play a significant roles. And then we change the safety features that we have at least certain redundant thing. For example, the alignment, we have absolute encoder. On the top of that, we have a tilt meter. Similarly, if somebody try to increase the gap of this beyond 11, there will be something called limit switch that will give you a software warning. You just cannot cross this. But still, if you cross, there is something kill switch that will make the motor outside the power, so the motor cannot move. Even it fails, there is a hard stop. So there are several things that we incorporated and built into that undulator. And we have 2 dedicated PLC on that. One is for the motion. Rest of the things we have to make sure that whether they are in a proper way and then they move forward. This has been now developed. Now we see that what is the technology go ahead and what are the challenge involved. If you look into 4th generation's light source, we have a defined state section. Now the idea is that we need to put large number of period. Large number of period will give me the brilliance, which goes as n square. And if you want to put a large number of period, length of each period will be smaller. The moment we reduce the period length, magnetic field will be lower. So the requirement is contradictory. We need to have a high B and a smaller period. Now, how do you look into this? Before the last century, people used to started working on electromagnet, but because of the compactness on this smaller period and higher B, electromagnet needs a current density of around 200 ampere per millimeters to match with permanent magnet. Therefore, that has been phased out. Now, the permanent magnet undulator has been operated, most of them. Now suppose the permanent magnetic field will depend on the magnetic property, pole gap and the block size. I will make it the smaller one, block size limited. So my magnetic field that we produce is limited. Now what do you want to increase the magnetic field? What we do is that we reduce the pole gap and exponentially magnetic field will increase. Whenever we have make a permanent magnet undulator, there is a vacuum chamber sitting in between. If you remove the vacuum chamber, and we will be able to reduce the gap from 10 to 12 mm to 6 mm period length, and then it will increase the magnetic field further. But if you are not happy with this, we have to dip all the thing into the cryogenic where the BR will increase and we will get highest possible magnetic field, and that's we are looking for. Now this is come to the bottleneck. Now if you increase even further magnetic field, there is no way the permanent magnet existing technology can give us. Therefore, now the community has shifted to superconducting magnet. In all performance, if you look into the gap, this is say the period length is 16. Permanent magnet will give you a field around 0.5 Tesla. If you dip into this, we'll get a magnetic field of around 1 Tesla, but superconducting magnets always lying ahead. So the performance wise, tunability, superconducting magnet will be able to perform better than this, but at the cost of cryogenic and other complicated technologies. Now where do RRCAT stand for? We have developed two such magnet and we are reasonably comfortable. We have characterized up to 12 mm. To make it vacuum, we have to go to 6, 7 or 5 mm. That we'll be able to do, and we have to put the vacuum chamber in it. That also within our reach, we have been working on that. Cryogenic undulator, we have to start working. Superconducting undulator assays, if you want it to be internationally competent, we must work on this. We have already working on two devices, which is called superconducting undulator and wavelength shifter. The technology we learn from that will help us. That is the beginning to start superconducting undulator. I'll just slowly move into some of the, now people may have doubt whether this technology is matured or not. If you look into that, all that FEL that been proposed like XFEL, SINE or LCLS, they have all sanctioned. They have been working on superconducting undulator. So all that XFEL will use undulator on that part. There are certain advantage I have written here, which will be available in the literature. But let's now look into that. There is another undulator that we make, we characterize, and that is a beam property as we expected. This is within the expected line. Now, any magnet that we make, it may not be the correct one. There will be some errors, but we cannot predict the error at the beginning. Therefore, we must be ready with the correction schemes. There is standard correction scheme. We can put a correction coil and send a current to do. There is something else we'll do, we call magic finger. We have shown the red dots that. Now we clarify these things. This is kind of one particular magnet block that we have taken. Rather than putting magnet, this is an aluminum chamber. We put some smaller magnets. Here I have assumed 9 magnets because you can use as many as you want. One small 3 mm cylindrical magnet and 8 mm diameter. The advantage here is the mechanical assembly. We can place them whether any one of the 9 top and bottom, or we can change the position in there. Why do we do that? Let's see an experimental data. We have a complete paper on that. We'll talk on later. Suppose I have made an undulator where the magnetic field B dot dl seems to be within 50 Gauss centimeter. Now we have a value which is around 200 Gauss centimeter. What to do with that? We can have this at the entry and exit and create a magnetic field which is just opposite directions. So that resultant field coming into plus minus 20 Gauss centimeter, which is the reasonably good limit. So this is the passive correction scheme. This is an correction coil, this is active. As we change the gap, we have to change the current and do. So this correction scheme plays a significant role in reducing the field error if arises after fabrication of the superconducting undulators. Now, just give you a summary of that. If you want to do that, we have to choose the magnetic blocks. Magnetic blocks means these are magnetizations. There is something called north-south similarity. Now, if you take a block, you measure magnetic field slightly top and slightly bottom, and you say that you must get this similar magnetic field, and there is a dimension of that. Now, strategy to statistically arrange magnet placement to achieve desired goals. That plays a significant role because each typical undulator have 1000 magnets. Any trial and error one do. Therefore, we have developed a code which plays with simulated annealing that helps us to achieve this. Hole gap tolerances with 20 micrometer, the control has to play a very significant role, particularly as we change the gap, magnetic force increases exponentially. Therefore, the control system must be able to do that. We are able to experimentally verify it is doing. Keep the deformation of the magnetic because of magnetic force 10 micrometer. That is this structural analysis has to be done with the part. Implementation of stable feature for physics and motion and safety. This has been implemented. Evolve protocol to control field tolerances. We have showed that the two schemes that we have evolved and tested, one is correction coil as a magic finger, and the field measurement system. We have both the systems ready with us, so we can go out for this undulator development. A system based on experience, we have reasonably confident to do it, go into this. Now I will move into my next topics is called solenoid magnets. It's been used in various places, but before we go into that, making any magnet is important to understand the basic theory and how do I characterize the magnet along with the fabrication part. Now, this solenoids, any magnet that we make is depends on the kind of use that I am doing. Solenoids are used largely in accelerator. It can be used in electron microscope and MRI. We have seen something here. Now let me say how it is look into that. This is the accelerator. In RRCAT, we have large number of solenoid plates. This is the beam dynamical property. I'll come later into that. Let me just define how it is different from accelerator and MRI magnet. If you have a MRI magnet, then you need to have a generated magnetic field at the center. I don't care what is happening to the edge. If you go to the hospital, the patient is pushed into the inside because only resonance will take place in the colorful graph where the field uniformity is 10 ppm. We have to achieve this. More details will be available to our paper which I have already published. About the beam dynamical part, as you see, the interesting part starts when you enter into the solenoid itself. Just you enter, this is a kind of elliptical beam and the path between that is spiral in nature. And it starts doing focusing when you just enter into the solenoid. Middle of the magnetic field is important, but edge is also important. So therefore, as per the applications of the uses of it, you have to design accordingly. We have to develop our own understanding of the particular subjects. Due to lack of science, I am not going into the theoretical part of it, but we have already published this in Nature 2024, this work. For details, we may discuss on that. But here, as we have talked about the motion, you see the magnetic field here axial, and my electron also moving in axial direction. So the force acting on that is basically zero. What basically happens is that when we move.
Dr. Sinha, you have 2 minutes.
2 minutes, okay. So now I'm just going into the characterization part. We have developed this solenoid and we just put a indirect cooling on that. I put a jacket here so that we can change the jacket. Solenoid have two parts. One is the property, is called spherical aberration coefficients, and then focusing length. Theoretically, we need minimum CS, so have a better focusing. But if you reduce the CS, we can increase the focusing length, the focusing power reduce. Therefore, there will be a trade-off between that to do. So, as a designer part, we must know how to tune that. Even the magnet is made, I just take it out and make a small changes on R here. We can tune that as per the need we can provide. Cooling played a very significant role. So, we have tried to put additional cooling here, and this kind of simulation help us to do. Now, it's a characterizations that plays a very significant role. In accelerator, when you put a magnet, people say the position of the magnet is X. How do I know the center of the magnet? My magnet, this is some kind of mechanical structure, coil is inside. But whenever we move the magnetic field, we take a derivative of axial field, it will, the center, it will pass to zero. So if I have a reference here and I know where is my magnetic field crossing to the zero derivative of dB by ZZ, I say this is my center and pass on this. And one more important thing in any solenoids, ideal, if you are passing to the axis of the solenoid, you have to identify it with the three-dimensional sensor. Axial field is here, say 2000 Gauss. But if your axis is not properly made, then we are supposed to get off-axis field, that the blue and green color we are giving this thing as we are out from axis. But the actual axis is that this is all the field data. If you are able to find out the actual axis, the magnetic field will be as small as possible. Here it is 1 Gauss. This is the limit of our measurement sensor. So this is a well-defined magnets. that give us field. Now we are just going into the technological part. Due to the lack of time, I am not going into the details. Earlier, we used to make magnets using OFFC copper, which is imported. Now it's possible to using in aluminum strip is available there. It is cooled down by ordinary water, no need of LCW. Relative cost is cheaper. Power loss is less. Power loss is less because my current density is less here. We don't need interturn. It is an inbuilt aluminum oxide coating. We need interturn. Fabrication is faster. Only disadvantage is the compact, and this is the relatively large one. And last, an important part is this acknowledgement. I acknowledge all the members of AMTD. This is a very special tribute to our beloved colleagues, Sri K. Selamlo, and we acknowledge his contribution to the all projects. Thank you very much.
Thank you, Dr. Sinha, for presenting very important technology development of undulators, which are very important for our future industry project, as well as solenoids and magnetic characterization facilities. Now the talk is open for few questions. Yeah, Dr. Pant has a question.
Source of magnets. Conducting undulators you are not planning now.
Not yes, but we have started working, but immediate need we will go for.
What is the philosophy that you would like to adopt? Permanent magnet or?
No, as I say that SBRS is done on 10 years project. So in the first phase, we'll go for permanent magnet.
But there the source of the magnets or the?
Source of the magnet, as I says, we have been looking for international source. We have several connections. For example, the source being delivered to various other accelerator centers. We have colleagues there. Through them, we have already received magnets that will build it up. Initially, we are relying on them, and DAE or BRC is having another channel to develop permanent magnet. If we are able to get from that, is fine. But we have a parallel channel open. We'll get it from international sources.
Should a project be based on some development activity which is just starting now?
Development activity on what? Material or undulator?
On the material.
Material, I think BRC has already taken, and BRC group director was there. We have talked to him. He's not here. He has agreed to work on some of the material, but we mostly work on NDFEB. They are working on samarium cobalt. Let's see what is happening. But I think as the project has started, and through our director, we have already approached them.
Sir,
yes, please.
Sir, very nice talk, very informative. I have a doubt कि आपने लास्ट में बोला सोलिनॉइड फैब्रिकेशन वाले जो मैग्नेट होंगे जो एल्यूमिनियम बेस्ड होंगे उसमें LCW की जगह नॉर्मल वाटर चलेगा वो सर मेरे को क्लियरिटी समझ में नहीं आया कि व्हाई it won't require LCW in that case because the objective behind using LCW is the current isolation.
Let me make you very clear here with my here we have there is no current flowing in the cooling. This is a jacket here. This is indirect cooling. Current is flowing, current conductor is not carrying LCW. This is a separate cooling system and we have to put it outside, it will cool. So current is not passing through that, only water. That is the advantage, that's why we separated it and then this will help us to do.
So if there are no more, is there any question? Okay. So since there are no more questions, let us thank once again to Dr. Sinha for a very talk. Present a moment with Dr. Sinha.
I thank Shri Puntampekarji sir for chairing this session and conducting smoothly this multi-flavored session. Now I invite outstanding scientist Shri Govind Parchani ji for presenting a memento to our chairman of this session, Shri Puntampekarji.
I have an important announcement. We have arranged for all the participants who will be interested in visiting Indus facility. At 7 o'clock in the morning from guest house RRCAT, a bus will be leaving. All the participants may register at the registration desk and find out the details from there. We will reassemble at 2:15 sharp in the respective parallel halls. And I also request that please discuss with the registration desk the details of the modalities, how you will be allowed to go inside the RRCAT campus for visiting in this facility. Thank you, sir.
Hello, 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 hello. Are you?
Hello.
Yes.
have been online. Hello. Hello. हेलो हेलो आ रहा है ये सिस्टम में इससे आ रही है कि हेलो 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 चेक हेलो 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 अब उसको बंद करने का क्या फायदा 25 बार अगर चीज छेड़ोगे तो चेक बहुत धीमे है ना तेज करेंगे तभी तो चेक 50 यस या चलेगा
They are requested to please load their presentation. Any participant who is having presentation in parallel session 5.1 and has not uploaded their presentation are requested to please come and upload the presentation. सभी को नमस्कार। अभी हम लोग पैरेलल सेशन 5.1 स्टार्ट करने के लिए हैं। देखिए, RRCAT is known for two of its major programs. Although there are many programs, we know, but the important one are laser and accelerators. And one thing which combines both of these is basically free electron laser, which requires accelerators as well as lasers. And we all know in India, for the first time, the free electron laser, which was built, and the person behind them is Dr. K.K. Pant. And I request K.K. Pant, sir, to chair this session. Sir. So in this session, we are having 4 talks.
Thank you, Rishipal ji. So we have 4 presentations of 15 minutes each. So the first speaker is Mr. Dr. H.M. Kevlani. He will talk on experimental study of proton beam emittance in multi-species beam for MEHIPA. So I will ring up after 13 minutes. And please wind up in 2 minutes so that we have time for a question or two. So Mr. Kevlani.
Okay. May I start, sir? Good afternoon, everybody. I am Hitesh Kevlani from Ion Accelerator Development Division. On behalf of our team, I am presenting my talk on experimental investigation of proton beam emittance in multi-species beam. So our outline of the talk will be, I will give brief introduction for the ion source, Ellison scanner beam emittance measurement, followed by emittance characterization in the ion source just after the ion source and after the focusing solenoid. Further, I'll discuss about the space charge compensation with the help of nitrogen gas and in different experimental conditions like focusing solenoid and microwave power, and I'd conclude the talk. Starting with the ECR ion source, we have successfully completed the LEHIPA project. In MEHIPA, we have 2 ion source. One is a 3-electrode ion source, one is a 5-electrode ion source. This one is a 3-electrode ion source. It is a 2.45 gigahertz magneton base. Power level is 500 watt to 1.4 kilowatt. We are operating power, and it is a SS plasma chamber, 3-electrode geometry. First is a plasma, second is a suppressor, third is a ground. Magnetic field is tunable. It is 800 to 1000 Gauss. Base operating pressure is 3 into 10 to the power minus 7 millibar. Gas flow in the range of 2 to 4 SECM. Key parameter of the ion source: operating range 30 to 50 kV, beam current 10 to 20 milliampere, operating pressure with hydrogen gas 5 into 10 to the power minus 6 to 2 into 10 to the power minus 5. Required beam emittance less than 0.35 milliliter. RMS normalized. Operation mode CW and pulse. And these are the key requirements: reliable, repeatable, and stable operation, because every time we accelerate the beam, it requires stable beam. So starting with the beam emittance characterization. So this is the first setup in which we are measuring the emittance just after the ion source. So this is the ion source, this is the extractor geometry, plasma chamber, this is the vacuum chamber, this is the beam current to monitor stable beam is there, and this is the beam emittance diagnostics chamber, which is Ellison scanner. This is the photograph of the system. Electromagnet coil, microwave link, plasma chamber inside there. This is the extraction geometry. This is the vacuum chamber. This one is the DC-CT, and this is the Ellison scanner in X and Y direction. Base vacuum of the system is 5 into 10 to the power minus 5 millibar, and we have operated the condition the plasma and beam for stable operation before we start the experiments. So this is a Ellison scanner. It has the 2 slits. First is here. These are the electrostatic deflector plates, and these are the second slit followed by Faraday curve. We are scanning this mechanism to X and Y direction and applying the voltage sheet to measure divergence at every position of the beam. These are the key parameters of the Ellison scanner. So this is the beam on which we are measuring the characterizing the emittance and proton fraction. This is the forward power. This is the reflected power. As you can see, we are at after trigger, the forward reflected power getting and reducing and stabilize to the stable value. This is a beam current and this is a trigger pulse. This is a pulse operation on the ion source. So as we measure the emittance after the ion source, we have measured on two conditions at 30 kV and 50 kV. As we are both interested in at LEHIPA, we are a 50 kV beam RFQ, and at MEHIPA we are designing for 30 kV input energy. So at 30 kV we are getting the beam emittance in YY prime for a current range of 10 to 20, 90 milliampere, maximum 90 milliampere, and optimized beam emittance is 0.275 millirad, while as 50 kV which is we are getting higher in the range of 0.45 millirad. So these are the tunable data and we have measured after the ion source. Now this is the problem statement for my talk. So we have measured this emittance. So my question is this the emittance of ion proton beam? So we are measuring the emittance after ion source and we are claiming that this is the ion source emittance, but it is not the emittance of a proton beam. It is a combined emittance of a multi-species beam. And what are the species available in the beam? We can measure with the help of two methods. One is a bending magnet, one is a wind filter. So first we measure what are the species available in the beam. So first we have measured with the help of bending magnet. So we have put a ion source followed by focusing solenoid, drift space, TRR magnet, DCCT, and we bend the magnet and we can go up to 3 kilogauss with the help of this bending magnet. So when we sweep the magnet, we are getting three species, H plus, H2 plus and H3 plus, and percentage are mentioned 60%, 33%, 70%, 7%. These are tunable according to operating condition. We can tune the parameter of H plus, H2 plus, H3 plus. Now in this scan, we are not getting H2O fraction because when we are feeding the hydrogen in the plasma chamber, we are generating hydrogen with the help of hydrogen generator, or we are getting the cylinder. So some content of H2O plus are also there, which we are not getting because it requires above 4000 Gauss magnetic field. So we have done the second method, wind filter. What we have done, we have put a wind filter after the ion source. Wind filter is a E-cross filter. Electric and magnetic field are applied in opposite direction, and we are putting one field fixed, like magnetic field we are keeping fixed 850 Gauss, and we are sweeping the electric plate voltage. So what happened? Bending, all the species are bended, and correction for opposite force is applied in the form of electric field. So we get so in wind filter we have one slit. These are electric plate and magnetic field perpendicular, and we are getting second slit and Faraday cup. So as we increase the plate voltage, we will get all the species information. So we are getting information of H2O, H3, H2 and H plus. So we are getting 4 species, and this one small is a H2O2. It is a higher mass ion, but its percentage is very less. So these are the species available in the beam. So as we got the result that emittance after the ion source is 0.27 for 30 kV beam and 0.4 for a 50 kV beam, but it is the emittance of a combined multi-species beam, combined emittance. So to measure the emittance of a specifically H plus beam, what we have done, we have filtered the H plus beam emittance species with the help of focusing solenoid. So what we have done, we have put a focusing solenoid. We have put two diagnostic, one is SCCT and one is DCCT, and follow one TRR magnet, and we put one Ellison scanner at the end. So what the play is there, when we are focusing the beam, all the species are focused in different manner. Low mass species will focus more and higher mass species will focus less. So with this, if we put a solenoid at 1000 Gauss for 30 kV beam and take the emittance scan, so we'll get this kind of emittance beam space ellipse, which contains H plus, H2 plus, H3 plus and H2O plus. 4 ellipses are present in our beam when we are focusing the beam. Now we are interested in this portion of the beam which is used to accelerate in the beam. So if we filter out and measure this portion, this will give actual beam emittance. We can measure this emittance by bending also, but I have to observe what are the effect is going on other species to measure, to see that we have done after the solenoid. So if we increase the solenoid magnet, so now this is a 1000 Gauss. So this is H plus and H2 plus is nearly focusing. As we increase the focusing solenoid to 1100 Gauss, H2 plus also started the focusing, and H plus become nearly focused at the point, and for 1200 got H plus again started defocusing, and H2 plus comes in a focus diverging means focusing area. So you can see the H2 plus is just entered in the second and fourth quadrant. So in this case, if now this is the emittance we have achieved. Now to increase the fraction of H plus, we have measured the emittance after the focusing solenoid. If we change the plasma conditions, like in plasma we are generating H plus, H2 plus, H3 plus, these are generated with the help of electron. Now electron has its cross section with neutral and H2 plus atom, H plus atom and molecular ion. To increase the fraction, we have put an aluminum boron nitrate plate in the plasma chamber. So with older boron nitrate and alumina, its efficiency of generating secondary electron are reduced. So we have replaced with the fresh one, and we have again taken the scan. So you can see that in space this ellipse, which is H plus and H2 plus, the concentration of particle in phase space H plus is become dominant. So we can feel the how this insertion of alumina and boron nitrate improve the beam emittance H plus, and also in the phase space how it is representing. So we measured the emittance for a 30 kV beam in this experiment. So this is the combined beam emittance plot, and this is the filtered H plus. We remove all the H2 plus component, and we measured this with the, and it is come in the range of 0.12 pi mm milliliter RMS normalized. So to measure this emittance, there are two methods. One, we can remove this and plot this. Another is that we can fit this portion H plus with Gaussian sigma and mu, and which we also plot this, and we subtract two ellipses with each other and plot this. Both the method we have done. So we, in the range of 0.12 we are getting the emittance. Second, for 50 kV beam, we again do the emittance measurement. So in this case, we got the emittance in the range of 0.2 pi mm millirad, 0.21 pi mm millirad. So for the conclusion of this experiment is, when we designed the ion source, it was for 50 kV 0.2 pi mm millirad RMS normalized. While measuring after the ion source, we are getting 0.4. But when we filter out the other species and measure, so it will come in the range of 0.4. So we can measure see this. This is a 30 kV beam, and emittance after the just after the answer was 0.27. While it is at the, when we filter out the H plus, it comes in a 0.12. Where in the case of 50 kV, it was 0.4 after the ion source and combined emittance, and at the end when we filter out, it comes in the range of 0.21 pi mm RMS normalized, which matches our design parameter of 50 kV. This simulation was carried out by Dr. Pradeep Roychody, and design was the answers were done by them. So which matches with our design parameter. Secondly, we have done some experiment regarding space charge on the beam. So in this phase, we have extracted the beam and we have inserted the nitrogen gas. So when we, this is the zero flow of nitrogen. So you can see this is the at 1200 Gauss. This is the H plus and H2 plus beam emittance. So this is the particle of the, this is more normally in this range. When we increase the gas flow from 1 SCCM, 2 SCCM, 3 SCCM. If you observe that the higher tail particle of the Gaussian are removed, and mean sigma of the Gaussian, that high energy was filter out, and mean portion of the beam are set, and H plus ion concentration in the beam is increasing, which is you can see the more red portion in the beam. So if you measure this emittance and plot this with the help of gas flow, so this is nitrogen gas flow, and this is the beam emittance. So if these are 0 SCCM, if we increase the gas flow at 2.5 SCCM of gas flow, we have observed the space charge compensation effect has been showing on, and emittance reach in the range of 0.12 to 0.12 to 0.12 pi mm millirad RMS normalized. Now what processes are going on? Actually, space charge forces of combined beam is going on, which are H plus, H2 plus, H3 plus and H2O plus. Now when we are introducing nitrogen, nitrogen gas interact with all the species, and after 2.5 SCCM, H plus emittance become dominated, and the emittance of the H plus improves, and the higher tail part of the beam will are lost and beam current reduces, which is observation from this experiment. Same way we have carried out with the help of experiment we can with by varying the micro power. So our design power we are getting higher current at 1100 watts. So as we increase the power from 500 watt to 1100 watts, you can see the spaces will become more dominant. And if we plot for two cases, 0 SCCM and 2.5 SCCM, this is a plot of beam emittance with micro power. So as increase the power, we are getting the higher current and beam emittance also improves. So I will summarize my talk. So ion source has been characterized in terms of beam emittance and proton section. Beam emittance has been characterized. Combined beam emittance contain 4 species: H+, H2+, H3+, and H2O+. Filtered emittance is contain H+ beam emittance, which is in the range of 0.275 mm for combined. 0.12 is a filtered, which is matching with the design parameter. Also, the space charge compensation experiment has been carried out with N2 gas for 0 to 4 SCCM, and we are getting better space charge compensation at 2.5 SCCM. Thank you.
Thank you, Mr. Devlani, for finishing well in time. I think we can have a few questions. Yes.
Yes, sir. Thank you, sir.
Please use the mic so that everybody can hear you.
Yeah, what I was saying that it was a very nice talk. I have a small query that when you were measuring the emittance, multi-species and the single species, in case of a 30 keV and 50 keV beam, 30 keV is having a 12 milliampere current and the 50 keV is having 8 milliampere.
Sir, I have the...
But inherently, it is within your design limit. Inherently, the emittance is increasing with increasing keV. What could be the reason for that?
Emittance will?
Emittance is increasing when you are moving 30 kV to 50 kV. 30 kV was 0.12 and 50 kV was 0.21. So emittance is increasing with keV. So what could be the reason?
Emittance was, this ion source was designed for 50 kV for LEHIPA application. So the required parameter was 0.25 mm RMS normalized. So this source was made for 50 kV application, and we have same source available for our R&D experiment at Venn graph. When we got the requirement for 30 kV, we have started the experiment, and we observed that we have also done the simulation and experiment. We are getting lesser emittance at 30 kV. So this is the reason for that.
That was my question. That what could be the physics behind it?
So it's optics of the beam, that first two electrode, and density of the electron. If you see the this Child-Langmuir law with and we simulation of this 3 electrode and plasma meniscus, this density is better, giving the electric field generated by this 3 electrode geometry for 30 kV is more converging for this. That is the reason. Yes, sir.
It was nice presentation, Kevlani.
Thank you, sir.
Actually, I have 2 questions. One is information. What is the scan time for 1 dimension emittance measurement?
So with 0.5 mm step size, our repetition rate is 2 Hertz. Okay, and so we are taking 100 mm step size. To 100 mm into 0.5 is 200 m, and our step size is 2 Hertz, na? So 100 seconds.
So for 100 seconds, you are saying that your beam is stable for.
So we are doing that before starting the experiment. What we are doing before taking the scan, we run for the system for the around 3 to 5 days continuously. And when we are planning the experiment, we'll take in a single shot all the experiment. And first of all, we repeat the experiment daily. When you are getting the repeatability, after that we are starting the experiment.
Okay. Another thing that you have shown the emittance picture images, it is showing unsymmetric.
For 50 kV, na?
For 50 kV.
It is because after the focusing solenoid, because of that.
Okay. Focusing solenoids couples the emittance in the 2 planes.
Yes.
Is it the reason?
Because of little bit of alignment also, and because there are shear also alignment. So there are magnetic components are adding, and effect of each component, and because of non-linearity and magnetic fields, because of that some reason is there. So that may be that.
Okay.
One question is from back.
Hello. One last question.
Thank you for the nice presentation. One more thing is whether the different species present in the beam, have different focusing.
Yes, yes, yes.
So that with energy that spread maybe that because of that or for the H plus only.
So at as I have seen.
Yeah.
So if you see this, so this one is 50. So this one is 30 kV beam. This is H2 plus. 1000 Gauss, 1100, 1200. If I apply for 1400 Gauss, it will be focusing point for H2 plus, which I have done, but we are interested in H plus, so that I have shown the for that.
What is about that the bluish tail, the another one?
What?
What that another line bluish?
This is H2 plus beam emittance.
Okay.
If you see, there are 4 species: H plus, H2 plus, H3 plus, and H2 plus. There are 4 ellipses are there.
Okay. I think we can have more detailed discussions during
Thank
tea.
you.
So we thank Mr. Kevlani for finishing well in time.
Thank you, sir.
And on behalf of the organizing committee, we present a memento to Mr. Kevlani.
Thank you.
The next presentation is by Ms. Monica on machine learning algorithm for beam profile monitoring in high intensity Linac. 15 minutes, so I'll ring a bell after 13 minutes. Thank you.
Should I start? Okay. So good afternoon all. I am Monica from BRC. So I am going to present a small talk on machine learning algorithm for beam profile monitoring in high intensity Linac. So this is going to be outline of my talk. So I will start with some introduction, then I will go to some basic methodology, then beam profile reconstruction routine, and then reconstruction results using the simulation data from 8 electrode BPM and 8 feed-through based WCM. Then I will summarize my talk with some future direction. Okay, so in high intensity accelerators, beam diagnostics plays an important role. So beam diagnostics can be divided into 2 categories. One is the invasive technique and one is the non-invasive techniques. So these invasive techniques are destructive in nature, and however they are accurate but can damage the sensors and can disrupt the beam, especially in high intensity beams. While the non-invasive techniques use the electric and magnetic field of the beam, and accordingly it will characterize the beam. So some of the examples in non-invasive techniques are the BPM, button BPM, which are the beam position monitors, which are used to measure the position of the beam, and WCMs, which are the wall current monitors to measure the beam current, and the longitudinal bunch measurements in Linacs or in other accelerators also. So here we are trying to widen the range of measurements using the same diagnostic device, using the same non-invasive device. So we are trying to reconstruct the transverse beam profile using the ML algorithm, which is however possible with the invasive techniques like the wire scanners using computed tomography. So we have write a Python-based code using the machine learning algorithm. So here, instead of a conventional 4 electrode-based BPM, we are going for 8 electrode BPM, and this is a schematic for 8 electrode BPM, where electrodes are placed uniformly over the metal sphere, and beam is passes. Here we are showing some offset in the beam. So the signal which is appearing on these electrodes is basically can be calculated using the image charge method, and this is a basic equation to calculate the image charge method, and the more details can be found in the references and more in other physics books. So this is the basic equations to find out the electrode signals on these 8 electrode, but further we can expand it, and its higher order moments can also be calculated, and we can also multiply it with the charge distribution in X and Y. So normally in accelerators, Gaussian distributions are found out, So if there are two different Gaussian distributions which are having the same sigma square, so the sigma square I'm defining here as sigma x square minus sigma y square. So the Gaussian 2D Gaussian distribution, which is having two profiles which are having such kind of distributions which meet this criteria, can have the same signals. So that can give me the degenerate solutions. So I want to avoid these degenerate solutions also. So to meet the accurate beam profile distribution, I should put some physical constraint on my ML algorithm. So, okay. So here I have generated a simulation-based input beam in 2D. So it is a 2D Gaussian distribution in X and Y. And here I am plotting the corresponding signal on the electrodes. So it is a normalized signal plots. And in actual measurements, I will be available with these BPM signals. So this will be my white true signal. So actually, I will have only these signals, and I want to reconstruct this beam distribution using this white true signal. So that output that I am interested is the X-tri distribution. So since it is a Python code, so I will just tell about a little bit about my code. So I'm initially starting with some random Gaussian distribution with n number of sets. So in my case, I'm using initially 100 set of Gaussian distributions. So n number of particles with x and y coordinates have been stored in a matrix X, which is of 2 cross n order, and the corresponding signals, BPM signals of these distributions are stored in a matrix Y, which is a 1 cross 8 matrix. Now to avoid the degeneracy, which was defined earlier, I have a radius limitation in my code. So I should have predefined a beam radius that I should know with some invasive techniques. Okay, what will be my beam radius within which I will generate these initial distributions. So that will mitigate my degeneracy problem. So once I have those initial Gaussian distributions, so if I calculate their respective potentials on the electrode, then that will never be same to my actual BPM signals that I will provide to this. So I have some beam manipulation operators, so which I am defining as translation operator, scaling operator, shearing operator, and a banding operator. So just for example, like a translation operator. So if my beam which is having some distribution in X and Y, but it is having some offset. So what it will do, it will manipulate the position of X and Y of each particle with a small amount of delta X and delta Y so that it can go towards an actual distribution. Similarly, the scaling operator will stretch the beam with respect to its center. This shearing will rotate the beam, and banding will introduce some distortion if it is a nonlinear distribution. Afterwards, now after applying these beam manipulation operators, which I have defined here, so those initial distributions which I am defining here will get transformed. Now to identify which are my good signals, or which distributions I have to select it and which distributions I have to neglect it. So that is based on a loss function. So basically this loss function is guiding my algorithm and will help us to identify the good distributions. So it is having two components. So one is the mean square error component. So it will match the signals between a y true is my actual signal and y tri is my BPM signal, which is coming through the simulation distributions. So this mean square error should be as low as possible. The other component is the exponential penalty term. So this penalty term will help me to find out the actual beam size. So the size of the beam in X and Y should be accurate as much as possible. So if it is away from the actual position, then the penalty on that distribution will be very high and will be neglected. So my total loss function is a combination of these two functions, which is MSC plus EP. So I have to minimize this loss function. So this is a basic flow chart for this. So again, I will just recapping the previous things. So I will start with some n random Gaussian distribution, which I am storing in X n matrix. So n will go from 1 to n. And then I am calculating yn corresponding BPM signals. And then I will try to find out the loss function, which will never match to my y true signal, obviously. Then I will apply some beam manipulation operators, which was defined earlier. And those distributions will get transformed. Now those transformed beams will be stored in X and tri. And then the corresponding signal are Y and tri. So now I will try to find out the loss function corresponding to this thing, and it will operate all the manipulation operators till this loss function criteria is met. Now, the distributions which are minimized, so some of the distribution will have the lowest minimum loss function, and they may sit to a local minima, and they may sit to the actual minima of the distribution. That may be an actual distribution. But now, since now the probability of going into the next algorithm, which is a genetic algorithm, is based on this loss function. So the distributions and set of distribution, I will select the top 3 or top 5 distributions which are having the lowest loss function. So basically the probability of their selection is inversely proportional to their loss function. So those distribution I am selecting, I am storing in GN. Now it comes to the genetic algorithm part. So this method is highly inspired from the genetic algorithm, which is based on a optimization technique and on a natural selection, where the candidate population are being optimized based on some crossbreeding and mutation based on some fitness factor that was defined in the system. So it is similar to that. So the optimization goal is to minimize the difference between the simulated and true electrode signals, and the beam manipulation operator will try to modify the beam shape, position and size with a higher amplitude here, and it is an iterative optimization. So as I have stated in last slide, so I will start with some white true signal that I will get from the experiment. Then I will start with some initial random Gaussian distribution, and then we'll minimize the signals at the probes using the loss function. Then the selection of distributions randomly based on some fitness value. Then I will select some top 3 beams from here, and I will mutate each solution with a higher mutation rate. So that higher amplitude and the mutation rate will be more than the beam manipulation operator, where I was applying delta X and delta Y. So here those delta X and delta Y will have a higher amplitude, so that these distributions which gets stuck at some local minima will get out from the local minima, and then the new distribution which I will get here will become my new set of initial random Gaussian distribution. So this is an iterative optimization, and it will go on until the convergence criteria is satisfied or the iterations that I have defined are met. So here are some simulation based data. So after the code was developed, so we validate this code initially with the simulation results. So the picture which is having input beam is basically generated initially from these simulations, and the picture which is having a reconstructed beam is actually the reconstructed beam done by the code. So the signals corresponding to this input beam was sent to the code as a white true signal, and this is the corresponding reconstructed beam. So this was initially done with the 2000 particles. So here we observed that the reconstruction was a little bit poor. So then for the same beam, beam parameters, we increase the number of particles. So this was the input beam in that case, and these are the probe readouts. So after these signals were sent to the code, then we observed the reconstructed beam. So this is the reconstructed beam, and the corresponding BPM signals are shown here. So with more number of particles, we observed that the reconstruction was much better. Now to observe the effect of iterations, we plot the previous results with the iteration wise. So this was the iteration 1. So in the first iteration, we observed that beam was a little bit circular, and as the iteration progresses, so it is moving towards the actual distribution. So we observed that the initial 10 to 12 iterations are enough to gain the actual beam information, like if it is rotated or it is offset. So that is enough, but we have selected 20 iteration to find out a balance between the accuracy and computational efficiency. So in our code, we are using right now are 20 iterations. So after validating the code, we have preliminary designed a 8 electrode BPM, and this is a design in CST Microwave Studio. So for the design part, we are using CST Microwave Studio, and we are using a frequency domain solver and weak field solver. So these are the frequency domain solver results for this 8 electrode BPM. And since after optimizing it, so after optimizing it in the frequency domain solver, then we use the wake field solver. So in wake field solver, we can define the particle bunch information. So we can define the particle charge, its sigma, and the velocity. So okay, so since this, if we define a center beam, then there will be no effect, then there will be equal signal on all the 8 electrodes. So we provide an offset beam. So with the offset beam, we observe that there is a difference in the signal amplitudes. So then we normalize these signals, and these are the normalized input signals which were sent to the reconstruction code, and this is the reconstruction beam. Since we cannot define any beam shape here in wake field solver, there is no option for that. So we assume that, okay, the reconstruction code should provide us a circular beam, so which was expected, and these BPM signals were also closely matching to each other. So this is a preliminary design right now. So we have another beam, non-invasive beam diagnostic device, which is a 8 feed through wall current monitor. So this we have characterized, developed, and recently installed in the LEHIPA Beamline. So it is a high bandwidth wall current monitor, and it is different from the conventional resistive wall current monitor device. So in conventional wall current monitor, there is a ceramic gap which is placed, and resistance are put over all the gaps to capture the beam information. So here, instead of that, that gap has been replaced by a tapering, and then there is an inner coaxial metal cylinder where these feed-throughs are mounted. So these are the lab characterization results. And these are the actual beam experiment results with 20 MeV proton beam. So during the experiment, we used only one feed through. Other feed throughs were matched to 50 ohm. Since this device is already installed in LEHIPA Beamline, so we are planning to utilize the signals from this 8 feed through WCM. So now to see its feasibility, we use again the simulation tools right now. So we again use the wake field solver, and some offset beam was given, and those offset normalized signal were sent to the code, and this is the reconstructed beam. So now I'm going to summarize my talk. So we have developed a Python program to reconstruct the transverse beam profile using ML algorithms, and the beam radius has been recognized as a physical constraint to avoid the degeneracy in the system. And increasing the number of particles also improves the quality of the reconstructed beam profile, but it comes at a cost of simulation time. So the reconstruction method, initially we validated with the simulated generated distribution, and later we tested it with the 8 electrode BPM and 8 feed through WCM simulation results. So the plans are underway to utilize the WCM signals, which is now operational in LEHIPA. And once we get the enough data set and enough beam profile distribution using the experimental data, so we are, then that data can be a valuable training data set for ANN and CNN, which is a more advanced diagnostic tools. So thank you for your kind attention.
Thank you for finishing in time. Talk is now open for a couple of questions. Dr. Vinith Kumar.
Monica, very interesting talk. So what you described about the measurement of the beam profile using this electrode BPM, I was just curious, has this been reported by, I mean, have others worked on this? Like, what is the status?
Sir, that paper I have mentioned, so the basic methodology they have given in their paper, and the more detail, like that. Those.
This has been implemented, and like.
So using WCM and actual BPM measurements results, it has not been even be reported, but the simulation results people have reported something.
Practical implementation will be
still
first time, kind of.
Yes, sir.
Okay, thank you.
Okay, thank you for this nice talk. I have a little question that what happens if you do the same for only 4 probes, yes, not using many other probes?
So, okay, so I will just go for that. So for that loss function formula, so that loss function formula, So, okay, so this formula has been defined as 1 by NE, y prime minus y true, and like this. So it is inversely proportional to 1 by NE. So NE is the number of electrodes that you are using. So if you go for 4 electrode, then obviously the errors will be more and the reconstruction will be poor in your case.
Okay, one last question. Yeah, sir.
Hello. So my question is regarding the you are taking 20 iterations to converge your solutions. So anyway, you are going to implement this in real operation of the facility.
Yes, sir.
And WCM is giving the data and whenever you passing the beam.
Yes, sir.
So what is your total time taken for converging the solution and the repetition rate of the machine?
So, sir, as of now, it depends on the whether you are using a normal PC or workstation. So the simulation time will depend on that, obviously. So right now, I'm running it on a normal PC, which it is using this Jupyter notebook is actually using only 1 core, and the space it is using very less. So it is taking roughly around 2 days, to be honest. But it also depends on the what input parameters you are feeding to your code. So if you already know whether your beam will be rotated or slightly elliptical in shape, so if you implement that in your code, then you can reduce it down to half or lesser than that.
My worry is about the machine operation. Let us suppose machine is operating at 1 hertz.
Yes, sir. Maybe we can have detailed discussions during tea. Okay, so thank Monica again for a nice talk. On behalf of organizers, we present a memento to Ms. Monica. The next talk is on generalized 4D phase space reconstruction method concatenated with particle tracking code by Mr. Sanjay Tempu. Yeah.
तो ड्रॉप डाउन है ओके present what
So 15 minutes total.
Okay, sir. Thank you, sir.
I'll ring a bell after 13 minutes.
Okay. So, this is a method. Let me give you the introduction first. This is a method where we like to get what is the 4D space beam distribution is at any optical accelerator layout. So, I have the co-authors for this paper here. So, you take any accelerator facility in the world, you want to know what is the 4D beam space information. 4D, I mean, he says XX prime, Y prime. That is the transverse beam space information. So knowing it, you can do a lot of things better. You can optimize your accelerator facility to satisfy the need of it. So that is the main crucial part of it. So there are other methods to get the beam matrix. I would like to highlight those things first. And when I go to my method, I'm going to prove you that why is the most generalized method. So I have broadly classified it into this way. So there are some methods that do only 2D projections. Either you look at the X plane or you look at the Y plane independently. I call these methods that measure only 2D projections. You have this basic quad scan, basic paper plot slit techniques. So these methods conventionally used, I will say, in most of the accelerators in the world, because people wants to make life simple and they do not deal with correlations. So it will work for your uncorrelated beam distribution. Here, the correlation, what I want to emphasize is the interplanar correlation. That is the correlation between the X and the Y plane. Suppose there are other methods that can deal with correlations also, that can deal with like the advanced paper plot, slit scan combined with tomography methods. But all these two list of methods are, I want to emphasize here, as matrix based. That is that you are propagating the beam using the transfer matrix, and hence it is a linearized theory. So there is a linear assumption built in it. And also, this does not include space charge effects. So sometimes people do is include space charge, but they linearize the space charge and use the method also by matrix base. But this may come at a cost like distribution assumptions, so and so. So coming to our method. So I say that this method is a generalized method. It will work, to put in a free way, it will work without correlation, with correlation, and it will even work with the space charge. Why it will work? It relies on these two core principles. First principle is that you will require a several set of 2D profiles, intensity profiles, as an input for this method, and you feed it to the algorithm, and what it generates you is the full 4D space beam reconstruction. If you look at it, there is a space charge effect. How we are incorporating the space charge effect is that the evolution is not matrix based. We are using a particle tracking code to evolve our beam throughout the layout. So this is the two core principle. So how are you going to do this method? Let me describe you the method here. So you take any accelerator facility in the world, your facility, you look at a point, that is a point of interest, where you want to reconstruct your 4D beam distribution. You let the beam evolve through set of your optical elements. It can be anything. It can be your quadrupole, dipole, which you have control over, and you go to the point, the profile monitor point. That is where you place your screen and get the intensity profile. I call this point the measurement point, and the point of reconstruction as the reconstruction point. You do get some profile. You do it for not for one settings, you do it for many settings. This is what you do in the experimental procedure. In the parallel, what you do within a particle tracking code of your interest, you do the same thing, but here, what you introduce, here is a test beam of your interest. This is my guess beam, where I put it here. I'll evolve through the same set of beam optical layout, and I will play it with the same field settings that I got here to get a simulated profile here. So what I have is a measured profile that is actually my experimental profile, and here the simulated profile. Of course, since my test is not the actual one, here it will not match at the first scenario at all. So what we do next is comparison. So there is a comparison going on here. So to put it simple, this method is you start with a trial beam, pass through the optical layout over the same settings that you have played with here in the actual layout, get a profile, and you try to redistribute this test beam in such a way that this simulated profile matches the profile that you have actually got in the measured one. This is the whole crux of the method. If I say this is actually, if you understand this part of the flow chart of this algorithm, then I think you understand most of the part of the algorithm. Rest are all tidbits. So how are we doing the iterative comparison? So comparison between the measured profile and the test profile. So what you take, you have an intensity profile per setting, which looks like this. You first do is discretize into small grids. You do a grid by grid comparison per setting per profile. So within a particle tracking code, what you will have is that you know where at what grid the particle will hit. So for every particle, we will assign a weight per every setting. So the settings of all the particles are taken into account. So weights are basically calculated comparing the intensity of a single grid at the actual experimental profile and the grid at the same location grid in the test profile. So suppose, so you get a weight, a single weight, and you get it for per particle, per setting, you get a weight. Now what you do is that there may be some particle hitting a grid that doesn't exist in the actual profile. Those weights, you set it to 0. That those particles, we will discard it. We will delete those particles. If any of the settings having a particle having a weight 0, we'll delete those particles. After that, what we'll do is that with leftover particle that has weight, we try to introduce new particles in the surroundings of the test distribution uniformly. So we put in summary, what you have done, coming back here, is that when you have come to this profile and do the comparison here, what you have done is deleted those unwanted particle that has not matched the profile and enhanced those particle that has highly matched those particles, match those profiles per grid. This comparison is done grid by grid. So now at this iterative step, you have a new set of test distribution. You let it evolve through the same setting, get the same profile, and you go to this step 2 and compare again and repeat this step until you hit some saturation. So after this, I would like to say, when do we know that our profile, the test profile, matches with the actual profile? To account for that, we define a quantity called root mean square error, RMSE, at every iterative step. What we have looked is that we look at intensity per grid of the reconstructed profile and the intensity per grid of the measured profile. We take a difference of it and we square it and mean with respect to the grid. So reduction in this value will signify that we are going more closer and closer to our actual distribution. So you will see that this value starts up quite large comparatively and falls, gradually flattens and saturates. And saturation of this will yield us to say that when to stop the iteration. So here the challenge is that when we discretize our screen profile, how do we select the grid size? So at the start, you want to keep in the few points here. So if you have very large grid size, you will reduce accuracy. You will have a lot of particles that are existing, unwanted particles. And if you go for smaller grid size, you will put some constraints that will say that you are deleting a lot of particles. So you need to have there will be an optimization problem for here. So what we have done is approach an adaptive grid size approach. We start by larger grid at the start of the step, and after as the step proceeds, we will gradually decrease the grid size. So this is basically what we have done is that in this updatation, once you run the iteration, you start with a certain grid size, you run it for a while with the same grid size till you hit some tolerance, then you update the grid size. This criteria, you check it here, is that you calculate the RMSE at the current step and you go to the RMSE at the previous step, you take the difference of that one. This will signify if it hits some saturation for a particular grid size, then you update the next grid size. So this is how we go for the grid size variation. Another thing, so I actually want to test the efficacy of the program, how the program is well working or not. So what I have done is taken an experimental layout come as simulation. I have done a simulation of it. So during simulation, I have taken the reference beam and I have to generate a correlated reference beam. So how the correlated beam is generated is via something called Cholesky decomposition. So what is this method? So you start with some uncorrelated data set at the start, and you say that you require a certain covariance matrix to be satisfied. You take a Cholesky decomposition of that matrix, you add this decomposed matrix with the uncorrelated data set, then finally what you have got is new data set, transformed data set, that will be correlated in such a way that will satisfy your original covariance matrix. The purpose of using this method is because it provides you control correlation in a sense that you can have every element of the covariance matrix, the correlated part, of your desired quantity. So to quantify the interplanar correlation, we need a factor, a coupling factor. I call it the coupling factor. So this factor, if it is 0, then we'll say that there's no interplanar correlation. And if it is large, we'll say it has quite a large interplanar correlation. So for simulation purpose, I have taken two layouts. The first layout I have taken is from the heavy ion beam layout of the RAV facility at VECC. So up there, you will see here at the behind there is a Linac 3, which will provide you an energy of 415 kV per nucleon. I have taken a nitrogen beam, nitrogen 4+ beam that takes up energy of around 5.8 MeV. And throughout this procedure, the reconstruction point where I want to get the 4D beam distribution is at this end, which is, you can see it from the side view, this diagnostic box. And the measurement point where I'll get the profile, 2D profile, to be fed into my algorithm to reconstruct the 4D distribution at this point is here in this diagnostic box. So I have got several settings. So the thing is that the settings are selected in such a way that I play with these two quadrupoles that is given to me by the operator. So this is the engineering diagram for this. This is the reconstruction point, and this is the two quadrupole and the measurement point. So what I have done is that I have used here as a reference beam. First, I have done with the case 1 without interplanar correlations, almost zero correlation in the planes. Second case I have done is some interplanar correlation with decoupling factor of 0.8.
So you have 2 more minutes.
Okay. So 9 profiles were selected. The settings are to be selected in such a way that it is experimentally feasible. That is, there is a screen size limit that I have to put a profile in, and there's a field limits provided to me by the operator of the quadrupole. So I have selected 9 settings. So the problem with quadrupole is that I don't get a full phase advance in one plane. This came because of my limitations of screen size, the optical layout, and the field limits available to me due to quadrupoles. So I had quite a good phase advance in X. I don't have quite good in Y. If I were to have better here, I will have lose in here. This came because of the optical limitations that I have. So the settings are selected in such a way it should ideally span the full phase advance. So in our reconstruction algorithm, I have started with this initial test beam, which is uniform, independent in X, X prime, Y, Y prime at the step 0. This is the test beam that I have taken it. After several series of this evolution of beam through the layout and comparison iteratively, I have come to this distribution. This is roughly after 15 iterations. If I compare with the actual distribution that is happening, reference distribution, it looks like this. So you can see it's quite a we have well reconstructed this distribution here. So this is for the correlated one. This was for layer 1. So this is the RMSE of how the RMSE behaves over the iterative step. So it starts large, quite large, 10 to the power minus 1, and it falls down, hits around 10 to the power minus 6. And this is where you say that I am done a well enough reconstruction here after the 10th step. So in the layout 1, it worked with and without interplanar coupling. So I could have better reconstruction if I had proper phase coverage in the other plane also. So another thing I have taken is another layout which comes from the Linac. Here the reconstruction point is just after the electron gun at this point, and the measurement point is on this diagnostic box. Here I played with the solenoid field to get it. What is different from the previous layout in this layout is that it has a space charge effect. So the problem of having angle span, phase advance span in both the planes is not problem here, because the solenoid rotates the beam in both planes simultaneously.
Please try to wind.
Okay, thank you. So coming to my result here, this is the reconstructed distribution compared with the reference distribution, and this layout include this space charge. So finally, I like to conclude that the method works in following scenarios. First one, it worked without interplanar correlation, the case 1 of the layout 1. It worked with interplanar correlation, layout 1 of the case 2. And it also worked with the space charge. And I would also like to point that I started with just a uniform distribution as the guess distribution. I have come to the actual distribution, which was the Gaussian in nature. So there was no distribution assumptions required. So hence, I would like to conclude that it works in several scenarios, or most of the scenarios. And hence, it is the generalized 4D space reconstruction method. Finally, to end it up, I would like to keep in mind few things should keep in mind before using this method. So it will work better if you have a very reasonable phase at space advance span. So apart from having reasonable phase span, the accuracy is determined by taking large number of particles in the particle tracking code and taking final grid size. But this comes at a cost. You will have a computational cost. So either you have the patient or the hardware to do it. Apart from that, there's a limitations like resolution of your optical system that will determine the final grid size in the algorithm. So this concludes my talk. And finally, I would like to do some acknowledgement. Thank you, Dr. Chirandip Das, for this space charge modeling part.
Thank you, Mr. Bhutia, for a good, nice talk. I think we will have one quick question. Yeah, minute one.
Very interesting presentation. You mentioned at the end, probably you did not have the time, but you mentioned about that it works even in the presence of space charge, right?
Yes, yes, yes.
Space charge, actually, the transformation itself is the distribution dependent. So it is really interesting that it works in that case. Will it break down at very higher value of space charge? I mean, since you are doing the calculations, maybe.
Not tested for the very high values of space charge. This one, it tested for mild values of space charge for now.
Okay, so maybe you can find out at what limit it breaks down. Thank you.
Oh, so we thank the speaker again.
Okay.
And on behalf of the organizers, we present the memento to.
But sir, I'd like to say that I think it will work because this doesn't depend on you are doing particle tracking at the end. So if your particle tracking code can incorporate the space charge effect, it should work. There's no assumptions needed here. Thank you. Thank you, sir.
Last 15 minutes talk today is by Mr. B.B. Srivastava. He will talk on beam orbit correction for beamline users of upgraded Indus 1 storage ring. We appreciate his dedication to the field. He's here in spite of some very difficult personal circumstances. Mr. Srivastava, 15 minutes, so I'll ring a bell after 30 minutes.
Okay. ठीक है सर आपका है सर ठीक है
Sorry.
So good afternoon to all of you. So I am going to present a work which was actually a group activity sort of things, and recently the Indus 1 has gone for the major upgradation where various diagnostic devices has also been installed, and to improve the performance what we have done and how we have achieved, I am going to talk about that. So this is basically a new orbit where various types of diagnostic devices has been installed, and we are in this talk mainly talking about the beam position monitors. This is the first time we have installed and commissioned it and being used continuously. So there are total 8 beam position monitors, and we have also developed the processing electronics indigenously and tested it, and we have deployed it. So these are the locations what I talked in the previous slides. These are the actual devices, and these are the electronics which has been kept in the magnet power supply hall of Indus 1 and interfaced with the system. So this one is the processing electronics. This first graph gives the resolution, intrinsic this resolution in the laboratory environment, and this is the stability of the beam for both the cases. This is duration is 1 hour. This is with the beam. This one is the 0.63 micron resolution. Say we can just considering less than a micron, and this is about 2 micron. This RMS stability is that. These are the specifications of the electronics. This works in this region, and this is the GUI which has been developed by my colleague at control rooms to display the orbits, control the orbit, and various things. This response matrix measurement, etc. So our work started with the reference orbit generation. So for this, my colleagues have been developed the slow orbit feedback systems, and this measures the response matrix using 8 cross 8. This we have 8 beam position monitors and 8 steering coils. By using that, it determines the response matrix, and after applying that, we are able to calculate the steering coil strengths, and these are estimated using orbit and inverse of response matrix. Finally, applying singular value decomposition technique, we are going to achieve the orbit. At the beginning, at the very initial stage, the SOFB system which was implemented using SVD techniques with lambda equal to 5. Lambda equal to 5 means we have total 8 parameters. And only 5 have been used out of that, and it is just to avoid the saturation of the steering coils, right? And initially the correction rate was kept at 4 Hz. So this was the this red colored graph shows this is uncorrected orbit. Uncorrected means whatever is the situation, we are not going to apply any corrections, and this is a natural injection orbit, red color one. And after that, we have applied a new orbit, selected a new orbit, and tried to make it near to the absolute zero position. So green color shows that, and by using that, these orbits were actually obtained through applying a magnetic field through the steering coils. So that was driven by the power supplies, and because of this was demanding very high current. Mostly all the steering power supplies were engaged about 60 to 70% during this operation, and this was giving a very limited operation in this SOFB action, this limited current source. Second one thing was that while doing this, since this was done first time, so what we have observed that near to this zero orbit, these beamline users were getting very low SR flux. Sorry. And this orbit, basically at this orbit, they were unable to realign because the beam lines are very old and they have limited facility of that, and they were unable to maximize the flux. So this is the typical curve. Before that shutdown, they were about to getting this 4,000 counts, and after that they were getting a 600. That was a significant decay in that when we are operating at the corrected orbits. So to analyze this issue, we went through multiple steps. So first thing was that this beam quality issue, we have analyzed the recorded data which was kept on the Indus 1 server, this Indus server. So this curve shows when there is no SOFB is applied. So this is a natural decay, this current, and one can see that there is a drift in the position. That is very slow. It is about 4 hours. So here we can see only this 80 micron shift is there. So and when we apply the SOF at 4 Hz, this actually positional variations are very high. Right? So analyzed to establish the relation, whether it is really because of the our correction action or it is just a natural things, we just analyze further, and that was to see the power supply readbacks. So this one is the power supply readback when the SOFB was kept off, and all the power supply were on. So there were this fluctuation in this stable position, this stable current was less than 10 milliampere. But whenever the power supply, this SOB action was on, this fluctuations was going about 200 to 300 this milliamperes. So this was seen that actually while stabilizing this, actually this actual phenomena was happening like that, it was the beam was oscillating. So it gives the impression that most probably the correction is this overcorrection. So we studied those, and the fluctuations were seen, and and after to this on demand to analyze this, what we applied, applied on demand correction. On demand means whenever the beam shifts from its orbit by 35 micron, we will recorrect it. Rest of the time it will keep. So this was the earlier position, and after this is a stable position. This beam is totally within the 35 micron. So another issue was that the beam size and this intensity, sudden intensity changes at nearly 60 to 70 milliampere, and this was analyzed and through the diagnostic beamline, and one can see that this size, vertical size was drastically changing at that point. And while analyzing the data, these images, we could see that at higher current the beam size is very high and ellipse is also diagonal. At low current this ellipse size is very small and it is this horizontal. So the size is very small. That's why the intensity, the position was almost constant after that. And the beamline users were getting a very stable flux per milliampere counts. So this phenomena was observed that it is related with the quadrupole power supply settings. So next thing was that since the corrected orbit we are unable to serve the purpose and the beamline users were unable to realign according to this, so we again went for the user orbit so that we could satisfy all the users. So in that case multiple iterations were done starting from the injection orbit. Slowly we moved towards the this corrected orbits, and by getting a feedback from all the beamline users, we finalized a single point orbit that we named it user orbit. And presently this machine is operating at that user orbit. So one can say that this user is worldwide, the orbit is kept close to the center point of the beam pipe. So this is not an ideal orbit, but this satisfies all the beamlines, and at present this is only the suitable option because of the constraints. These are the comparison of the user orbits. This red one is the uncorrected orbit. Then this was the corrected orbit at which point the users are getting very low flux, and finally what we have corrected, this one blue line, this is user line. All the beamlines are satisfied at this point, and right now what we can measure the parameters on which we can whether this is good or bad. It is only lifetime. So the lifetime at this green colored orbit and the blue colored orbit is almost same. So that's why we have kept it right now. So the beam orbit correction with respect to user of Indus 1 has been successfully done. In user orbit, the lifetime of the store beam is nearly 160 minutes. And from storage ring point of view, the corrected orbit is generally preferred. However, in the present case, user orbit fulfills the needs of the beamline users. That's why we have gone it. It was observed that the beam position drift is primarily dependent on the beam current. That 80 micron drift is occurring overall through the field cycle, 200 minutes. This highlighted the need of the slow correction in the SOB. To address this, SOB correction was 2 Hz. Finally, we have kept it 2 Hz and on-demand correction. Though now the system has applied orbit correction only when the reference orbit deviates from the plus minus 35 micron and stops over the corrections once the deviation reduces to plus minus 10 micron. Following these modifications, fluctuation in the beam lines are significantly reduced. The current, the it is maintained within the plus minus 35 micron with the SOFB action, and overall work highlights the complex design of these things, orbit correction, beam dynamics, beam performance, and the need of holistic approach to optimize the SR beam, right? So, okay, thank you very much.
Thank you, Mr. Vastaji, for finishing well in time. So I think we can take a few questions.
Srivastaji, it was a very nice talk. I want to know that by knowing the ellipse shapes, how you are doubting on the quadrupole power supply?
Actually, we have analyzed the recorded data, and this moment of time, the quadrupole power supply was changed.
Means it is observed?
Observed, yeah.
Sorry. Is this purposely changed or is changed during the operation by itself?
We have verified it by later on by purposely, whether it is linked with or not. Initially, it was observed by the this diagnostic.
So, sir, with your permission, yeah. One more question. What is the roadmap for further improvement of the overall performance of orbit correction in Indus 1?
Yeah.
So is this end of the result, or are we thinking for further improvement for the orbit correction as well as providing the beam to the users?
See, with respect to the user orbit, this is the best one until there is a facility of the realignment of the beam lines, right? Another thing is that the SOB action, it shows that we need a very slow action because there is no any other frequency, it doesn't seems like that. So right now we have applied on-demand correction. Later on we can slow it down, say 0.1 hertz or so.
Okay, so if there are no more questions, we thank Srivastavji for a wonderful talk and for finishing well in time. So on behalf of the organizers, it is a pleasure to give him a memento. Okay, so we now come to the oral posters session. There will be 12 presentations of 5 minutes each. So I would urge all speakers to please first highlight their poster ID so that people can visit the posters and then bring out the highlights of their work so that detailed discussion can be had at the poster. So the first presentation will be by Aarti Chaudhary. It is on development of 325 MHz single spoke resonator 2, manufacturing challenges and solutions. So Ms. Aarti Chaudhary and Mr. A. Shinde, are you there in the audience? Okay, so they are not here. So we will proceed with the presentation for poster ID 775, electromechanical modeling of superconducting RF cavity by Shweta Agrawal. So 5 minutes time, 3.5 minutes, I will ring a bell.
Yeah, arrow up down and verified that I go. So like
Good afternoon all. I'm Shweta Agarwal from Ion Accelerator Development Division of BRC. I'll be presenting electromechanical modeling of superconducting RF cavity. So in the upcoming medium energy high intensity proton accelerator, MEHIPA phase 1, the proton beam shall be accelerated to 40 MeV using both normal and superconducting structures. RF cavities can be represented by its electrical and mechanical equivalents, and coupled together these form the electromechanical model of the cavity. This model, when implemented on hardware, creates a real-time simulator which allows replication of the cavity dynamics and its analysis under various operating conditions. The advantage is that the simulator allows testing of the cavity electronics without requiring expensive, time-intensive physical superconducting RF cavities and their associated infrastructure. Figure 1 shows the equivalent circuit model for the cavity. The electrical model uses lumped resistor, inductor, and capacitor with the differential equation shown in equation 1. And the mechanical model caters to the detuning of the cavity due to mechanical disturbances and vibrations with the differential equation shown in equation 2. The equation 1 and 2 are discretized to be simulated and then finally implemented on hardware. This is the complete electromechanical model of the cavity. The center shows the electrical model, and the output of the electrical model is fed to the Lorentz-Force detuning model. The output of the detuning model, which is the detuning of the cavity, is fed back to the electrical model, and this shows the output, which is further being displayed on a GUI. This is the GUI. The input parameters of the GUI are shown, which is the cavity resonant frequency, the internal and external quality factor of the cavity, R by Q of the cavity, the generator, and the beam current. And the output parameters are the cavity voltage and its phase, the reflected voltage, the fall time, and transmitted and reflected, and the cavity power. This shows the plots which are shown on the GUI, and here the parameters which can be fed as well as can be read. This is the result from simulation. The first shows the result due to various coupling conditions of the cavity. We can see the overcoupled, critically coupled, and the undercoupled conditions, and it can be easily distinguished from the reflected voltage waveforms. The figure 5 shows the effect of LFD, Lorentz-Force detuning, which we can see that there is a detuning in the cavity. That is a change in the frequency of the cavity, and also the transmitted voltage phase is also changed. The next is the implementation of the model on a real-time simulator using a Xilinx Zinc F7010 FPGA. The input to this model is the INQ components of the input cavity voltage, and the output is the INQ of the cavity voltage being built in the cavity. This figure 7 shows the result with the I component as a pulse input and the Q component set to 0. We can see the blue curve showing the cavity output voltage I component, and the Q here is 0. Similarly, figure 8 shows the same conditions, but now the detuning delta omega is kept a non-zero value, which is shown by the output I and Q components both being non-zero now. To summarize, the electromechanical model has been simulated as well as implemented on hardware, and the results of the latter match the simulation and the analytical results. A real-time simulator with all the features of the actual cavity implemented will provide a powerful platform for the testing and the validation of the RF electronics. Thank you.
Thank you for finishing well in time. Please visit the poster in case you have questions, because we have 12 presentations now. Thank you. So the next talk is going to be by Mr. Manoj Kumar, Cryogenics Operation of 2K Test Facilities for Superconducting RF Cavities at RRCAT. You'll have 5 minutes. I will ring a bell after 3.5 minutes. Please wind up in 1.5 minutes after.
कैसे करना है ये पॉइंटर है ये ऐसे कर लो ना इसे भी कर सकते हैं आगे
सभी को नमस्कार I am presenting cryogenics operation 2K test facilities for superconducting RF cavity at RRCAT. RRCAT had taken a project for developing superconducting RF cavity. This cavity test at 2 Kelvin. For 2K operation, a large and dedicated cryogenic system is required. For helium liquefaction, you use LR20 liquid helium plant. And for transferring liquid helium, we use in-house fabricated transfer line for BTS. It is around length is 12 meter. And for STS, around length is 55 meter. And in each test cycle, about 5,000 liter liquid helium we are using. And for LN2 shield cooling at 80 Kelvin, we use a Linac 50 liquid nitrogen plant. And in each test cycle, we use around 1,500 liquid nitrogen for that. And for 2K operation, this is a BTS crash state with connected helium transfer line with DIVAR. And after filling the after filling the desired level of liquid helium in the BTS crash state, it is further reduced to temperature 4.2 Kelvin to 2 Kelvin. For it, we use decrease the crash state pressure. For decrease the crash test pressure, using 2K pumping station. This is a 2K pumping station, and we have a total 3 set, And each set is contained at one is a booster pump, one is a backup pump. Its capacity is a booster pump is 2600 cubic meter per hour, and backup pump capacity is 630 cubic meter per hour. After during 2K pumping operation, a large amount of gas are coming from the BTS crash state and is collecting in the gas bag. And gas bag is a total, we have a total 9 gas bag, and gas bag is connected into a helium recovery compressor. And helium recovery compressor compressed 140 bar gas and collected into jumbo cylinder. And we have a jumbo cylinder, total capacity is about 15,000 liter liquid helium equivalent gas. Operation of VTS facilities. This is a cryogenics layout of the VTS, and these facilities can test 650 megahertz, 1.3 gigahertz elliptical cavity, 325 megahertz spoke regenerator, and this cryostat can. This is a VTS cryostat. We are looking the layout. This is a VTS cryostat, and this cryostat around hold 2,800 liter liquid helium, making it the largest liquid helium cryostat in India. The testing of SCRF cavity required stable 2K operation within pressure variation within 0.2 millibar. This stable operation is achieved using in-house design precision valve controlled by pneumatic positioner with micron level step accuracy. And this is a cool down curve, or this is a precision 2K control valve. After successful testing in the SCRF cavity in VTS cryostat, cavity dressed, then tested in the STS cryostat, and VTS facilities has been expanded for the STS operation, incorporating the helium transfer line, return line, 5K return line, 2K pumping line, and safety measure and instrumentation have been integrated in the cryostat distribution system. Helium was transferred into both methods, supercritical method and liquid method. The STS cryostat with dressed 5-cell cavity was cooled down to the temperature 1.94 Kelvin while maintaining liquid level more than 90%, simultaneously helium filling and gas pumping. Resource management and sustainability effort. To minimize helium leak losses, regular recorded helium leak detection in conduct on the more than 100 joints every week. Leak check are performed at the everywhere here gas are presenting, helium recovery compressor, and we have achieved 0.5% during each test cycling, and stock assessment are conducted on a weekly basis. And we have developed in-house helium extraction for the BTS cryostat after over the BTS test, and this liquid is distributed in the RRCAT in different division for using low temperature experiment. And we have this is a we are looking at leak detection is a pigtail joint of the cascade helium cylinder, and we detect the leak, and after that we replaced it. And that figure is showing that after cooler of the recovery compressor, he also observed the leak there, and and we repaired it. And the other figure is showing that cryogenic jetty valve correction during operation when jetty was leaking, and after that we opened it and find that one seal was broken and then change it. The process liquid helium after 2K operation, liquid helium production, 80K sealed cooling, and helium achieving 2K through evaporating cooling and helium gas recovery. Through improved resource management, helium recycling and infrastructure, we have overcome operation challenge and achieved over 70 successful test cycle in a VTS and multiple cool down in STS cryostat. We have achieved helium gas loss rate and less than 0.5%. We acknowledge all our section people, and acknowledge also the colleague from superconducting cavity developed division, RF system division, accelerator control system division, health physics unit of RR. Thank you, sir.
Thank you, Manoj Kumarji, for a nice talk and for finishing on time. The next talk will be by Sri Koma Gyanaspurti. It will be on calculation of heat dissipation during electropolishing of SCRF cavities. Sorry, Srimati Miss Koma Gyanaspurti. So 5 minutes. I will ring a bell after 3.5 minutes. Please wind up in 1 hour.
The next.
Laser.
Laser pointer which one?
Good afternoon all. Today I will be discussing about the calculation of heat dissipation during electropolishing of SCRF cavity. So superconducting cavities are the essential components of the particle acceleration. And in order to achieve the required optical performance, we need very high quality cavity surfaces. So we will be using electropolishing technique to get the smooth and defect-free cavity surfaces. In electropolishing process, we'll use niobium cavity as anode, aluminum as cathode, and H2SO4 and HF in 9:1 ratio as electrolyte. So electropolishing of the SE-RF cavity is carried out in the mass transfer control regime decided by the VI graph. The success and the quality of the electropolishing is highly dependent on the temperature, because changing temperature can directly affect the reaction rates, material removal rates, and the surface smoothness. So to maintain the temperature, first we should know what are the heat sources. So in this study, we are trying to estimate what are the heat sources and their respective heat loads, and comparing their values with the experimental data. So here, here we are having the EP setup. Now 650, we are doing calculations on the single cell 650 niobium cavity. So niobium, we are having elliptical portions and 2 beam tubes on either side, and a aluminum cathode which is coaxially aligned with the niobium cavity, and an external cooling system to maintain the temperature. So first heat source is the heat source due to the chemical reactions. During EP, we'll see the oxidation and dissolution of the niobium. There will be a simultaneous oxidation and dissolution near the of the niobium at the anode. And we can see the overall reaction is this one. And if you calculate the enthalpy change, it will come as negative. So the reactions which are happening here are exothermic. So these reactions will act as a heat load to the system. And second heat source is the heat load generation due to the electrolyte. Like any other conductor, passing electricity through electrolyte will also dissipate heat. So as discussed before, beam tube is a very simple cylindrical structure with cathode radius as 15, anode as 60, and its length 170 degrees. So if you directly apply this formula, we can find the resistance of electrolyte in the beam tube. But in the elliptical section is a complex, and with it's a complex structure, and we'll have the various outer radius. So in order to calculate the resistance of the electrolyte in the elliptical part, first I divided the elliptical part into 10 parts with outer radius using this formula. So then I substituted this, and all the 10 parts will be parallelly aligned like this in between cathode and anode. So if you do EP at 20 degrees, we'll get a total electrolyte resistance of around 0.126 ohm. So the third source is the heat generation near the electrode. So though niobium is a very good conductor, we'll have a passive layer on the niobium, which is made up of Nb2O5. So it is a very bad conductor. So passing a current through this layer also will give the significant amount of heating. So if you see the I versus V curve of this electropolishing, in both the etching region and plateau region, we can see the passive layer. So to calculate the passive layer resistance, first we should calculate the voltage drop near the anode. So in etching, I took a voltage of 6 volt. So in that 6 volt, we'll see a 2 voltage volt drop near the anode. So it will give approximately 0.09 ohm. So if, and in plateau region, I took 18 voltage, and it will, anode voltage drop will be around 10. So here, in plateau region, at least 0.09 ohm of resistance will be there. And it can be maximum heat resistance will be, drop will go to till 10 voltage, which will give to 0.2 ohm. So heat load calculations are as follows. Due to chemical at 18 volt and 50 ampere temperature, due to chemical reactions, we can, these are the calculations. So minimum passive layer resistance is calculated using 0.09 and maximum using 500. In order to determine the actual heat load which is happening, we turned off the external cooling system. So we saw a temperature rise of 15 degrees in almost 950 seconds. So it will need a temperature total heat of this much, and our heat calculation minimum are in this range. So our experimental values are within the range of theoretical calculations. So these measurements will help us to optimize the EP process. Thank you.
Thank you for finishing on time, and thank you for a good presentation. So the next talk is going to be by Mr. S.V. Kokil. He will talk on development of second sound-based quench detection diagnostic system for SCRF cavities being processed at RRCAT. So five minutes total. So I will ring a bell after 3.5 minutes.
Okay, so good afternoon, everyone. I'll be presenting paper on development of second sound-based quench detection system for SCRF cavities being processed at RRCAT on behalf of my seniors. And the basic thing is that high beta SCRF cavities are made of high purity niobium, and they are processed well to get defect-free inner surface, because inner surface is the RF surface. And then the cavity may quench due to localized defects. So the detection of this localized defect in such a large cavity is a difficult task, and it is essential also so as to repair them and reprocess them. And there are two detection methods which are usually followed. One is the temperature mapping, which is connecting sensors around the cavities and know the temperature spot. The second system is the second sound system, which is based on the thermal wave of helium phase 1 and phase 2. So we are implementing the second sound system. The heart of this system is oscillating superlic transducers used to detect the second sound. The application of OSTs for quench spot detection is explained over here. And this is basically the construction of OSTs. The heart of the system is this nucleopore film, which is coated with gold. This film has a special property. It is a porous film. It allows helium of phase 2 to pass through on either side, but it will restrict that helium phase 1 on one side. So whenever there is some quench, there is a disturbance in this phase, helium 1 and helium 2. So you get the vibration on this particular neoprene ring. So this we have implemented, the gold coating is there on one side. The other side we have put this brass disc. They form a capacitor, and this vibration of this new nucleopore film, we measure in terms of capacitance. So because this capacitance we have biased with DC bias of 120, and the disturbance will get it signal conditioned and measure it with the data acquisition card. That is 1 megasamples per second, because the timing is important. The time we are really interested in timing of the quench signal and the oscillating signal. So these are the OSTs mounted on the cavity insert. This will be dipped in this 2K cryostat as explained by Manoj. So quench location detection procedure will be the data from OSTs and RF power signals was acquired using 1 megasamples per second data acquisition system. And the signals were displayed and monitored during the actual VTS test. And the GA is developed, and we can monitor them and save them for the future reference also. So the saved data is analyzed. This is the signals from the 4 OSTs. You can see it over here. I think the cursor and all those timings will not be able to see over here. But the delay time between this RF signal and the quench signal and the OSTs are measured. And accordingly, as per the 20 millimeters per second second sound speed, the distances were calculated. And the quench spot for one of the cavities, I have taken as example of single cell 104. The timings were like this. The spot was detected as this. And then this spot was inspected internally with the help of optical inspection badge. And this was the spot detected. So this is the defect actually. In conclusion, I can say that we have developed an OST where fabricated in a house, developed a quench detection system using OSTs. System was successfully used for quench spot detection in a single cell and 2 of the 5 cell SARF cavities where we observed the quench. And then the results were analogous with the temperature mapping system, which we are still implementing that also. And the defects were located by optical inspection bench. In some cases, even the optical inspection bench could not really pinpoint the defects. So we have taken the mold and they were inspected in 3D confocal microscope. So this is one of them. This is for one of the 5 cell cavities that we could see this, and this is the 3D confocal microscope result. So we would like to acknowledge Dr. Chandrachud Mukherjee and Sri Anand Yadav and team. And these are the references. So thank you.
Let us thank Dr. Kokil for a nice talk and for finishing on time. So the next talk is by Dr. Anirudh Bose. He will talk on nitrogen doping of niobium samples and its characterization studies for effective processing of superconducting RF cavities at RRCAT. So Dr. Bose, 5 minutes, and I will ring a bell after 3.5 minutes.
He said next to you.
Good afternoon. Good afternoon. So the topic of my presentation is nitrogen doping of niobium samples and its characterization studies for effective processing of superconducting RF cavities at RRCAT. So the outline of the talk includes the introduction, the challenges in nitrogen doping, and work done at RRCAT on nitrogen doping activity and its results. This is the typical processing cycle that is followed for high beta cavities at RRCAT, which includes these steps. The major steps that you can see is the bulk electropolishing, where actually hydrogen gets absorbed in the niobium surface, which needs to be removed by this fifth step, which is the hydrogen degassing or nitrogen doping. The standard baseline treatment includes this hydrogen degassing, whereas the improved version includes the hydrogen degassing plus the nitrogen doping at 800 degrees centigrade. The primary advantage of this process is that it increases the quality factor of the cavity, which actually is done by reducing the surface resistance. What is the nitrogen doping recipe? It is basically heating the cavity under vacuum at 800 degrees centigrade and soaking it at 3 hours. And then we inject this nitrogen gas at 25 millitorr for 2 minutes, then evacuate and soak it for 6 minutes, followed by cool down, which actually leads to 2 times of the Q compared to that of the dressed cavity, degassed cavity. Sorry. Where the Q basically becomes 2 times that of the degassed, hydrogen degassed cavity. So what happens when we inject this nitrogen gas is this nitrogen diffuses into the niobium matrix. And this nitrogen now transforms into 2 parts. First, it forms the crystalline nitrides on the niobium surface, which may be superconducting, may not be superconducting, depending on what type of niobium nitride phases are formed. And the rest part goes into the interstitials. Now, since these are non-superconducting, they need to be removed through the next cold electropolishing step, and this has to be measured as to how many microns to be removed based on the thickness, based on the depth up to which these crystalline nitrides are penetrating. And then we have to make sure that the nitrogen content that remains should be within this 40 to 100 ppm in the niobium matrix, so that there is an increase in the Q level. So what are the basic challenges? As you can see, this nitrogen injection, the purity of this gas has to be evaluated, and there has to be a technique that needs to be put in place. And the overall control of this nitrogen gas pressure during this 2 minutes also is important. Otherwise, it would lead to large number of different types of nitrides that would have varied depth, and there would be a variation in the performance depending on how much we are able to finally remove. So as you can see, the challenges are the purity of gas, its evaluation, duration, and its control. And subsequently, there would be one more challenge, that the contamination that could be inside the furnace due to the niobium cavity surface or furnace components prior to the start of doping process. And as I said, depending on this parameter, there would be difference in the nitride precipitation concentration and depth of doping, and subsequently material removal. This is the setting of nitrogen gas bleeding attachment. Basically, after a few iterations, we actually introduced this fine control valve and a manual valve, where we could basically evaluate the, basically qualify the nitrogen supply. And as you can see, we have qualified the LN2 Divar as well as the 5N purity cylinder, where you can see that once we bleed nitrogen from this Divar, there are other impurities that are coming into the picture. Apart from the increase of nitrogen. Whereas when we are using a 5N purity, we cannot see any other impurities. Now, coming to the doping studies, this is doped using the original bleeding setup that was there. And as you can see, there are lots of nitrides into this surface, whereas here we get a very clean nitride. And these nitrides are basically NB2N in a star-shaped precipitate, so which are very uniform. And they can be easily removed. This is the depth profile, where you can see there's a nitrogen depth profile and the carbon depth profile. The contamination in this case is slightly larger compared to this modified bleeding setup samples. And there is one more study that I have just put into this, is the effect of shielding on the nitrogen doping. Earlier, the cavities were nitrogen doped under non-shielded condition, where there was no caps placed on the flange faces, whereas here you can see there are shielded cavities. This is a process that has been followed by Fermilab. But what we found out is that due to this difference in the shielding, we can see the carbon contamination goes down the moment there is a shielding, and the nitrogen nitrogen concentration goes up. So that gives us a better chance of getting a more cleaner surface. And using this improved setup, we tried to dope a single cell cavity, which was already processed 4 times. The result summary before the doping trial, where the gradient was around limited to 12.8 megavolt, and the Q at maximum gradient was less than 1 into 10 to the power 10. Low field Q was less than 3 into 10 to the power 10, and field emission was on the slightly higher side. So this was then processed. So first the surface was reset, and nitrogen doping was done with this 2x6 recipe. And after with this improved setup, and we can see the results after the doping trial, where the gradient has increased and it has gone to 24.7 megavolt per meter. The quality factor is also increased, and it is 2.7. And the main factor, this is the RBCS, which has reduced to 1.5 to 2.4 nano, which is half of the standard EP treated cavities. So definitely this doping has led to higher improvement in the Q factor. And the low field Q, as you can see, is 4.32 compared to this 3. And the field emission was also on the lower side. So these are the results and the reference. Thank you.
Thank you, Dr. Bose, for a nice presentation. So the next talk is by Mr. Abhishek Jain. He will talk on efforts towards fabrication of 650 megahertz SCRF cavity using pulsed ND arc laser. So 5 minutes, I will ring a bell after 3.5 minutes.
Okay. Good afternoon to all of you. I am Abhishek Jain, and I will be presenting on behalf of my team that the efforts what we are making to make the fabrication of 650 megahertz cavity using pulsed ND arc laser. And we have already well proven this novel technique of fabrication by using pulse ND arc laser. And we have already developed a 1.3 gigahertz cavity, single cell cavity, and it was processed and tested at Fermilab, and it gave a exciting gradient of 31.6 megavolt per meter. And DAE has also taken the patent of this technology. And now I would like to highlight that why we delve into this technology, as there are some salient feature of this technology which because of low average power source of laser only, we will be able to make a good adequate weld seam with the help of peak power pulses. And because of this low average power only, we are able to get a very low heat affected zone. And there are some few advantages of this technology, which we have classified into two categories. One is economical and one is performance wise. Economical wise, we can say that very simple setup is there for welding of this cavity. That is very low. Capital cost is also very lowest, and operational cost will be also very lower. And the beauty of this technology is that the energy can travel through optical fiber. So multiple rigs can be fed with the same single source of laser, and because of that, that manufacturing time will be lesser. And performance wise, as I already said, that heat affected zone will be very lower because of low average power we are giving for making the weld seam. And there will be low distortion and low shrinkage, which will give a advantage of very less requirement of trimming and tuning of the during the multi-cell fabrication of the cavity. And obviously, we are doing this welding in a very inert gas atmosphere, so we can drive away the whatever the muck is generating there. That muck will be removed from that weld zone area, and we will get a very clean weld from there. This is a laser welding system which we are using, which is especially we have made our 1.3 gigahertz cavity in this rig only. And very simple laser source is there, which is tailor-made at in RRCAT itself. And it's a 1 kilowatt average power laser system, and the 600 joule of energy can be generated from a single pulse. And in millisecond range, we can give the pulse energy, and accordingly we can set the frequency of the pulses. And these are the results that we are seeing, that we can see that front side visual photograph is showing that very clean weld and ripples are showing, and back side we have smoothen pass we have given, and that smoothen pass is showing very clean weld. And by full penetration welding, we have confirmed it by metallography images, and metallographic images showing in lower images where we get the full penetration without any defect. And after completion of that experiments of full penetration depth, we have done a triple R measurement for the what triple R we are getting after this getting this full penetration depth. The triple R, which we are very excited. Okay, we have seen that triple R degradation is only in a very narrow zone, as you can see in the graph. It's only weld line से just 1.5 mm away तक में हमारा 300 से नीचे ट्रिपल आर जा रहा है, और that was our first attempt. So there is a scope of improving the triple R, and we will be doing the more experiments for improving the triple R. And finally, we have developed in concluding remarks, we have developed the parameters for full depth penetration of 3.4 mm thickness for making the 650 megahertz cavity, and we have qualified with the help of micrographs. Without any defect, we are getting the weld and the triple R also is showing the results, which is a very only 262 lower triple R we have got. And we will future will be more experiments, and triple R can be improved with the better handling of the sample, and we will be using ultra high pure gas for that. And in future we will be doing the experiments for making the other test also, the vacuum leak tightness test and tensile testing also will be done by STM E8 standards. And thank you.
Let us thank Mr. Abhishek Jain for a nice talk. So the next talk is by Dr. Rupul Ghosh. He will talk on development of horizontal test stand, cryostat, and shipment to Fermilab USA. So Dr. Rupul Ghosh, 5 minutes. I will ring a bell after 3.5 minutes.
Okay. Hello. Good afternoon. I am talking on development of horizontal test stand, cryostat, and shipment to Fermilab. So as an introduction, this STS cryostat is designed to test 650 megahertz desk cavities at 2K. One of the unit is already installed and commissioned at RRCAT, which has been shown in slides by Mr. Manoj Kumar. And initially, 2 units of STS cryostat were designed and fabricated under IFC collaboration in Indian industry. And such a big, huge and complex cryogenic system was first time fabricated in Indian industry by Messrs. Inox India. And this vendor development for STS cryostat will also help us in procurement of cryomodule for DA's program. And design was jointly done by RRCAT and Fermilab, and relevant codes and softwares were used for design and analysis of various subsystems. And the design was jointly reviewed by Fermilab and RRCAT. Here, this FitCan and cryostat is detachable type for ease of transportation because of its total size limit during road transport. And refrigeration capacity is about 50 watt at 2K when it is supplied with supercritical helium gas at 5 Kelvin and 3 bar. And there are different fabrication challenges of this cryostat and FitCan. It's some very large scale precision machining was done for this vacuum vessel and for multi-axis alignment. And also this cryogenics circuit that is inside, particularly this FitCan piping, was very complex, and where more than 150 numbers of weld joints and several dissimilar bridging joints were there. So the very stringent QAP and hole points were identified, and all those were implemented meticulously. And all weld joints were qualified with as per relevant ASME code. And this both the vessels of cryostat and FitCan were ASME U-stamp, and all the butt joints of cryogen piping and vessel shell, those were also fully radiographed. As you can see some glimpses of fabrication, particularly this cryogenic support post. This is also another important thing where there is no screw or glue kind of thing. It's a 3-component joints. And this integration and acceptance test is also another important thing, because this integration of cryostat with FitCan at this CF flanges, that is also critical part. And in spite of all this, the Lie rate of the cryogenic circuits were of the order of 10 to the power minus 9 milliliter per second after integration at 80K, which is better than acceptable limit of 10 to the power minus 8. And after successful commissioning of one unit, another unit has been recently shipped to Fermilab USA by sea. And for that, a comprehensive contract was given where that new transport frame was designed and fabricated, and packing and forwarding also to Indian vendor. And this for this transportation frame, this permissible limit after shock absorber was 4G, 2G, and 2G in vertical, long, and transverse direction. And shock absorber was selected for this each of the units, and 40 feet open top high tube container was used because of this maximum height was 2.67 meter of this unit. And container loading was done at RRCAT particularly to rule out any undesired shock event during port handling. And all circuits and vessels were pressurized with 0.5 bar dry nitrogen. And all the packing units were wrapped with heat-shrink plastic to give protection from snow or seawater. And fumigated wooden ply was used as per international requirement. And HTS cryostat, it's this 4.8 ton, and it used a total 8 number of shock absorber, and 1.6 ton feed can was used, has used 4 numbers of shock absorber. So one can see these different stages of packing. And finally, shipment was started from here on 19th February, and it is expected to reach there by middle of April. So in summary, it's a very complex and compactly designed 2K liquid helium test cryostat, which was successfully fabricated first time in Indian industry. And leak rate was of the order of 10 to the power minus 9 millibar liter per second. And this successful development and commissioning will also pave way for our new procurement for future cryomodules. And the STS unit will reach Fermilab probably by mid-April. Thank you.
Let us thank Dr. Rupul Ghosh for a nice talk. So the next presentation will be by Mr. Roshan Abhishek. He will talk on forming limit curve by Nakajima test on ETP copper samples for MEHIPA 1 SSRB structures. So 5 minutes. I will ring a bell after 3.5 minutes.
इससे भी next कर सकते हैं.
अच्छा. Hello everyone, good afternoon to all of you. I am Roshan Abhishek from IDD BRC, and I am going to discuss briefly on the topic establishing forming limit curve experimentally via Nakajima test for ETP copper as a part of development of SSRB cavity structures under MEHIPA project. So SSRB structures, superconducting SSRB structures are being developed in BRC under project MEHIPA, and they are manufactured through sheet metal operation of high RRR niobium sheets. So right now, due to scarcity of niobium sheets, we are coming up with prototype with ETP copper. So the ultimate objective is to design and optimize sheet metal operation, and design and optimize sheet metal operation, and that is being done through forming analysis. So forming analysis results are analyzed and used for process optimization. So optimization needs failure criteria. Just like in elastic range, we define failure criteria in terms of yield strength. In plastic range, we use strain values. So all those strain values at the onset of localized necking, they are joined, and the best fit line is the forming limit curve. So let's see the forming limit curve and try to understand it. So this is the curve, which is this is the plot between major and minor strain. So this is the value of major and minor strain at the onset of localized necking for complete set of boundary condition possible in any forming process. For example, the rightmost portion asymptotic to x is equal to y line, we have equi-biaxial stretching in which major and minor strengths are equal. Whereas in the leftmost part, we have that part corresponds to the uniaxial tensile test. So we have negative minor strain, reduced value, which is corresponding, which comes from Poisson's ratio value. And the middle portion where the curve is cutting y-axis is the plane strain condition where minor strain is 0. And interestingly, major strain has minimum value there. So this value is most important in our study. And I have tried to focus on this particular part. So we can see the sample, the material sample under test are cut in shape as per ISO standard. So we can see the various shape starting from the thinner most part, which correspond to the leftmost part, that is uniaxial tensile test. And at the last is the circular part, that is for equi-biaxial stretching. So and the other shapes corresponding to the remaining of the curve. So as we move from the thinner part to the fuller part, we are moving from leftward towards the rightmost part of the curve. So this is the Nakajima test setup, which is at the National Material Laboratory in Jamshedpur. So it has a punching machine and camera setup for measurement of dynamic measurement of strains. So on the samples, electrolytic grid are imprinted. The grid size is 1.5 mm, and hydraulic punch is applied, and strains are measured through camera, and they are post-processed through software. So this is the result I have obtained for 3 samples. For the upper 2 are for the plane strain area, and the third is for the biaxial area. And this result is post-processed into FLC curve. So this is the FLC curve I obtained from middle portion plane strain area to the biaxial area. So this so by this, I have successfully established the FLC for ETP copper, and the foundational step for future niobium-based forming has been established. So only thing I have to repeat this whole setup with high triple R niobium sheet. That is our future work. So that's the significance of my work here. Thank you.
Thank you, Mr. Roshan Abhishek, for a nice presentation and for finishing in time. So we come to the next talk, that is by Mr. Hemant Kumar Patel on comparative analysis of various thermal links for conduction cooled 650 megahertz single cell SCRF cavity. So 5 minutes. I will ring a bell after 3.5 minutes.
Yes. Good evening all. I'm Hemant Patel. Topic of my presentation is comparative analysis of various thermal links for conduction cooled SCRF cavity. I'm presenting this on behalf of complete SCDD team, and my younger colleague Viprajit Paul has contributed significantly in this work. He's also here. We both will be at the poster ID 1009 after this presentation. So the basic objective of this work is superconducting cavities. Whenever we talk about proton accelerator, but recent developments are there in high power electron beams, where superconducting cavities are used. And these high power electron beams, the beam accelerators, they are basically widespread use in industry, especially for societal applications such as wastewater treatment, flue gas treatment, cargo scanning and all. So for that purpose, the basic requirement is that these should be compact accelerators. So to make this superconducting cavities, superconducting accelerators as a compact, the first requirement comes is the cryogenic infrastructure. The cryogenic infrastructure takes up a lot of space. So if we can design a system where conduction-based cooling using a commercial cryocooler is used for superconducting cavities to achieve the 2K superconducting temperatures, cryogenic temperatures, then the size can be reduced considerably. So with that object, the main objective of this work is design a conduction link which can cool the cavities from cryocooler. And the basic requirement for a thermal link to perform its work is better thermal conductance, uniform temperature, and then maximum temperature of the cavity, minimum thermal mass, and as well as ease of assembly. With these objectives, the different geometrical models were prepared and analyzed for their different parameters. The first thing was material selection. So pure metals, high pure metals exhibits a very high thermal increase in thermal conductivity at cryogenic temperature. So that property has been utilized, and high purity aluminum 5N high purity aluminum has been selected for this work, and then temperature dependent thermal conductivity has been modeled. With this uniform temperature generation considered inside the cavity, and 13 different models were prepared with varying different parameters of the cavity. We started with some simple model where only 3 conduction links were taken. Then we increased it to 4. Then again, uniformity was not coming. Then we introduced one aluminum ring in between, whose results were very good. Then after optimizing simple geometry, we moved to the single point complete geometry. And then here again, we have optimized different thicknesses, their angular positions, and the width of the links. So with this, 13 different models were prepared, and their results were compared. So here you can see temperature along the beam axis, then temperature at the equator, and overall temperature distribution. All these were plotted for all the 13 models, and their comparison were made, and best possible model was selected. So what we conclude from our analysis was that aluminum ring attached to the niobium welding ring has a prominent effect in making the temperature uniform across the equator. Second thing was increasing the width of the link has a prominent effect, as it was increasing the area of contact compared to increasing the thickness of these individual links. So with this, another thing we played with was angular position, which didn't had a significant effect. And with all these analysis, considering thermal conductance, minimum thermal mass, and ease of assembly, model 8 was selected for our final model. And with this, this is for the single cavity model. Now future work will be to develop a thermal conduction link for a 5-cell cavity. Thank you. Please visit poster ID 1009 for further information. Thank you.
Thank you, Mr. Hemant Patel, for finishing on time and for a good talk. So then next and last talk for this session is by Mr. Manish Bagre. He will speak on initial efforts in development of niobium tin based SCRF cavities for particle accelerators. So 5 minutes. I will give a warning bell after 3.5 minutes.
Yeah. So good evening to all of you. The topic of my presentation is the initial effort in the development of NB3 SN based SCRF cavity for particle accelerator. And we have a team with the BRC also including in our team with the Raghavan Tiwari and sir and other members. And this presentation I'm giving on behalf of my team. So potential of NB3SN cavity, we are using an IBM cavity for SCRF cavity for fabrication of cavity is a big workhorse material. And IBM is a superconducting, is a 9 Kelvin. And the quality factor we are getting it at 4.2 Kelvin, 6 into 10 raised to power 8. So with the help of NB3SN is a much better choice, which has a critical temperature 18 Kelvin and which has a high magnetic field 420 millitesla instead of 240 millitesla for niobium. So if we can work with the help of NB3SN, we are getting the maximum is getting 100 megavolt per meter instead of the 55 megavolt per meter for niobium. So that these things, if we can successfully make the cavity, we can achieve those shorter accelerator, and we are getting the high energy accelerator, particle accelerator beam. And for this one, if we are operating our cavity in a state of 2 Kelvin, like in superfluid helium, if we operate at 4 Kelvin, so the cost will be reduced due to the high quality factor. The challenge and gap area in the development of NB3SN cavity. So RRCAT has expertise in development of niobium-based cavity, and NB3SN is the new technology which we are working right now. The main challenge is the brittleness of the NB3SN during the fabrication. So that's why it is making in the film of thin film. And NB3SN cavity performance is known to be permanently degrade when the stress is applied to the cavity. So that due to this degradation is caused in a crack in the material due to the brittleness of the NB3SN film, and which causes deformation in the cavity during the processing, such as the tuning as well as the assembly of the cavity. And very micron subsurface defect, which causes the quench, which converted into the super normal conducting state. And this cavity is elliptical in the geometry, which is very difficult in the nature to deposit the thin film on that, which is very great challenge for deposition. And right now we are in single cell. The geometry is very similar in state very, but this cavity is made in multi-cell. In our case, 5-cell cavities, which is very difficult to code because there are a lot of elliptical geometries. So in international, it is a development process. Not achieve the desired performance like in 100 megavolt per meter, but it is in the development process in the NB3SN cavity. International progress on NB3SN cavity. Internationally, there are other internationally other universities like Cornell, other Fermilab, JLab, and IMP China. They are working on the single cell R&D for this 1.3 and 1.5 cell cavity, and they have successfully achieved the accelerating gradient 25 megavolt per meter or 20 megavolt per meter with the Q of 10 raised to over 10. So they have demonstrated in the single cell and also in multi-cell cavity. They have demonstrated to achieve the accelerating gradient 16 megavolt per meter at 4.4 Kelvin. So NB3SN cavity is ready for accelerator application. In RRCAT, we are also working on the NB3SN thin film development on the flat sample. So this shows that we have done the scanning electron microscope for the cross-section of surface topology, and we achieved this deposit layer of 1.3 micron thick on NB3SN film on the niobium substrate of high RR niobium material. And we also did the X-ray photoelectron spectroscopy on the Beamline 14. And we got the atomic composition of 74.46 and SN composition of 25.54%, which is the formation of NB3SN phase on the film. And expected without consideration of other oxygen and carbon composition due to ambient. We also did the XRD in Beamline 2, and which shows the peak of NB3SN composition. This for TC measurement, this perform we got the 17.45 Kelvin temperature, which is done by the BRC in BRC, and we got the which is equivalent to the 18 Kelvin. So we are getting that very close to the 18 Kelvin. These are the results. So micrograph of the cross section and surface topology show the presence of 1.3 micron thick niobium on the niobium substrate. And this we perform on the flat sample, which is results are very encouraging, and critical temperature is also close to the 18 Kelvin. And in future plan, we are growing NB3SN flat film on the curved surface, which is our next target. And based on this, we have planned to do on the single cell niobium cavity for 1.3 gigahertz and 650 megahertz. And we will plan to test in BTS to qualify its 4 Kelvin and 2 Kelvin. And based on this, we will plan to explore the possibility of NB3SN based SCRF cavity for conduction cooled Linac, which is future application. Thank you.
Thank you, Mr. Manish Bhargavi. With this, we come to the end of this technical session. Let us thank all the speakers for making it a good technical session where we have generally complied with the time schedule set by the organizers.
यहाँ पे मीटिंग तो होगी नहीं.
Because a big hand.
लीव मीटिंग या फिर मेन मीटिंग में ज्वाइंड है.
Next, I will like to
मीटिंग
thank
से निकाल दूं.
K.K. Pant sir for conducting this session very smoothly. And I will like to invite Prashant Khare sir to present a memento to K.K. Pant sir. Prashant sir. So with this session ends.